Hey everyone, welcome to the captivating world of data science. In this comprehensive crash course by Simplilearn, we have a thrilling journey through the art of transforming raw data into valuable insights. Data science is the key to unlocking hidden patterns, making informed decisions, and shaping the future. From the fundamentals of data collection and cleaning to the advanced techniques of machine learning and predictive analytics, this course will empower you with the knowledge and skills to navigate through the data-driven landscape. Join us as we unravel the mysteries of data, equipping you to tackle the real-world challenges and innovate in a data-centric era. Get ready to dive into the heart of data science with endless possibilities await. Now, we will get through the agenda for today's session. We will get started by understanding data science fundamentals in 5 minutes. Followed by that, we will go through the top 5 reasons to learn data science in 2020. For all the aspiring data scientists, we have a perfect roadmap for data scientists in 2023. Next, the top 5 best courses to learn data science. Then we will get started with statistics with data science. Then we have a brief fundamental or tutorial for R programming language, and followed by the fundamentals of R programming language, we have data science with R. Next, we have a brief fundamental tutorial for Python. Then we have data science with Python. Followed by that, we will go through data science algorithms along with some examples. Then we have machine learning algorithms. And finally, to make things interesting, we will wrap up the session by going through some of the most frequently asked data science interview questions and answers. So I hope I made myself clear with the agenda. That said, if these are the type of videos you'd like to watch, then hit that subscribe button and the bell to get notified.
Are you one of the many who dreams of becoming a data scientist? Keep watching this video if you're passionate about data science, because we will tell you how does it really work under the hood. Emma is a data scientist. Let's see how a day in her life goes while she's working on a data science project. Well, it is very important to understand the business problem first. In our meeting with the clients, Emma asks relevant questions, understands and defines objectives for the problem that needs to be tackled. She's a curious soul who asks a lot of whys, one of the many traits of a good data scientist. Now, she gears up for data acquisition to gather and scrape data from multiple sources like web servers, logs, databases, APIs, and online repositories. Oh, it seems like finding the right data takes both time and effort. After the data is gathered comes data preparation. This step involves data cleaning and data transformation. Data cleaning is the most time-consuming process as it involves handling many complex scenarios. Here, Emma deals with inconsistent data types, misspelled attributes, missing values, duplicate values, and whatnot. Then, in data transformation, she modifies the data based on defined mapping rules. In her project, ETL tools like Talent and Informatica are used to perform complex transformations that helps the team to understand the data structure better. Then understanding what you actually can do with your data is very crucial. For that, Emma does exploratory data analysis. With the help of EDA, she defines and refines the selection of feature variables that will be used in the model development. But what if Emma skips this step? She might end up choosing the wrong variables, which will produce an inaccurate model. Thus, exploratory data analysis becomes the most important step. Now, she proceeds to the core activity of a data science project, which is data modeling. She repetitively applies diverse machine learning techniques like KNN, decision tree, naive Bayes to the data to identify the model that best fits the business requirement. She trains the models on the training dataset and tests them to select the best performing model. Emma prefers Python for modeling the data. However, it can also be done using R and SAS. Well, the trickiest part is not yet over: visualization and communication. Emma meets the clients again to communicate the business findings in a simple and effective manner to convince the stakeholders. She uses tools like Tableau, Power BI, and ClickView that can help her in creating powerful reports and dashboards. And then finally, she deploys and maintains the model. She tests the selected model in a pre-production environment before deploying it in the production environment, which is the best practice, right? After successfully deploying it, she uses reports and dashboards to get real-time analytics. Further, she also monitors and maintains the project's performance. Well, that's how Emma completes the data science project. We have seen the daily routine of a data scientist is a whole lot of fun, has a lot of interesting aspects, and comes with its own share of challenges. Now, let's see how data science is changing the world. Data science techniques along with genomic data provides a deeper understanding of genetic issues in reaction to particular drugs and diseases. Logistic companies like DHL, FedEx have discovered the best routes to ship, the best suited time to deliver, the best mode of transport to choose, thus leading to cost efficiency. With data science, it is possible to not only predict employee attrition, but to also understand the key variables that influence employee turnover. Also, the airline companies can now easily predict flight delay and notify the passengers beforehand to enhance their travel experience. Well, if you're wondering, there are various roles offered to a data scientist, like data analyst, machine learning engineer, deep learning engineer, data engineer, and of course, data scientist. The median base salaries of a data scientist can range from $95,000 to $165,000. So that was about the data science. Are you ready to be a data scientist? If yes, then start today. The world of data needs you.
Technological advancement has offered us seamless connectivity, and the advent of smartphones and connected devices worldwide has elevated the gravitas at which the data is generated every minute. Zettabytes of data, endless data lakes and server farms, billion-dollar investments, stakeholders, CMOs, CTOs and CEOs. Everyone is dependent on one detailed report that data scientist delivers. A wise decision backed by data research and analysis can yield prospering results. Still, on the contrary, one wrong marketing decision, one misinterpreted detail could be a good recipe for a catastrophic financial disaster for an organization. That's the pivotal role a data scientist plays in any organization. A data scientist's caliber to devise algorithms to crunch numbers and extract precious information is invaluable. This is one good reason why data science is reported as the top IT profession in the current IT industry and is projected to be on the top for a good time. Welcome to Simplilearn's YouTube channel. Today, we will explain why you should learn data science. Before we get started, take a moment to subscribe to us and hit the bell to get notified of our content. If you're watching this, I'm sure you are interested in data science, looking for a flexible and online training program that better suits you like a glove and helps you get ahead in your career. Well, IT firms are venturing into data science, recognizing its potential to open the doors to a wide spectrum of opportunities. It enables enterprises to monitor and report performance metrics to facilitate heightened and reinforced decision making. Organizations can now analyze trends to make critical decisions to engage clients better, enhance company performance, boost productivity, and increase profitability. The organizational importance of data science is increasing at a relentless pace. The global data science platforms market is poised to grow at a CAGR of 16.43%, more than any other industry. Converging to IT, data science facilitates it with its power to extract information from larger volumes of data. Information technology makes our life easier by gathering and processing more data quickly and efficiently to provide results in minutes and hours, unlike days and weeks. Statistics and science have become the answer to complex data. Data science enables tapping and analyzing massive amounts of untapped data from many sources to leverage productivity and profitability. This is one good reason why many tech aspirants find data science to be the most interesting job profile. Apart from the IT domain, data science has spread its roots into other fields. For instance, the healthcare sector is more inclined towards data science and artificial intelligence to diagnose and treat the most complicated syndromes and robots to perform the most tedious surgeries. Online stores and shopping websites depend solely on data science to manage the supply chain and enhance the user experience by recommending the right product. Data science plays a pivotal role in transportation and logistics. It provides customized recommendations to best suit customers' comfort and manages unexpected circumstances using predictive analytics. Geographical experts, weather reports, and many more employ data science to predict seismic events, reservoir behavior, climate interpretation, water buoys to enable navigation, and more. Construction companies are integrating their process with data science to enhance plotting, constructing, and automating tasks to build better, faster, and bigger projects in the most efficient way possible. In the ever-evolving field of data science, new advancements and discoveries in research accelerate rapidly. You always get to learn something new, making every day's work exciting. New data science skills can be acquired endlessly, giving you a competitive edge with knowledge and expertise. The salary of a data scientist in India ranges from 15 to 25 lakhs per annum. And in the United States of America, the salaries range from $150,000 to $250,000 per annum. Depicting the future of data science results in an unmatched potential to settle in a secure job role. As the field expands, more jobs should become available as more data scientists are needed for analysis. Individuals wishing to pursue a career in data science can look forward to a bright future with data science. Data science has a huge scope across all industries. The global market for data science is expected to grow all the way up to $230 billion by early 2026. 2026, opening the gates for about 11 million data scientist job roles. Another important aspect of the future of data science is artificial intelligence. AI will likely to be most powerful technology data scientists will have to deal with in the future. To put it another way, the future of data science will align itself to make it better in the long run. To become a data scientist, the professionals in the organizations need to have healthy data literacy, powerful programming skills, mathematics, statistics, logic building skills, strong foundations in data cleaning, and a comfortable understanding of data visualization and machine learning algorithms. Handling all these are nothing less than herding cats. One skill gap could be the final nail in the coffin. If you are an aspiring data scientist looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Just grab Simplilearn's postgraduate program in data science from Purdue University in collaboration with IBM. That should be your right choice. For more details, use the link.
Google had gathered 5 exabytes of data between the beginning of time 2003. This amount of data started to be produced every 2 days in 2010 and every 40 minutes by 2021. The responsibility of a data scientist is to gather, clean and present data and have a keen business sense and analytical abilities. Let us have a discussion about it in the upcoming slides. How can you become a data scientist as a beginner? I guarantee you, after watching this video, you will have a clear understanding on how to drive your career as a data scientist. Hey guys, welcome to Simplilearn. Before proceeding, please make sure you subscribe to Simplilearn's YouTube channel and press the bell icon to never miss any updates. Today we are going to cover significance of data scientists in industries. After that, prerequisites and technologies required for a data scientist. And finally, salary of a data scientist. I have a query for you. Which technology is used by Google Maps to predict traffic jams? Deep learning, machine learning, natural language processing, data structure. Please leave the answer in the comment section below. And stay tuned to get the answer. Significance. Now we will see how top industries are involved in the field of data science. By 2025, the data science industry is anticipated to grow to a value of $16 billion. There is an abundance of data science jobs all over the world. Now let's list out crucial areas where data science is used. Media and entertainment. The major player in the media and entertainment sector such as YouTube, Netflix, Hotstar, etc. have begun to use data science to better understand their audience and provide them with recommendations that are both relevant and personalized. E-commerce. Data science has aided retail companies in better meeting their expectations. As they bring a unique combination of deep data knowledge, technology skills, and statistical experience, data scientists are in high demand in the retail industry. Top recruiters are Amazon, Flipkart, Walmart, Myntra, etc. Digital marketing. Large volumes of data are currently being fetched from its users through search pages, social networks, online traffic display networks, movies, web pages, etc. A high level of business intelligence is needed to analyze such large amount of data, and this can only be done with the proper use of data science approaches. Top recruiters are Amazon, Flipkart, Facebook, Google, etc. Cybersecurity. Data science and AI are now being used by the cybersecurity industry to prevent the growing usage of algorithms for harmful purposes. Top recruiters includes IBM, Microsoft, Accenture, Cisco, and many more. Before moving forward, what is the response to the Google Map question that I asked? Answer is machine learning. Coming to prerequisites. Now that we know significance of data science in industries, let us explore the prerequisites and technologies required for a data scientist. Seeing the demand of data scientists in every industry, it is obvious that the scope of a data scientist is very high. So, how to start? There is no necessity that you should be knowing any technology or programming language. You can be a layman too. Data scientists typically have a variety of educational and professional experiences. Most should be proficient in 4 crucial areas. Important skill is mathematical expertise. 3 concepts like linear algebra, multivariable calculus, and optimization technique are crucial because they aid in our understanding of numerous machine learning algorithms that are crucial to data science. Similar to that, knowing statistics is crucial because they are used in data analysis. Additionally, important to statistics, probability is regarded as a must for mastering machine learning.
Next is computer science. In the field of computer science, there is a lot to learn. But one of the key inquiries that arises in relation to programming is R or Python language. There are many factors to consider when deciding which language to choose for data science because both have a comprehensive collection of libraries to implement complex machine learning algorithms. In addition to learning a programming language, you should learn the following computer science skill: fundamentals of algorithm and data structures, distributed computing, machine learning, deep learning, Linux, SQL, MongoDB, etc. Domain expertise. Most individuals wrongly believe that domain expertise is not crucial to data science, yet it is. Consider the following scenario. If you are interested in working as a data scientist in the banking industries and you already know a lot about it. For instance, you are knowledgeable about stock trading, finance, etc. This will be very advantageous for you, and the bank itself will favor you over other applicants. And finally, communication skill. It covers both spoken and written communication. In a data science project, the project must be explained to others when findings from the analysis have been reached. This can occasionally be a report that you provide to your team or employer at work. Sometimes it might be a blog entry. It is frequently a presentation to a group of co-workers. Regardless, a data science project always involves some form of communication of the project's findings. Therefore, having a good communication skill is a requirement for being a data scientist. Apart from all this, practicing is very important. Keep using different tools. Also start reading blogs on data science. Start building projects on data science which can be added to your resume. Also, you can find many interesting courses on data science by Simplilearn. Salary reward is the result of good work. Now we shall discuss salaries that a data scientist will get. It should come as no surprise that data scientists may add significantly to a business. Every step of the process, from data processing to data cleansing, requires persistence, a lot of arithmetic and statistics, as well as scattering of engineering skills. One of the most important factors in a data scientist's salary is experience. At the beginner level, a data scientist can make $95,000 annually. The typical annual compensation for a mid-level data scientist is between $130,000 and $195,000. A seasoned data scientist typically earns between $165,000 and $250,000 per year. In India, at the beginner level, a data scientist can make 9,40,000 rupees on average per year. At mid-level, data scientists will get 20 lakhs rupees per annum. And if you are at the advanced level, you will get paid an average of rupees 25 lakhs annually. This salary will vary in different countries. The top hiring businesses in the US that provide the highest salaries for data scientists are Apple with $180,000 per annum. Next is Twitter with $170 per annum. Meta Technology $170 annually. LinkedIn $160,000 per annum. Wipro Technology provides 17,50,000 per annum. IBM provides 14 lakhs per annum. And Accenture will provide you with 19 lakhs per annum. And finally, American Express will provide on average of 13 lakhs per annum.
Now, before we move ahead with the session, if you are a professional with minimum 1 year of experience and aspiring data scientist looking for online training and certifications from leading experts, then search no more. Simplilearn's Master's course in Data Science in collaboration with IBM should be your right choice. For more details, use the link in the description box below.
No matter if you're recently graduated, have experience in the IT field, or are seeking a career change, these courses in data science will provide you with the necessary foundation to pursue a successful career in data science. Obtaining an education in data science can open doors to various job opportunities such as data analyst, data engineer, data architect, or data scientist. Your specific path in data science will depend on your skills and interests. However, all these career paths require a certain level of proficiency in programming, data visualization, statistics, and machine learning. Data engineers and data architects primarily work with coding, databases, and intricate queries, while data analysts and data scientists focus on analyzing, collecting, and interpreting large data sets to aid in making informed business decisions. It is a rapidly expanding and financially rewarding career path, with data scientists reporting an average annual salary of $130,000 in the United States, and in India it is 12 lakhs per annum. In this Simplilearn video on top courses for data science science, we will explore some of the top courses in data science, including Wharton, Purdue, IIT Kanpur. Purdue is a public research university located in West Lafayette, Indiana. The university's Department of Computer Science offers a data science program covering data mining, machine learning, and statistical modeling. Well, with Simplilearn's postgraduate program in data science, in partnership with Purdue University and in collaboration with IBM, you can have the opportunity to take the advantage of master classes by Purdue faculty and IBM experts, exclusive hackathons, and Ask Me Anything sessions by IBM. This program in data science is perfect for working professionals, and it focuses on essential job skills like R and Python programming, machine learning, NLP, and data visualization with Tableau. To prepare for the job market, you will learn all this through live sessions with experts, hands-on labs, IBM hackathons, and corporate projects. This course will also provide you with the data science certificate from Purdue, the 8th most innovative university in the US, along with IBM certificates from IBM courses. With this, you will also get a chance to build your resume and prepare your interviews with valuable insights from industry experts and 25 plus industry relevant projects from Amazon, Walmart, Uber, and Mercedes-Benz. You can find the link to this course in the description box. And the third one, Wharton. Wharton is a global technology company that has been a leader in the data science field for decades. In addition to offering a range of data science solutions and tools, Wharton also provides training and education in data science. This AI program, in collaboration with Wharton, impacts in-depth knowledge of big data, AI, and machine learning, and how to apply them across the three key business functions: marketing, finance, and people management. This program also covers the risks and ethics of using AI and how you can design governance frameworks for effective AI implementation. Apart from this, you will gain a certificate from Wharton Online, the Wharton School's digital learning platform, and you will learn how AI can be applied across business functions such as marketing, finance, HR, and you will also be having live master classes from top Wharton faculty and get insights on how AI is utilized across companies like McDonald's, Visa, and Citigroup. This program is designed to equip students with the skills and knowledge needed to succeed in this fast-growing field and become a data scientist by diving deep into the nuances of data interpretation, mastering technologies like machine learning, and mastering powerful programming skills to take your career in data science to the next level. Also, the link for this course is mentioned in the description box. Following that, we have IIT Kanpur. The Indian Institute of Technology Kanpur is one of the top engineering schools in India, known for its strong focus on research and innovation. The institute's Department of Computer Science and Engineering is one of the most popular universities offering data science courses. Taking advantage of such resourceful alumni, Simplilearn provides a professional certificate course in data science in collaboration with IIT Kanpur, mastering essential data science skills through applied learning with live classes by industry experts, asynchronous videos, hands-on labs, and master classes from distinguished IIT Kanpur faculty. Along with that, you will get hands-on experience on 25 plus industry relevant projects from the likes of Walmart, Amazon, Uber, Mercedes-Benz, and many more, along with career mentorship and profile building sessions with valuable insights from industry experts. This course is designed with a carefully curated curriculum that includes critical topics like Python, machine learning, NLP, and data visualization, delivered using hands-on labs and industry-relevant projects to help you advance your career trajectory. This data science course in India aims to demystify data science. The link is mentioned in the description box. And the last one is SPJMIR. SPJN Institute of Management and Research is a leading business school located in Mumbai, India. The institute's Business Intelligence and Analytics program is designed to provide students with a strong foundation in data science, analytics, and business intelligence. Therefore, Simplilearn has collaborated with SPGMIR to design the Data Science for Business Decisions program that will help you learn this in-demand skill set and turn yourself into a data-driven decision maker to optimize your organization's performance. This program enables you to master the concepts of machine learning, statistics, data visualization, etc., and create a strategy to implement a data science project in your organization. This program will help you drive digital transformation in your organization by understanding data privacy, data architecture, and governance. You will also earn a program completion certification from SPJMIR, a leading school of management in India, and master the concepts of data science through live sessions delivered by SPJMIR faculty. You will also bag an opportunity to avail of SPJMIR Executive Alumni Network membership post-program completion, hands-on experience on multiple projects, and a capstone pertaining to various industry domains. The link is mentioned below in the description.
Let's begin this lesson by defining the term statistics. Statistics is a mathematical science pertaining to the collection, presentation, analysis, and interpretation of data. It's widely used to understand the complex problems of the real world and simplify them to make well-informed decisions. Several statistical principles, functions, and algorithms can be used to analyze primary data, build a statistical model, and predict the outcomes. An analysis of any situation can be done in two ways: statistical analysis or a non-statistical analysis. Statistical analysis is the science of collecting, exploring, and presenting large amounts of data to identify the patterns and trends. Statistical analysis is also called quantitative analysis. Non-statistical analysis provides generic information and includes text, sound, still images, and moving images. Non-statistical analysis is also called qualitative analysis. Although both forms of analysis provide results, statistical analysis gives more insight and a clearer picture, a feature that makes it vital for businesses. There are two major categories of statistics: descriptive statistics and inferential statistics. Descriptive statistics helps organize data and focuses on the main characteristics of the data. It provides a summary of the data numerically or graphically. Numerical measures such as average, mode, standard deviation or SD, and correlation are used to describe the features of a dataset. Suppose you want to study the height of students in a classroom. In the descriptive statistics, you would record the height of every person in the classroom and then find out the maximum height, minimum height, and average height of the population. Inferential statistics generalizes the larger dataset and applies probability theory to draw a conclusion. It allows you to infer population parameters based on the sample statistics and to model relationships within the data. Modeling allows you to develop mathematical equations which describe the interrelationships between two or more variables. Consider the same example of calculating the height of students in the classroom. In inferential statistics, you would categorize height as tall, medium, and small, and then take only a small sample from the population to study the height of students in the classroom. The field of statistics touches our lives in many ways, from the daily routines in our homes to the business of making the greatest cities run. The effect of statistics are everywhere. There are various statistical terms that one should be aware of while dealing with statistics: population, sample, variable, quantitative variable, qualitative variable, discrete variable, continuous variable. A population is the group from which data is to be collected. A sample is a subset of a population. A variable is a feature that is characteristic of any member of the population differing in quality or quantity from another member. A variable differing in quantity is called a quantitative variable. For example, the weight of a person, number of people in a car. A variable differing in quality is called a qualitative variable or attribute. For example, color, the degree of damage of a car in an accident. A discrete variable is one which no value can be assumed between the two given values. For example, the number of children in a family. A continuous variable is one in which any value can be assumed between the two given values. For example, the time taken for a 100-meter run. Typically, there are four types of statistical measures used to describe the data. They are measures of frequency, measures of central tendency, measures of spread, measures of position. Let's learn each in detail. Frequency of the data indicates the number of times a particular data value occurs in the given dataset. The measures of frequency are number and percentage. Central tendency indicates whether the data values tend to accumulate in the middle of the distribution or toward the end. The measures of central tendency are mean, median, and mode. Spread describes how similar or varied the set of observed values are for a particular variable. The measures of spread are standard deviation, variance, and quartiles. The measure of spread are also called measures of dispersion. Position identifies the exact location of a particular data value in the given data set. The measures of position are percentiles, quartiles, and standard scores. Statistical Analysis System, or SAS, provides a list of procedures to perform descriptive statistics. They are as follows: proc print, proc contents, proc means, proc frequency, proc univariate, proc g-chart, proc box plot, Proc gplot. Proc print. It prints all the variables in a SAS dataset. Proc contents. It describes the structure of a dataset. Proc means. It provides data summarization tools to compute descriptive statistics for variables across all observations and within the groups of observations. Proc frequency. It produces one-way to n-way frequency and cross-tabulation tables. Frequencies can also be an output of a SAS dataset. Proc univariate. It goes beyond what proc means does and is useful in conducting some basic statistical analyses and includes high-resolution graphical features. Proc gchart. The gchart procedure produces 6 types of charts: block charts, horizontal, vertical bar charts, pie, donut charts, and star charts. These charts graphically represent the value of a statistic calculated for one or more variables in an input SAS dataset. The charted variables can be either numeric or character. Proc boxplot. The boxplot procedure creates side-by-side box and whisker plots of measurements organized in groups. A box and whisker plot displays the mean, quartiles, and minimum and maximum observations for a group. Proc gplot. Gplot procedure creates two-dimensional graphs, including simple scatter plots, overlay plots in which multiple sets of data points are displayed on one set of axes, plots against a second vertical axis, bubble plots, and logarithmic plots. In this demo, you'll learn how to use descriptive statistics to analyze the mean from the electronic dataset. Let's import the electronic dataset into the SAS console. In the left plane, right-click the electronic.xlsx dataset and click Import Data. The code to import the data generates automatically. Copy the code and paste it in the new window. The proc means procedure is used to analyze the mean of the imported dataset. The keyword data identifies the input dataset. In this demo, the input dataset is electronic. The output obtained is shown on the screen. Note that the number of observations, mean, standard deviation, and maximum and minimum values of the electronic dataset are obtained. This concludes the demo on how to use descriptive statistics to analyze the mean from the electronic dataset. So far, you have learned about descriptive statistics. Let's now learn about inferential statistics. Hypothesis testing is an inferential statistical technique to determine whether there is enough evidence in a data sample to infer that a certain condition holds true for the entire population. To understand the characteristics of the general population, we take a random sample and analyze the properties of the sample. We then test whether or not the identified conclusions correctly represent the population as a whole. The population of hypothesis testing is to choose between two competing hypotheses about the value of a population parameter. For example, one hypothesis might claim that the wages of men and women are equal, while the other might claim that women make more than men. Hypothesis testing is formulated in terms of two hypotheses: null hypothesis, which is referred to as H-null; alternative hypothesis, which is referred to as H1. The null hypothesis is assumed to be true unless there is strong evidence to the contrary. The alternative hypothesis is assumed to be true when the null hypothesis is proven false. Let's understand the null hypothesis and alternative hypothesis using a general example. Null hypothesis attempts to show that no variation exists between variables, and alternative hypothesis is any hypothesis other than the null. For example, say a pharmaceutical company has introduced a medicine in the market for a particular disease, and people have been using it for a considerable period of time, and it's generally considered safe. If the medicine is proved to be safe, then it is referred to as null hypothesis. To reject null hypothesis, we should prove that the medicine is unsafe. If the null hypothesis is rejected, then the alternative hypothesis is used. Before you perform any statistical tests with variables, it's significant to recognize the nature of the variables involved. based on the nature of the variables. It's classified into 4 types. They are categorical or nominal variables, ordinal variables, interval variables, and ratio variables. Nominal variables are ones which have 2 or more categories, and it's impossible to order the values. Examples of nominal variables include gender and blood group. Ordinal variables have values ordered logically. However, the relative distance between 2 data values is not clear. Examples of ordinal variables include considering the size of a coffee cup, large, medium, and small, and considering the ratings of a product, bad, good, and best. Interval variables are similar to ordinal variables, except that the values are measured in a way where their differences are meaningful. With an interval scale, equal differences between scale values do have equal quantitative meaning. For this reason, an interval scale provides more quantitative information than the ordinal scale. The interval scale does not have a true 0 point. A true 0 point means that a value of 0 on the scale represents 0 quantity of the construct being assessed. Examples of interval variables include the Fahrenheit scale used to measure temperature and distance between 2 compartments in a train. Ratio scales are similar to interval scales in that equal differences between scale values have equal quantitative meaning. However, ratio scales also have a true 0 point, which give them an additional property. For example, the system of inches used with a common ruler is an example of a ratio scale. There is a true 0 point because 0 inches does in fact indicate a complete absence of length. In this demo, you'll learn how to perform the hypothesis testing using SAS. In this example, let's check against the length of certain observations from a random sample. The keyword data identifies the input dataset. The input statement is used to declare the aging variable and cards to read data into SAS. Let's perform a t-test to check the null hypothesis. Let's assume that the null hypothesis to be that the mean days to deliver a product is 6 days. So null hypothesis equals 6. Alpha value is the probability of making an error, which is 5% standard, and hence alpha equals 0.05. The variable statement names the variable to be used in the analysis. The output is shown on the screen. Note that the p-value is greater than the alpha value, which is 0.05. Therefore, we fail to reject the null hypothesis. This concludes the demo on how to perform the hypothesis testing using SAS. Let's now learn about hypothesis testing procedures. There are 2 types of hypothesis testing procedures. They are parametric tests and non-parametric tests. In statistical inference or hypothesis testing, the traditional tests, such as t-test and ANOVA, are called parametric tests. They depend on the specification of a probability distribution except for a set of free parameters. In simple words, you can say that if the population information is known completely by its parameter, then it is called a parametric test. If the population or parameter information is not known, and you are still required to test the hypothesis of the population, then it's called a non-parametric test. Non-parametric tests do not require any strict distributional assumptions. There are various parametric tests. They are as follows: t-test, ANOVA, chi-squared, linear regression. Let's understand them in detail. T-test. A t-test determines if 2 sets of data are significantly different from each other. The t-test is used in the following situations: to test if the mean is significantly different than a hypothesized value, to test if the mean for 2 independent groups is significantly different, to test if the mean for two dependent or paired groups is significantly different. For example, let's say you have to find out which region spends the highest amount of money on shopping. It's impractical to ask everyone in the different regions about their shopping expenditure. In this case, you can calculate the highest shopping expenditure by collecting sample observations from each region. With the help of the t-test, you can check if the difference between the regions are significant or a statistical fluke. ANOVA. ANOVA is a generalized version of the t-test and used when the mean of the interval dependent variable is different to the categorical independent variable. When we want to check variance between two or more groups, we apply the ANOVA test. For example, let's look at the same example of the t-test example. Now you want to check how much people in various regions spend every month on shopping. In this case, there are four groups, namely East, West, North, and South. With the help of the ANOVA test, you can check if the difference between the regions is significant or a statistical fluke. Chi-square. Chi-square is a statistical test used to compare observed data with data you would expect to obtain according to a specific hypothesis. Let's understand the chi-square test through an example. You have a data set of male shoppers and female shoppers. Let's say you need to assess whether the probability of females purchasing items of $500 or more is significantly different from the probability of males purchasing items of $500 or more. Linear regression. There are two types of linear regression: simple linear regression and multiple linear regression. Simple linear regression is used when one wants to test how well a variable predicts another variable. Multiple linear regression allows one to test how well multiple variables, or independent variables, predict a variable of interest. When using multiple linear regression, we additionally assume the predictor variables are independent. For example, finding a relationship between any two variables, say sales and profit, is called simple linear regression. Finding a relationship between any three variables, say sales, cost, and telemarketing, is called multiple linear regression. Some of the non-parametric tests are Wilcoxon rank sum test and Kruskal-Wallis H-test. Wilcoxon rank sum test. The Wilcoxon signed rank test is a non-parametric statistical hypothesis test used to compare two related samples or matched samples to assess whether or not their population mean ranks differ. In Wilcoxon rank sum test, you can test the null hypothesis on the basis of the ranks of the observations. Kruskal-Wallis H-test. Kruskal-Wallis H-test is a rank-based non-parametric test used to compare independent samples of equal or different sample sizes. In this test, you can test the null hypothesis on the basis of the ranks of the independent samples.
Hello everyone. Welcome to this video on R4 Data Science full course. Today, we have our experienced instructors Richard, Ajay, and Pete Ferrari, who will help us learn everything from basics to advanced and master data science in R. We will start by learning data science from an animated video. You will then learn the essential concepts in data science and understand the important packages in R for data science such as dplyr and tidyr. You will look at some of the widely used data science algorithms such as linear regression, logistic regression, decision trees, random forests, including time series analysis. Finally, you will get an idea about the salary structure, skills, jobs, and resume of a data scientist.
Are you one of the many who dreams of becoming a data scientist? Keep watching this video if you're passionate about data science, because we will tell you how does it really work under the hood. Emma is a data scientist. Let's see how a day in her life goes while she's working on a data science project. Well, it is very important to understand the business problem first. In her meeting with the clients, Emma asks relevant questions, understands and defines objectives for the problem that needs to be tackled. She's a curious soul who asks a lot of whys, one of the many traits of a good data scientist. Now, she gears up for data acquisition to gather and scrape data from multiple sources like web servers, logs, databases, APIs, and online repositories. Oh, it seems like finding the right data takes both time and effort. After the data is gathered comes data preparation. This step involves data cleaning and data transformation. Data cleaning is the most time-consuming process as it involves handling many complex scenarios. Here, Emma deals with inconsistent data types, misspelled attributes, missing values, duplicate values, and whatnot. Then, in data transformation, she modifies the data based on defined mapping rules. In her project, ETL tools like Talent and Informatica are used to perform complex transformations that helps the team to understand the data structure better. Then understanding what you actually can do with your data is very crucial. For that, Emma does exploratory data analysis. With the help of EDA, she defines and refines the selection of feature variables that will be used in the model development. But what if Emma skips this step? She might end up choosing the wrong variables, which will produce an inaccurate model. Thus, exploratory data analysis becomes the most important step. Now, she proceeds to the core activity of a data science project, which is data modeling. She repetitively applies diverse machine learning techniques like KNN, decision tree, naive Bayes to the data to identify the model that best fits the business requirement. She trains the models on the training dataset and tests them to select the best performing model. Emma prefers Python for modeling the data. However, it can also be done using R and SAS. Well, the trickiest part is not yet over: visualization and communication. Emma meets the clients again to communicate the business findings in a simple and effective manner to convince the stakeholders. She uses tools like Tableau, Power BI, and ClickView that can help her in creating powerful reports and dashboards. And then finally, she deploys and maintains the model. She tests the selected model in a pre-production environment before deploying it in the production environment, which is the best practice, right? After successfully deploying it, she uses reports and dashboards to get real-time analytics. Further, she also monitors and maintains the project's performance. Well, that's how Emma completes the data science project. We have seen the daily routine of a data scientist is a whole lot of fun, has a lot of interesting aspects, and comes with its own share of challenges. Now, let's see how data science is changing the world. Data science techniques along with genomic data provides a deeper understanding of genetic issues in reaction to particular drugs and diseases. Logistic companies like DHL, FedEx have discovered the best routes to ship, the best suited time to deliver, the best mode of transport to choose, thus leading to cost efficiency. With data science, it is possible to not only predict employee attrition, but to also understand the key variables that influence employee turnover. Also, the airline companies can now easily predict flight delay and notify the passengers beforehand to enhance their travel experience. Well, if you're wondering, there are various roles offered to a data scientist, like data analyst, machine learning engineer, deep learning engineer, data engineer, and of course, data scientist. The median base salaries of a data scientist can range from $95,000 to $165,000. So that was about the data science. Are you ready to be a data scientist? If yes, then start today. The world of data needs you. That's all from my side today. Thank you for watching. Comment below the next topic that you want to learn and subscribe to Simplilearn to get the latest updates on more such interesting videos.
Data Science with R, sponsored by Simplilearn. That's www.simplilearn.com. Get certified, get ahead. My name is Richard Kirshner and I'm with the Simplilearn team. What's in it for you? We're going to go through an introduction to R, why R, CRAN, Comprehensive R Archive Network, and cover installing R. Then we'll get into simple linear regression using R, line of best fit using error summation, correlation analysis in R, and then we'll get into classification using R. Use case, predict the class of a flower. Let's start with an introduction to R. First, it's an open source. R is completely free and open source with active community members. Extensible. It offers various statistical and graphical techniques. Compatible. R is compatible across all platforms, Linux, Windows, and Mac. Library. R has an extensive library of packages for machine learning. Easy integration. It can be easily integrated with popular softwares like Tableau, SQL Server, etc. This only touches a little bit on these different aspects of R. The fact that it's it's very extensive. It probably has one of the most extensive set of data analysis packages currently out. It has a compatibility that is continually growing, so it's integrated with everything from cluster computing to Python integration, which is now coming out. And its extensive libraries allows you to import the different libraries to use for whatever your needs are. Makes it a very diverse and easy to use coding source for analyzing data. R is more than just a programming language. As I just touched upon it, it has a worldwide repository system, comprehensive R archive network, and it can be accessed at https://cran.rproject.org. It provides up-to-date versions of code and documentation for R. CRAN hosts around 10,000 packages of R. That is a huge repository focused on just data analytics. Let's install R to get started. You can easily download the executable file for R and install it from CRAN website. If you go under the downloads, in this case since I'm on a Windows machine, we'll walk through it from the R 3.5 version for Windows. So here we are at https://cran.r-project.org, and you can see down here we have the different options for the downloads. If we go under Windows, which is I'm on a Windows machine, if you're on a Mac machine you can do the Mac or Linux. There's install R for the first time. Just click on that and open and run it. The installation is pretty simple. Follow the default options to finish the installation. After the installation is complete, you'll see the R icon on your desktop. Alternatively, there are mirror sites, and so we can go into RStudio. Let's just take a quick look at that. If you're on the RStudio website, that's www.rstudio.com, you can go down under Products and RStudio Download. You'll see a number of options here. The first one is the RStudio Desktop Open Source License.
Now, before we move ahead with the session, if you are a professional with minimum 1 year of experience and an aspiring data scientist looking for online training and certifications from the prestigious universities in collaboration with leading experts, then search no more. Simplilearn's professional certificate course in data science from IIT Kanpur University should be your right choice. For more details, use the link in the description box below.
Quick note, if you're a Debian distribution, including Ubuntu, you can install R using its regular package management tools. And when you're using a Linux system, that is preferred because then it registers it properly on the setup system. Let's go ahead and open up our RStudio and take a look. Here we are, and I've opened this up in the RStudio version, which automatically opens up some extra windows, which is nice. Let's go ahead and take a look at that. We have our console on the left. This is your main workspace. So if I go in here and I do click the mouse, and I do a 4 plus 4, it'll come up and say the answer is 8. And you have some environmental information, and over on the right you have plots. Usually when you're working in here, let's do a script. We'll go up here to the plus sign in the upper left hand corner and just add some script in here. In this case it showed up on the top, but you can move these windows around. And let's say I do y equals 3 plus 4, x equals y plus 2, and then I'm going to do just x. And let's do a plot. We'll throw a plot in there. C is a notation that these are going to be Cartesian points. So we got 1, 2, 3. That'd be like your x. And then y, 3, 4, 5 for just a standard call scatter plot. You don't have to memorize this. We'll go into some of this later on. And then I can take all of this. If I go under code, since I'm working in the code console, and I go down to run, region, and just run all, it takes this code and just runs it through my console. And you can see down here, it's executed y equals 3 plus 4, x equals x plus 2, and if you add 3 plus 4 plus 2, you get 9. That's what the x does. And then I did a plot. I threw the plot in there, where I'm plotting 1, 2, 3, 3, 4, 5. And if you use just a straight plot, it's a scatter plot, and you can see that this appears on the bottom right, where you have your plots coming in. So it's a very quick way to show data. And this is one of the wonderful things about R, is it's very easy and quick to go through and do different functions on the data and analyze it. So it's a very popular package. Before you start programming in R, you should install packages and its dependencies. Packages provide pre-assembled collections of functions and objects. Each package is hosted on the CRAN repository. Not all packages are loaded by default, but they can be installed on demand. Remember earlier we were talking about all the different packages available? You don't want to install everything from R. It would just be a huge waste of space. You want to just install those packages you need. So to install packages in RStudio, you go under Tools and Install Packages. When you click on the Install Packages, you'll get a dialog box. You'll see where it has the repository CRAN, because there's other repositories, and you can even download and install your own packages you can build. And then you'll pick out the packages you want and separate multiple with spaces or commas, so you can install numerous packages at the same time. In this case, we're installing the forecast package, and you can see down here I just type in forecast, install all the dependencies, so it uses other packages to build on, it has those, and then just click on install and it's done. Before we cover the basic linear regression model, let's just take a quick look at some of the different parts of R, or parts of programming you'll need, or scripting. First, you need to know there are various data structures in R. We have vectors, we have matrices, we have arrays, data frames, and lists. Vectors is the most basic data structure. If you remember, vectors are a location and a direction is how they're generally defined. Although vectors, when you're talking about scripting, can contain numerous different values. You could have vectors with 4, 5, 6, 7, 8 different values in it. For example, a picture on the computer might have the location of the pixel and the number for the red hue and the green hue and the blue hue. So now you have something with 5 different numbers in it consisting of that vector. Matrices allow you to move stuff around. So you might have a 2x3 matrix that you switch to a 3x2. We looked at an XY plot earlier. It might be that you have everything you have 10 different numbers and each one has 2 values, XY, and you need to switch that matrix. So then you have 2 arrays of 5 numbers. Arrays are just that, a collection, and you can have arrays of arrays of arrays. Data frames have labels on them, which makes them easier to use. So usually we use a lot of data frames when we're working with data because they're just easy. You can have a column and you can have a row. So think of rows and columns when you see the term data frames. And then lists are usually homogeneous groups. So in R, you're usually looking at similar data that's connected in the list. So the first thing we do is, before we're even importing the data, you should have the data ready. So we need to look at the data and see what's going on. You can import data from various sources, including Excel, Minitab, CSV, table, text files. CSV is usually a text file, comma separated variables, tab separated variables. There's all kinds of different options here. And importing the table is very simple. We have table, read table, file equals data table, header equals true. And let's just take a closer look at what we're talking about here. Scratch the closer look. I didn't realize it was just for example. So importing a table file is pretty simple. You read.table, file equals data.table, so whatever the name of the file is, comma, header equals true, so if there's a header to it. In this quick flash, they have name, age, gender. We'll actually do this in R with another data set in just a minute. But you can see it's very easy to read. A lot of people use R even in other programming languages so they can quickly look at the data before they even start analyzing it. CSV file, same thing, read.csv. File equals data CSV, header equals true, separation equals space. So in this case, even though CSV stands for comma separated variable, this one is separated by spaces, and they have the header, name, age, gender. So it's the same file saved as a CSV file. And there's also Excel. Excel has its own issues as far as making sure you know what the tables are and the headers are, but you can see that each one of these is easy to import. So, and just like it's easy to import the data, you can also export tables in R. So you can see here, write.table, myfile, see myfile.text, comma, separated. And the scoop T just means it's tab separated. So if you're using tabbed files on there. Example, Excel. So you can write a .xls to my file. In this case, they did a text. Separation equals scoop T, so it's a tab separated for Excel file. CSV, same thing. Very easy to write a CSV file to your computer once you've changed the data or altered it depending on what you're doing with it. And once we have our data imported, and we can save it afterwards and export it, graphing. Visualization in R is very powerful and it's quick. Love doing this before even exploring the data. Sometimes you just want to graph it to see what it is there so you have an idea of what you're looking for. So graphics in R cover a huge amount of different things. R includes powerful package of graphics that help in data visualization. These graphics can be viewed on screen, saved in various formats including PDF, PNG, JPEG, WMF, and PS, can be customized according to very graphic needs. You can copy and paste in Word or PowerPoint files. R supports various types of graphics including bar chart, pie chart, histogram, kernel density plots, line chart, box plot, heat map, word cloud. There's even some more obscure ones, but these are the main ones that most people use. I know I use a lot of heat maps, but word clouds are a lot of fun if you're doing websites and data and word analysis. And then histogram is very popular. All of these are very widely used. Let's look at the box plots, also known as whisker diagrams. Box plots display the distribution of data based on minimum, first quartile, medium, third quartile, and maximum. So right off the bat, we can use a box plot to explore our data with very little work. To create a box plot, we simply give a box plot and the data. Very straightforward. So we might have passenger numbers in the thousands. I guess this is exploring data dealing with airplanes. And you can see here they just have a simple plot. If you break it down, you have your, if we go back one, you'll notice we have like a minimum, a maximum, our medium, first quartile and third quartile. Let's just break that apart. You can see the line on the bottom is your minimum, your line on the top is the maximum. You have your medium and your first quartile right there. First quartile and third quartile. And the way a lot of times you read this is things that are above the box are outliers and things below the box are outliers, and what's in the middle of the box is usually the data you're looking at. Linear regression. Now we have a few tools of what R can do. Let's look at the theory behind linear regression and how that applies to what we're going to use in R. Let's understand more concepts by solving a few algorithms. Firstly, linear regression, which can be applied in two ways. One, we can estimate the relationship between two variables. Does body weight influence the blood cholesterol level? So we just want to know if it's even a valid connection or not. Will size of the house affect the house price? So we can estimate the relationship between two variables also. And then we can predict the value of one variable dependent on the basis of other independent variables. So once we know they're connected, we want to use that to go ahead and predict it. In the cases above, maybe the body weight versus cholesterol. So the higher the body weight is, probably the higher cholesterol. So first we explore, is there a connection? And if there is, can we actually apply that to a linear regression model where we can see how they're connected? Same thing with house pricing. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. Y being the dependent variable, x being the independent variable, m being the slope of the line, which you can see over here on our graph, equals y2 minus y1 over x2 minus x1, and c being the intercept, or the coefficient of the line. Now, you don't have to memorize all the formulas we're going to go in here, because most of R does this for you. But you do need to know what's going on in the back end so that you can understand if it's working or it's not working, where the problem lies. Types of linear regression. There's simple linear regression. Considers one quantitative and independent variable, x, to predict the other quantitative but dependent variable, y. And that's the formula we just saw, y equals m times x plus c. And then we have multiple linear regression. Considers more than one quantitative and independent variable. So instead of having just x, you have x of 1, x of 2, x of 3 to predict the other quantitative but dependent variable y. So instead of looking at just body mass, we might also look at height. So you have body mass and height would be two independent variables. Housing prices might have to do with the distance to a certain area. So location might be one of the variables along with the size of the house. Let's consider a sample data set with 5 rows and find out how to draw the regression line. So in here you can see we have independent variable and our dependent variable, where we've taken some random data. In this case we have 1, 2, 3, 4, 5 for x, and we have 2, 4, 6, 5, 8 for y. And the first thing we do is we might plot it. If you look at the plot, you can see that it has a nice line through it. And just eyeballing it, you can guess that there's probably a linear regression model that will fit this data. Then we go ahead and calculate the mean. We count the mean of x and the mean of y. And you can see that we plotted that on there, 3, 5 for this particular data set. And so drawing the equation of the regression line, we'll go ahead and take a summation of x, a summation of y, take a summation of x squared and a summation of y squared, and then x times y. This is why it's so nice for the computer to do this work for you, because I don't know about you, I hate sitting there with a calculator, and if you have just 5 variables, that would be very long, not a big deal, but if you're doing hundreds of variables, definitely much easier to let the computer do it all. So the intuition behind the regression line breaks down to the linear equation, which is represented as y equals m times x plus c. In this case, m equals this very lengthy formula where you have your summations. So all the values that we've already computed fit right into this equation. And so you have n being the number of variables. That's what the n stands for. Your x times y, we computed the sum of x, sum of y over the number of variables times the sum of x squared minus the sum of x squared. And then, of course, we have, you put the numbers in and you get a value of 1.3, and you find out that your c is equal to 1.1. Once we have this formula, we can easily compute the y values. Y equals m times x plus c equals 1.3 times 3 plus 1.1 equals 5. And this would be the example of x equals 3. You could also put in x equals 6, an unknown value. Let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 1.3 and c equals 1.1. So here's our regression line, and then you can see if we put in all the numbers 1, 2, 3, 4, 5, we don't get the exact prediction because it's a line through the data. You'll see that it's ever so slightly off, 2.4, 3.7, 5, 6.3, 7.6. But it is a good estimate of what the data is going to generate. Let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 1.3 and c equals 1.1. The best fit line should have the least sum of squares of these errors, also known as e square. The predicted y value, residuals of errors, the actual y values. So one of the things we're looking at when we put this information together is we want these distances to be minimized, so it has the smallest amount of error possible. Let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 1.3 and c equals 1.1. And here you can see we've done the same kind of chart. We have our y predicted, and then we have the actual y minus the y predicted, because we are looking for the error squared or the e squared values. The sum of the squared errors for this regression line is 3.9. We check this error for each line and conclude the best fit line having the least e square values. Minimizing the distance, there are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. And no matter how you compute the errors, you can see here this is what it's basically going through. It's taking the line and slowly adjusts it until it has the minimal error available, the minimal distance between the line and the different data points. Use case. We'll start with linear regression, and then we'll jump in and also do a decision tree, so you can see how they are same and how they differ in the way they function and what they're used for. And while we're going through the use case, you can start linking the theory behind it connected to the actual use. And as you connect those dots, you can see that by making changes in the model based on the theory, you can also fine-tune it. We'll talk about that briefly as we go through this. For this analysis, we'll use the default CARS dataset to find the correlation between variables. CARS is a standard built-in dataset that makes it convenient to show linear regression in a simple and easy to understand fashion. And we'll start with head CARS and string CARS. Now I've gone ahead and removed the script on here to make this easier to see, and we don't have to do any kind of importing of data because it's already in there. I'm just going to type in head and CARS and hit enter. And what you're going to notice is it's going to display the first 6 rows, 1, 2, 3, 4, 5, 6, and you'll see speed and distance. Now this is a little bit like a spreadsheet, so if you're using an Excel spreadsheet it should look the same, and this is a standard data frame kind of setup. In this case, whenever you say head, it usually lists the first number of rows, depending on your package. In R, it starts with 1, and then it does the first 6 rows. String, when we do string of CARS, it's going to break it down and show us that it's a data frame. It has 50 objects, that's with the 50 OBS, of 2 variables. And then we have speed. The first variable is going to be a number, is what NUM stands for, 4477, it just starts listing the data there. And distance. Now I'm assuming the speed is the speed of the engine. Otherwise, if it's the speed of the car, then the distance should always be the same. And that would just be kind of silly. But this is the speed of the engine, and based on the speed of the engine, can we correlate that to the distance? Let us visualize the data using scatterplot to understand the relationship between predictor and response. And I want you to notice that in this slide, a line has been drawn through the data. Now when we first start with data, you don't have that line. So as we plot it, I want you to kind of visualize that line there and just kind of say, hey, does this stuff kind of scatter around a line or not? Before we actually create the model. And we simply do plot, and I'm going to do a shorthand here, CARS, and I hit enter, and it comes over here to the right and plots our data for us. Now because there's only two variables, I don't have to do anything special. I'm going to expand this over environment so we can see it. And you can see you can just visualize a line right through the data, and it's all clumped along that line, which makes it really nice for doing a linear regression model. Now I did something a little tricky here because I'm very lazy. I typed in plot cars. A lot of times you don't want to do that because you don't want to plot all the data. We could do plot, in this case cars, $, speed, the first variable, cars, $, distance. When I do that, I get the same plot. All I'm doing is telling it to use just these two columns of data. And although the first one is quick and easy, if you only have two columns of data, the second one is what you really want to do when you're plotting data like this. You want to control which columns you're using. And then we want to do a correlation. Correlation analysis studies the strength of a relationship between two continuous variables. It involves computing the correlation coefficient between the two variables. If one variable consistently increases with increasing value of the other, then they have a strong positive correlation, a value close to 1. And again, I can just type in correlation cars, the short form, and we can see we have a nice correlation going on there between the two. What we really want to do though is we want to correlate cars, and then we're going to do the speed, comma, cars, and the distance. And so when you look at this, I actually hit the enter key in the middle of that, which is fine. You can, in R, do it line by line. So if you're trying to do a bunch of different columns, you might want to do that to make it easier to read. And you can see here I get the point 806894. The closer this is to 1, the more these correlate. So it's saying there's a pretty good correlation, positive correlation between the two variables. And if you look at it when I did just cars, which did the correlation over all the variables, you'll see that speed correlates with speed 100% because they're the same. That's just the nature of that. But when you look at speed versus distance, we get the point 806849. And if you do distance to distance, you get also 1 since they're identical variables. So now it's time to build our linear regression model on the entire data set to build the coefficients. Let's just take a look and see what that looks like. Back in our console, I'm going to type in linear mod. And in R, we want to do the arrow, kind of like an arrow in a line, or in this case, the less than minus sign. That's the same as assigning whatever we're going to put after it to this variable. So we're creating the linear variable. LM stands for linear module, and we're going to look at speed and distance. So we put the little squiggly bracket between them. This lets R know we're going to deal with these two columns, comma, data equals cars. And when I hit enter on here, we've generated our linear mod. Now we want to go ahead and summarize it. And we simply do a summary and then brackets, linear mod, and it generates all kinds of information on our model so we can explore just how well this model is fitting the data we have right now. Now if you've done linear regression in other packages and scripts, you're going to see that this is so easy to explore data in R. So even somebody who's working in, say, Python or Spark, Hadoop, coming back to the R console to do some basic exploration of the data is very beneficial. And if you use just R, R goes into all kinds of different packages, and you can even do cluster computations through H2OR. There's a lot of cool things. This is what makes R so wonderful, is how easily we can summarize something like a linear model. And to explore this data, let's go back to the slide. And we'll see here where it says the residuals, the first 1Q stands for first quadrant, median, third quadrant, max, coefficients. And we first want to do is look at the estimate standard deviation on here. And you'll see the intercept is at minus 17.5791 and speed 3.9324. So we can compute the distance equals to the intercept plus the beta times the speed, which just means that we can assign a distance equal to minus 17.579 plus the 3.932 times the speed. The value of p should be less than 0.05 for the model to be statistically significant. And this is one of the things I love about R. You can see right down here, we punched in the numbers and it even tells you the significant codes. So if you're trying to guess or remember, it tells you right away, hey, this 1.49 to the minus 12th is way below 0.001 on there. And it even puts 3 stars next to it, so you can see that that is a very high correlation. And you can see the 0.0123 gets 1 star because it is greater than the 0.05, or it's less than the 0.05. So this shows that there's a very high correlation. Statistically, it's very significant. So now we're going to go ahead and create a training and a test data set. And the first thing we want to do is we want to set the seed so the sample can be recreated for future use. Remember, in all these different regression models, they usually have some randomization going on in the back to kind of fit it and guess where it's going to go. And if you want everything to match, you want to start with the same seed in that randomizer. That way it recreates it identical every time you run it on a different computer. And just like working with data in any package, we're going to create indices for the training data, and we're going to model the training data, and then we're also going to do the test data and build our model on the training data. And let's walk through that and see what that looks like in R. And I actually mistyped that one. Let's type in set.seed to set our seed for the 100. Let's go training row index, and that's our name we're making up for our variable. And we're going to set that to sample. Now, sample is a command in R, so we're going to take a random sample of some of the data. And then we're going to do 1 colon in rows cars. So this is the number of rows in cars, and we're going to start with 1 and sample them. So row 1 of the data. We're skipping any of the titles on the top. And then in the sample, it has 2 variables that go in. The first one is the in rows of cars, and then we want to do 0.8 times in rows of cars. And this basically says that we're going to take 80% of all the rows in the car sample. And we'll hit enter to go ahead and run that. And we see here that I had an error, and that is because it's in row. Actually put an S on there. That's something I do a lot on. We'll just fix that real quick. Brings up a point that if you use your up down arrow, you can quickly paste through the last things you typed in, and then you can reuse them. So there we go. Now I have my training row index, which is basically a list of all the rows we're going to use. And now that we have a training row index, we'll go ahead and create our training data variable. And we'll assign that cars, and we'll put that as a training row index. And this is supposed to be brackets because we're dealing with a array type format. We want to do the training row index, comma, because we just need the index of the row, and as far as the columns, we want all the columns. So here we have our training data. And now we set up a training data, we also need our test data. And with our test data, we'll assign that also to cars. And because we use the training row index and we use the sample to create it, we can simply do a minus sign training index, comma. So it's identical to the training data, but the test data is going to be the rows that were not included in the random sample of 80%. So it's going to be 20% of the data. And of course, it's very easy to do mistakes on here. So we'll come back into this, bring back up the error, and then we have training index, training row index. There we go. Very easy to correct errors in R. So now we have our training data and our test data. So we have 80% in training data and 20% in test data. And let's go ahead and create our model. We'll call it LM mod. And this is identical to what we did earlier. Here's our linear model. We're going to have our 2 different columns. If you remember above, we had to tell it which columns we wanted. And we're going to do distance and speed. And then the data, we're going to set equal to training data. So as opposed to doing all of cars, we want to use just the training data on here. And now that we've created a model off of the training data, we need to go ahead and run our prediction off of our test data. We want to see how the test data, which has nothing to do with the model so far, how well it fits. And we'll go ahead and call it distance predict. There's our assignment, so we're going to assign the value to it. And with R, we type in predict, and then we called our model. We go ahead and pull up our model, LM mod. And so we're going to use that model, and then we want to put in the test data. Here's our test data. And so now we're creating the distance predict variable, and we're going to put all the information as far as predicting on our test data. And we'll run that. Just hit the enter key. And then, if you remember from before, we want to review the model diagnostic measures. And so we're going to go in here and do a summary. And you'll see in here we have a couple different things going on. But let's go ahead and take a summary of this and just walk through what this means. So summary, and then we called it LM mod, and we hit enter, and it pulls it up. And we have a nice summary of our LM mod. And the first thing we're going to note is that the data that's right now in our LM mod that we're summarizing is our training data. And let's go back to the slide and highlight this. So the data equals the training data. That's where the LM mod comes in. Residuals, we have our minimum, our first quarter, medium, third quarter, and the max, or quadrant, not quarter. You'd think I was doing a business analysis as opposed end of the year taxes in first quarter versus quadrant. We look at our coefficient. We can see where our intercept is and our speed is. And we note over here our significance codes, so they all match up. So a simple correlation between the actuals and the predicted values can be used as a form of accuracy measurement. So we take a look at the model we created, and now we need to take our predictions and just see how accurate it is on the data that we didn't use to program the linear model. So let's create a variable called actuals underscore predicts and assign it data frame. This is how we create a data frame, is we just assign data.frame, and we'll do a cbind. And in our cbind, we're going to take our data and we're going to create a column called actuals. So this is our choice, the name actuals. This is going to equal test data, and then we're going to use a $sign and distance. And we're running out of a little room there, so let me pull this over so we can see it better. There we go, distance. And then we also want to take and compare that to what we predicted for our other data. And we'll call this column predicteds, and that's going to equal our distance predict. And remember, distance predict is set to the predicted values of our test data. So what this is we're saying, hey, here's our test data, the actual data, and the distance, and then we have what we predicted that distance to be. And we'll go ahead and assign that. And we can do a quick head, actuals predicts, there we go. And remember, head shows us it's a data frame, so it's going to show us the labels and the first set of data. In this case, you'll notice that the rows have a different count. They're not 1, 2, 3, 4, 5, 6. Well, we randomly picked 20% of the data. So this is the first 6 rows of that random selection, which comes out as 1, 4, 8, 20, 26, 31. And we have the actuals, so the actual value is 2, and the predicted value on this first one is -5, so they're way off. 22, 7, 26, 20, 26, 37, 54 to 42, 50 to 50. So one of these is actually pretty right on, where a lot of them are really off at the beginning. Let's just see what that looks like though, because just eyeballing the first 6 rows does not tell us what's really going on. So let's create another variable, correlation accuracy, and we're going to assign this correlation, COR. Remember, we do a COR, and we have our actual predictions. So let's just see how our actual values versus the prediction correlate with each other. And we assign that one actuals underscore predicts. There we go. Let it auto finish for me. And we can just go ahead and type in correlation accuracy and see what that looks like. So we have an actuals 1, a predicts 0.8, and you can see how they kind of correlate. We have the 0.82, and if you remember from before, we're looking for either 0.001, 0.01, 0.05, 0.1. That is the p-value, which we're not looking at here. This is not based on the p-value. This is based on what we looked at earlier with correlation, that the closer to 1, the closer the values are. And so 0.82 gets upwards of 1, so you see that there's a normal, pretty much a correlation in here. But we want to dig a little deeper, because this doesn't really tell us how accurate it is. For that, we're going to use another tool. For that, we're going to calculate the min-max accuracy and MAPE. And the min-max accuracy equals the mean value of the minimal actuals and predicts over the max value of the actuals and predicts. And then the mean absolute percentage error, or MAPE as it's called, equals the mean of the absolutes predicteds minus actuals over the actuals. That's a lot to follow as far as remembering all these different math and theory behind it. Cool thing though is it's all done pretty much for you. So you can compute all the error matrices in one go using the regress eval function in DMWR package. Since this is the first time I've used this install, I'm going to have to install the DMWR package. So we can actually install it 2 different ways. If you remember, we talked about installing package earlier. We can go under Tools and Install Packages, and I certainly could type in DMWR. It even comes up and lets me know that's one of the main packages up there. Well, that's a tool of the RStudio setup. You can also install this using the console. We simply type in install. You can even see here it comes up install packages and then DMWR. And when I hit enter, it should do the same thing as the other one does. It goes through and installs the DMWR package. And it takes just a moment to zip through all the different package setup. And then the format for DMWR is DMWR. We're going to go : We are specifically looking at the regression.eval. And then we're going to do actuals underscore predicts. And we'll go ahead and put in the individual columns on this one. So we have actuals. I love the auto typing. And then again, actuals predicts. And this time we want to do it against the predicteds. We'll go ahead and hit enter on here. And you'll see in here it comes up with our MAE, MSE, RMSE, and the MAPE values. So we looked at the linear regression model. Let's go ahead and take a look at the decision trees. So let's go ahead and talk about another algorithm, decision tree. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. It is a tree which helps us by assisting us in decision making. Let's look at the basic terminologies to understand decision trees. We have our root node, we have a splitting, we have decision node, and then those split into terminal node, decision node, terminal node, terminal node. And each decision node continues to split until it ends in a terminal node. Note, A is the parent node of B and C. Also note we call the terminal nodes leaf nodes. You can also see that we have a branch or a subtree. So when you have a split, everything under that split under one side is called a subtree. You cannot build your decision tree without knowing entropy and information gain. Entropy. Entropy is the measure of randomness of impurity in the data set. So we have here a bunch of fruit, and you can see we have, it looks like apples, oranges, and bananas. It's very chaotic, so it's a very random data set. It has a very high entropy. And if we take out one group, let's say we take out the apples, it's a little less random. Now we only have bananas and oranges. So it's a less random data set, and we have lower amount of entropy. Entropy is a measure of randomness or impurity in the data set, so when you have a homogeneous data set, we will have entropy equals 0. And here you can see it's all oranges. An equal divided data set will have an entropy equal to 1. So here we have half, or what is it? Looks like a couple bananas, a couple oranges, and a couple apples. So everything is equal. So we have an entropy of 1 on there since there's 2 of everything. Information gain. It is a measure of decrease in entropy after the data set is split, also known as entropy reduction. So we look over here and we have an entropy equals E1, and the information gain as we split the bananas out, the size becomes smaller, and you'll see that E1 is going to be greater than E2, or we measure E2 of the apples and oranges in this case. If you love your fruit, it's probably getting you hungry right about now. And then the information gain from our level 2 equals E2 minus E1, where E2 is greater than E3. And as we come down here, we'll see that the E3 is now the third level where we split the oranges and apples out. And each time that entropy becomes less and less and less, until in this case we have an entropy of 0, since they're all homogeneous in their order. All oranges, all apples, all bananas. So let's take a look at the use case decision tree and actually put this into code and see what that looks like as we go from theory to script. And to predict the class of flower based on the petal length and width using R. And you'll see here we have these beautiful irises, probably the most popular data set for beginning data analysis and statistics. We have the Setosa, the Virginica, and the versicolor. Let's install the packages that will help us in the use case. So because we're doing decision tree, we have rpart.plot, and then we have the library rpart and the library rpart.plot. Let's go ahead and take a look at that. And if you remember, we have 2 ways of installing it. We can do the install packages. We did that earlier. Here we go, install packages, using my up arrow to get to it. Or we can go up to tools, install packages, and I can do rpart and rpart.plot, and then go ahead and hit the install. Packages that will be updated as are currently loaded. Oh, it looks like some of them are already loaded. That's fine. We'll just go ahead and update those. And once we have those updated, let's take a look and see what we have going on here. Oh, it's still loading. Let's go ahead and type in library rpart and library rpart.plot. So we want to bring it into our console that we're working in. So up and now we just download the packages, and now we want those libraries available to what we're doing. So the iris, although it's built into the R package download on the basic download, we actually have to install the data or bring the data in. So we're going to do the data iris, and then we're going to do the string iris. And let's just flip back on over to our RStudio and set up our data iris, and then we're going to do string. Before we do that, let's do head iris. There we go. And you can see the head has sepal length, sepal width, petal width, species. In this case, the top part's all Setosa, and each row gets a number. And then we did the string iris. and that comes up with information. And if we flip back to our slide, you can see here the structure of the database under string is it's a data frame. It has 150 objects, 5 variables each, so each one has 5 variables. All features are numerical except species, which is categorical as it is our target variable, which we want to predict. So we want to predict whether it's going to be a varicosa, versicolor, setosa. So you can see here we want to predict all the features are numerical except species, which is categorical. It is our target variable which we want to predict. And you can remember that's the setosa, the versicolor, the virginica, the 3 different categories we saw earlier in the beautiful pictures of the flower. And so we're going to go ahead and use the set seed to decide the starting point used in the generation of sequence of random numbers. Remember, we set the seed so that if we ever want to reproduce what we're doing, it will reproduce the same thing each time because it's using the same randomizer seed. Bring slightly different results, but depending on what you need it for. And then we're going to generate random numbers using runIf. And the question is, why do we want to create random numbers on here? It's kind of an unusual thing to do for nRows iris. And let's go back and just take a quick look here. Actually, we want to go back to our RStudio. And you're going to notice when I did the head of iris, what did I have? I had setosa, 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 setosa. So the data is organized by species, and it's already grouped them together in the data set. Well, we want to randomize that so that doesn't affect our output. And then we'll go ahead and take and create our iris ran, where we recreate the data frame based on a random order instead of setosa all being grouped together. Let's go ahead and put that into our RStudio and set.seed, and we'll match their number. It's 9850. This way we'll have identical results to what they're doing on the slides. Then we're going to set the variable g equal to runIf and base this on nRow of iris. And finally, we're going to create iris underscore ran, and we're going to assign our variable we're creating iris underscore ran, and we'll set that equal to, we're going to do that to the original database, we're going to set that equal to iris, and we need brackets because we're assigning the variables, and we want to change the order, so there's an actual command order we can do. It's going to be order G, so this means all the rows in the order that G is, so we just randomized all those rows. And then we want to keep all the columns. We'll just put a comma and we'll leave it blank for the columns. So now iris ran will have some randomized rows coming in. And if we do head, let's just do this real quick, iris ran. We can see that it's no longer setosa, setosa. We now have virginica, setosa, versicolor, setosa. And you can see the row numbers at the beginning. We have 103, 20, 63, 17. So they're randomized on there pretty well. Now that we've done a little data manipulation, we can go ahead and build our model using our part as follows. And one of the things I want you to notice here is we're going to build our model for our R part on the first 100, because our data equals iris ran 1 to 100. There's 150 objects, so we're keeping a third of them off to the side. That way we have our training set and our test set already pre-built because we randomized the rows going in from the beginning. And then once we've done that, we want to go ahead and print our model out and take a look at it. Let's go ahead and put this into our RStudio and take a look. And so we have our model, we're going to call it model, that's our variable name that we're giving it. We're going to assign that our part, and in brackets we'll start with species, and we want to correlate species to all the other columns. So how do we do that? And the shorthand is just to put a period there. And then we're going to put a comma, and then we want to set our data equal to iris ran. That's the data we put in there. And remember I said we're going to do just the first 100 rows, so we can save the last 50 for testing. So we can do that simply by doing row 1 to 100. So in R you start with 1 for your rows. And because we want all the columns, we just put a comma, and that denotes that we're going to use all the columns in here. And in the R part, there's different methodologies. We're using the method equals class. And you realize that we're doing a classification between the 3 different types of flowers, and so this is what we want to go ahead and set up our model with. And when we run that, we've now created a nice model for us. We can go ahead and just type in model, hit enter, and you'll see it'll print out a bunch of information about our model to let us know what's going on in there. And let's just break that down and see what that looks like. So we have our target, our predictors, that's species, and it's going to relate to, we used a period to denote all the columns. We're going to take the first 100 rows to train the data, and we have the defining method to be used as classification. That's what the method equals class is. And what we want to do next is we're going to do a plot and take a look and see what this actually looks like, a little visual here, which is nice. And we simply do that with our plot for the model. And let's break this down a little bit and just see what that looks like in the R setup. And we do this rpart.plot. A little bit of a mouthful there sometimes. That's part of the rpart package or module. So when you imported this in, it also included its own plotting format. And we're going to send it our variable model. And there are actually a number of types of plots listed for rpart, but we're just going to do type equals 4, fallen.leaves equals t, and extra equals 104. Let's go ahead and hit enter on there. And you'll see right over here on the right hand side, it goes into our plots. We just enlarge that. We have our versicolor, our setosa, versicolor, virginica. And let's go ahead and break that down. As you can see down here, it represents the tree as it splits. It looks at it and says, hey, if the petal length is less than 2.6, it's going to be a setosa. So 34% of them fall into that category. And if the petal length is greater than 2.6, then looks at that and says, okay, now I have 3 different variables. We're going to split it again. Petal width is less than 1.7. It's going to be a versicolor, and if it's greater than 1.7, it's a virginica. And so you can see here, it's a very simple tree it forms. It's only got a couple levels. You can see a branch off to the right. Very nice depiction of what's going on as far as the model now that it's created. But once we create the model, we need to figure out, is this model any good? So let me go back over here and let's go back to our slides. And the first thing we're going to do is we're going to take our test data. Remember, we saved 50 rows for the end to go ahead and run a predict on there. So let's go ahead and run that prediction. So we'll call it model_predict. And we're going to hit a wrong button there to predict. And what are we going to predict? We're going to predict our initial model. And we need to send the data. So data equals. And we don't actually have to put the data part in. We just put in iris_ran. And then we want to do just the last 50 rows. And we denote that by 101:150 and then comma, and we'll leave that part blank since we want all the columns to show up. And then finally, this is a classification, so we need to let it know that type equals class. There we go. And let's just see what that looks like. Model predict. And so this is what the data is put out as, is it says whatever this is, 131 is a virginica, number 10 is a setosa, line number 95 is a versicolor, and so on all the way through. What we really want to know is how good our model is. So we're going to go ahead and install a couple more packages. We're going to install the packages required to use the confusion matrix. And to do that, we're going to install caret and E1071. And then, of course, we want to set them to our project by using the library command. And so we can simply install packages, and we want caret, and we'll go ahead and just do that right there. There's caret installed. And we went ahead and did the install for packages E1071. As it goes through there, it's a really quick install compared to the caret. And then once we've installed the packages, we need to load it into our workspace. So there's our library caret. Oops, I should load it in there. There it goes. And once that's loaded, we'll go ahead and also load or set the library to the E1071 so that we have both those libraries available to us. And here we go, library, and then this one is E1071. And now these two libraries are fully available to us. And then we're going to use these tools to create the confusion matrix. And this one, confusion matrix, this is the iris ran. And then we'll go ahead and put the brackets here, and we're only going to do 101 to 150, and then we only want the first 5 columns, not the last 5 columns, the first 5 columns. So 5 in there, and we'll set that to our model predict, and then when we hit enter, it's going to head and just print out all this information. So right here, we're looking at our confusion matrix to see how everything kind of balances out. Let's go over that and see a little closer what that actually means. So the first part we see is a reference. And in here we have our prediction, because that's what we call it, the column, if you remember correctly. And we have it for setosa, versicolor, virginica, and then we have setosa, versicolor, virginica going down each side. And the way you read this is if you look at this, we predicted 16 out of 16 setosa. And then versicolor, we predicted 13 of the versicolor, and then 2 of those we predicted as virginica. So we were wrong on 2 of those. And with the virginica, we predicted 17 correct, and we had 2 wrong that were versicolor. So we look at the overall statistics on here, and we have an accuracy of 0.92 and a 95% CI. That's pretty good as we're going through here. Those are good deals on that. And there's a lot more information as you go down this. The one thing I want to remind you on this as we're looking at these predictions, and this is also true for the linear regression model we looked at earlier, when we talk about the accuracy, that is the accuracy on this data. And we say that as a programmer to make that a very clear distinction, because if you're in data analysis, you should cringe if I say, this is a 95% accurate model without that put in there, because bad data in, bad data out. We won't go into detail right now on that, but that is very important to note that whenever you quote any of the accuracies on here or you discuss any of these values that come up.
So, what does Python have for data science? Python is an interpreted, dynamically typed language with a precise and efficient syntax, and is renowned for its ease of use to analyze, visualize, and present data. Python has an extensive library with built-in modules, providing easy access to system functionalities, which not only improves accessibility, but also provides standardized solutions for everyday programming challenges. By taking away platform-specific requirements and replacing them with platform-neutral APIs, modules in Python libraries encourage users to make programs portable. Why should a data scientist use Python? Apart from being an open-source ecosystem, Python and most of its incredible libraries are platform-independent, so you can run this notebook on Windows, Linux, or OS X without a change. Python is part of the winning formula for productivity, software quality, and maintainability at many companies and institutions around the world. Python is one of the leading technologies used widely in academic circles and industries because of its flat learning curve. Still not sold on Python? Then here's some proof. Case study. ForestWatch.com, a weather report accuracy rating service, is a 100% Python solution, using it in all its components, the front end, back end, as well as the performance critical portions. Python was chosen to develop this solution as it comes with many standard libraries useful in collecting, parsing, and storing data from the web. Python is impressive as an object-oriented, rapid application development language. One of Python's key strengths lies in its ability to produce results quickly without sacrificing maintainability of the resulting code. Because of the clean design of the language, refactoring the Python code was also much easier than in other languages. Moving code around simply requires less effort. ForecastWatch.com was made possible because of the ease of programming complex tasks in Python, the rapid development that Python allows, the ease to analyze and represent data in a simple and visually appealing style. Market potential. So how does the future look for Python as the tool for data science? According to KD Nuggets, 46% of all the data science jobs list Python as the skill required, second only to SQL. According to a survey by the Association for Computing Machinery, ACM, posted on javaworld.com, Python has surpassed Java as the top language used to introduce U.S. students to programming and computer science. Projected skill gap. There is also going to be a huge demand for data scientists who know Python. McKinsey & Company, a trusted advisor and counselor for many of the world's most influential businesses and institutions, projects that by 2018, the demand for data scientists who know Python may surpass supply by perhaps 60%, making Python a must-know skill for data scientists. Forbes.com mentions that the demand for Python programmers in big data-related positions increased by 96.9% in 12 months.
Now let's talk about Python. For doing data science, we need some kind of a programming language or a tool and so on. So this session will be about Python. There are other tools like, for example, R, and we will probably do a separate video on that. But this session is on Python, and you must have already heard Python is really becoming very popular. Everybody is talking about Python, not only data science, in IoT and AI and many other places. So it's getting very popular. So if you are not yet familiar with Python, this may be a good time to get started with it. So why do we want to use Python? So basically, Python is used as a programming language because it is for data science, because it has some rich tools from a mathematics and from a statistical perspective. It has some rich tools. So that is one of the reasons why we use Python. And if you see some of the trends, if you're probably tracking some of the trends, you will see that over the last few years, Python has become programming language of choice, and especially for data science. SAS was earlier one of the most popular tools, but now increasingly Python is being used for doing data science, and of course as well as R. One of the reasons, of course, is that Python and R are open source compared to SAS, which is a commercial product. So that could definitely be one explanation. But beyond that, I think it is the ease of understanding this language, the ease of using this language, which is also making it very popular, in addition to the availability of fantastic libraries for performing data science. What are the other factors? There are speed, then there are availability of number of packages, and then of course the design goal. Alright, so what are each of these? Design goal. Primarily, the syntax rules in Python are relatively intuitive and easy to understand. Thereby, it helps in building applications with concise and readable code base. So with a few lines of code, you can really achieve a lot of stuff. And then there are a lot of packages that are available that have been developed by other people, which can be reused. So we don't have to reinvent the wheel. And last but not least, the speed. So Python is a relatively faster language. Of course, it is not as fast as, let's say, C or C++, but then relatively it is still faster. So these are the three factors which make Python the programming language of choice. So if you want to get started with Python, the first thing obviously is to install Python. So there is some documentation, there are some steps that you need to follow. So we will try to briefly touch upon that. Otherwise, of course, there is a lot of material available on how to install Python and so on. You can always look around, but this is one of the, again, there are different ways in which you can also install Python. So we will use the Anaconda path. There is a packaging tool called Anaconda. So we will use that path. You can also directly install Python, but in our session we will use the Anaconda route. So the first thing you need to do is download Anaconda, and this is the path for that. And once you click on this, you will come to a page somewhat like this, and download, you can do the corresponding download based on whether you have a Windows or Ubuntu. There is also a download possible for, or package available for Ubuntu if you are doing something on Ubuntu. So based on which operating system, in fact this page will automatically detect which operating system you are having, and it will actually suggest. So for example, you see here, if you're running Mac OS, then it will automatically detect that you have Macs, and the corresponding installers will be displayed here. Similarly, if you're on some flavor of Linux like Ubuntu or any other, then you will get the corresponding download links here. And then beyond that, you can also select which version of Python you want to install. Of course, the latest version is in the 3.x range at the time of recording. This 3.6 is one of the latest versions, but some of you may want to do or start with the earlier version, which is Python 2.7, 2.x, and you can download that as well. If you don't have anything installed, then my suggestion is start with Python 3.6. Alright, so once you do that, you will be able to install Python and you will be able to run Jupyter Notebook. Okay, so now that you know how to install Python, and if you have installed Python, let's take a look at what are the various libraries that are available. So Python is a very easy language to learn, and there are some basic stuff that you can do. For example, adding or printing a hello world statement and so on without importing any specific libraries. But if you want to perform data analysis, you need to include or import some specific libraries. So we are going to talk about those as we move forward. So pandas, for example, is used for structured data operations. So if you, let's say, are performing something on a CSV file, you import a CSV file, create a data frame, and then you can do a lot of stuffs like data munging and data preparation before you do any other stuff, like for example machine learning or so on. So that's pandas. SciPy, as the name suggests, it provides more scientific capabilities. Like for example, it has linear linear algebra, it has Fourier transform, and so on and so forth. Then you have NumPy, which is a very powerful library for performing n-dimensional or creating n-dimensional arrays, and it also has some of the stuff that is there in SciPy, like for example linear algebra and Fourier transform and so on and so forth. Then you have Matplotlib, which is primarily for visualization purpose. It has again very powerful features for visualizing your data, for doing the initial what is known as exploratory data analysis, for doing univariate analysis, bivariate analysis. So this is extremely useful for visualizing the data. And then Scikit-learn is used for performing all the machine learning activities. If you want to do anything like linear regression, classification, or any of this stuff, then the Scikit-learn library will be extremely helpful. In addition to that, there are a few other libraries, for example, networks and iGraph. Then of course a very important one is TensorFlow. So if you are interested in doing some deep learning or AI related stuff, then it would be a good idea to learn about TensorFlow, and TensorFlow is one of the libraries. There is a separate video on TensorFlow, you can look for that, and this is one of the libraries created by Google, open source library. So once you're familiar with machine learning, data analysis, machine learning, then that may be the next step to go to deep learning and AI. So that's where TensorFlow will be used. Then you have Beautiful Soup, which is primarily used for web scraping, and then you take that data and then analyze and so on. Then OS library is a very common library. As the name suggests, it is for operating system. So if you want to do something on creating directories or folders and things like that, that's when you would use OS. Alright, so moving on, let's talk in a little bit more detail about each of these libraries. So SciPy, as the name suggests, is a scientific library, and it very specifically, it has some special functions for integration and for ordinary differential equations. So as you can see, these are mathematical operations or mathematical functions. So these are readily available in this library, and it has linear algebra modules, and it is built on top of NumPy. So we will see what is there in NumPy. So this is again, as the name suggests, the num comes from numbers. So it is a mathematical library, and one of its key features is availability of an n-dimensional array object. That is a very powerful object, and we will see how to use this. And then of course you can create other let's say objects and so on. And it has tools for integrating with C, C++, and also Fortran code. And then it of course also has linear algebra and Fourier transformation and so on, all these scientific capabilities. Okay, what else? Pandas is another very powerful library, primarily for data manipulation. So if you're importing any files, you will want to create it like a table. So you will create what is known as data frames. These are very powerful data structures that are used in Python programming. So Pandas library provides this capability. And once you import the data into data frame, you can pretty much do whatever you're doing like in a regular database. So people who are coming from a database background or SQL background would really like this, because it is they will feel very much at home, because it feels like you're viewing a table or using a table, and you can do a lot of stuff using the Pandas library. Now there are two important terms or components in Pandas, series and the data frame. I was just talking about the data frame. So let's take a look at what are series and what is a data frame. So within Pandas we have series and data frame. So series is primarily, some of you may also be knowing this as let's say an array. So it's a one-dimensional structure, data structure if you will. So in some other languages we may call it as an array, or maybe some others probably an equivalent of a list. In R perhaps, I'm not very sure on that aspect, but yes. So this is like a one-dimensional storage of information. So that is what is series. Whereas data frame is like a table. So you have a two-dimensional structure, you have rows and you have columns, and this is very, people, as I said, who are familiar with SQL and databases will be able to relate to this very quickly. So you have like a table, you have rows and columns, and then you can manipulate the data. So if you want to create a series, this is how you would create a code snippet. And as you can see, the programming in Python is very simple. There are no major overheads. You just need to import some libraries which are essential, and then start creating objects. So you don't have to do additional declaration of variables and things like that. So that is, I think, one key difference between Python and other programming languages. And what does this series contain? it has to contain these numbers 6346, and X is my object consisting of the series. So if you just say X, it will display the contents of X, and you will see here that it creates a default index. Then you have data frame. So if you want to create a data frame, as you can see, the series is like a one-dimensional structure. There is just like a row, one row of items, whereas a data frame looks somewhat like this. It is a two-dimensional structure. So you have columns in one dimension, and then you have rows in the other dimension. How do you create a data frame? You need to rather import pandas, and then you import. In this case, we are basically creating our own data, so that's the reason we are importing NumPy, which is one of the libraries we just referred to a little bit before. So we are using one of the functionalities within NumPy to create some random numbers. Otherwise, this is not really mandatory. You probably will be importing the data from outside, maybe some CSV file, and import into the data frame. So that's what we are doing here. So in this case, we are creating our own test data. That's the reason we are importing NumPy as NP, and then I create a data frame saying pd.dataframe. So this is the keyword here. Similarly here in this case, while creating series, we said pd.series, and then you pass the values. Similarly here, you're saying pd.dataframe. Now in order to create the data frame, it needs the values in each of these cells. What are the values in the rows and what are the values in the columns? So that in our example we are providing using this random number generator. So np.random is like a class or a method that is available in NumPy, and then you are saying, okay, generate some random numbers in the form of a 4x3 matrix or 4x3 data frame. The 4 here indicates the number of rows, and the 3 here indicates the number of columns. So these are the columns, 0, 1, 2 are the columns, and these are the rows. Here 0, this is 1, this is 2, this is 3. Okay, and once again it will, when you display df, it will give us a default index. There are ways to omit that, but at this point we will just keep it simple. So it will display the default index and then the actual values in each of these rows and columns. So this is the way you create a data frame. So now that we have learned some of the basics of pandas, let's take a quick look at how we use this in real life. So let's assume we have a situation where we have some customer data and we want to kind of predict whether a customer's loan will be approved or not. So we have some historical data about the loans and about the customers, and using that we will try to come up with a way to maybe predict whether loan will be approved or not. So let's see how we can do that. So this is a part of exploratory analysis. So we will first start with exploratory analysis. We will try to see how the data is looking. So what kind of data? So we will, of course, I'll take you into the Jupyter notebook and give you a quick live demo. But before that, let's quickly walk through some of the pieces of this program in slides, and then I will take you actually into the actual code and do a demo of that. So the Python program structure looks somewhat like this. The first step is to import all the required libraries. Now, of course, it is not necessary that you have to import all your libraries right at the top of the code, but it is a good practice. So if you know you are going to need a certain set of libraries, it may be a good idea to put, from a readability perspective, it's a good practice to put all the libraries that you're importing at the beginning of your code. However, it is not mandatory. So in the middle of the code somewhere, if you feel that you need a particular library, you can import that library and then start using it in the middle of the code. So that's also perfectly fine. It will not give any errors or anything. However, as I said, it's not such a good practice. So we will import all the required libraries. In this case, we are importing pandas, NumPy, and matplotlib. And in addition, if we include this piece of code, %matplotlib inline, what will happen is all the graphs that we are going to create, the visualizations that we are going to create, will be displayed within the notebook. So if you want to have that kind of a provision, you need to have this line. So it's always a good idea when you're starting off. I think it's a good idea to just include this line so that your graphs are shown in line. Okay, so these are the 4. We will start with these 4 lines of code. Then the next step is to import your data. So in our case, there is a training data for loans by the name loan p_train.csv, and we are reading this data. So in this case, you see here, unlike the previous example where we created a data frame with some data that we created ourselves, here we are actually creating a data frame using some external data, and the method is very straightforward. So you use the read_csv method, and it is a very intuitive function name, and you say pd.read_csv and give the path of the file, CSV file. That's about it, and then that is read into the data frame df. This can be any name. We are calling it df. You can call xyz, anything. There's a name, just the name of the object. So head is one of the methods within the data frame, and it will give us the first 5. So this is just to take a quick look. Now you have imported the data. You want to initially have a quick look how your data is looking. What are the values in some of the columns and so on and so forth, right? So typically you would do a head, df.head, to get the sample of, let's say, the first few lines of your data. So that's what has happened here. So it displays the first few lines, and then you can see what are the columns within that, and what are the values in each of these cells, and so on and so forth. You can also, typically you would like to see if there are any null values, or are there any, is the data for whatever reason is invalid or looking dirty for whatever reason, some unnecessary character. So this will give a quick view of that. So in this case, pretty much everything looks okay. Then the next step is to understand the data a little bit overall for each of the columns. What is the information? So the describe function will basically give us a summary of the data. What else can we do? Pandas also allows us to visualize the data, and this is more like a part of what we call it as univariate analysis. That means each and every column you can take and do some plots and visualization to understand data in each of the columns. So for example, here the loan amount column we can take, and then the hist method will create a histogram. So you take all the values from one column, which is loan amount, and you create a histogram to see how the data is distributed, right? So that's what is happening here. And as you can see, there are some extreme values. So this is again to identify, do we have to do some data preparation? Because if the data is in a completely haphazard way, the analysis may be difficult. So these are the initial or exploratory data analysis is primarily done to understand that and see if we need to do some data preparation before we get into the other steps like machine learning and statistical modeling and so on. So in this case, we will see that here by plotting this histogram, we see that there are some extreme values. So there are some values, a lot of it is around 100 range, but there is also something, one or two observations in the 700 range. So it's pretty scattered in that sense, or they're not really scattered, distributedly scattered, but it is randomly scattered. So the range is really huge. So what can we do about this? So there are some steps that we need to do, normalization and so on. So we'll see that in a bit. So this is for one of the columns. Let's take another column, which is applicant income. Similar situation. You have most of your observations in this range, but there are also some which are far off from where most of the observations are. So this is also this also has some extreme values. So we'll have to see what can be done. Credit history is the binary value. So some people have a 0 value and some will have credit history of 1. This is just like a flag. So this basically is telling us how many people have a 1 and how many people have 0. So looks like majority of them have a value of 1 and a few, about 100 of them, have a value of 0. Okay, what else can we do? So we now understood a little bit about the data. So we need to do some data wrangling or data munging and see if we can bring in some kind of normalization of all this data, and we will kind of try to understand what is data wrangling and before we actually go into it. Okay, so data wrangling is nothing but a process of cleaning the data. If let's say there are multiple things that can happen. In this particular example, there were no missing values, but typically when you get some data, very often it will so happen that a lot of values are missing. Either they are null values or there are a lot of zeros. Now you cannot use such data as it is to perform some, let's say, predictive analysis or perform some machine learning activities and so on. So that is one part of it. So you need to clean the data. The other is unifying the data. Now if these ranges of this data are very huge, some of them are going from some columns are going from 0 to 100,000 and some columns are just between 10 to 20 and so on. These will affect the accuracy of the analysis. So we need to do some kind of unifying the data and so on. So that is what data wrangling is all about. So before we actually perform any analysis, we need to bring the data to some kind of a shape so that we can perform additional analysis, actual analysis on this and get some insights. Now, how do we deal with missing values? This is a very common issue when we take data or when we get data from the business, when a data scientist gets the data from the business. So we should never assume that all our data will be clean and all the values filled up and so on, because in real life, very often the data will be dirty. So data wrangling is the process where you kind of clean up the data. First of all, identify whether the data is dirty and then clean up. So how do we find some data is missing? So there are a few ways. You can write a small piece of code which will identify if for a given column or for a given row any of the observations are null primarily. So this line of code, for example, is doing that. It is trying to identify how many null values or missing values are there for each of the columns. So this is a lambda function, and what we are saying is find out if a value is null and then you add all of them. How many observations are there where this particular column is null. So it does that for all the columns. So here you will see that for loan ID, obviously it's an ID, so there are no null values or missing values. Gender has about 13 observations where the values are missing. Similarly, marital status has 3 and so on and so forth. So we'll see here, for example, loan amount has 21 observations where the values are missing. Loan amount term has 14 observations and so on. So we'll see how to handle this missing values. So there are multiple ways in which you can handle missing values. If the number of observations are very small compared to the total number of observations, then sometimes one of the easy ways is to completely remove that data, or delete that record, exclude that record. So that is one way of doing it. So if there are, let's say, 1 million records and maybe 10 records are having missing values, it may not be worth doing something to fill up those values. It may be better off to get rid of those observations, right? So that is the missing values are proportionately very small. But if there are a relatively large number of missing values, if you exclude those observations, then your accuracy may not be that very good. So the other way of doing it is we can take a mean value for a particular column and fill up wherever there are missing values, fill up those observations or cells with the mean value. So that way what happens is you don't give some value which is too high or too low, and it somehow fits within the range of the observations that we are seeing. So this is one technique. Again, it can be case to case, and you may have to take a call based on your specific situation, but these are some of the common methods. If you see in the previous case, loan amount had 21, and now we went ahead and filled all of those with the mean value. So now there are 0 with missing values. Okay, so this is one part of a data wrangling activity. What else you can do? You can also check what are the types of the data. So df.dtypes will give us what are the various data types. So all right. So you can also perform some basic mathematical observations. We have already seen that mean we found out. So similarly, if you do call the mean method for the data frame object, it will actually perform or display or calculate the mean for pretty much all the numerical columns that are available in this, right? So for example, here applicant income, co-applicant income, and all these are numerical values. So it will display the mean values of all of those. Now, another thing that you can do is you can actually also combine data frames. So let's say you import data from one CSV file into one data frame and another CSV file into another data frame, and then you want to merge these because you want to do an analysis on the entire data. Okay, one example could be that you have data in the form of CSV files, one CSV file for each month of the year, January, February, March, each of these are in a different. So you can import them into, let's say, 12 data frames, and then you can merge them together as a single data frame, and then you perform your analysis on the entire data frame or the entire data for the year. So that is one example. So how do we do that? This is how we do. Again, in this case, we are not importing any data. We are just creating some random values, using some random values. So let's assume I have a data frame which is by the name 1, and I assign some random values here, which is a 5x4 format. So there are 5 rows and 4 columns, and this is how my data frame 1 looks. And then I create another data frame, which is data frame 2, again random numbers of the format 5x4, and I have something like this. Now I want to combine these two. How do I combine these two? I can use the concatenate or concat method, and I can combine these two. So pd.concat, and it takes the data frames 1 and 2. If you have more of them, you can provide them, and it will just simply add all of them, merge all of them, or concatenate, whatever you call, whichever term you call, it will. So of course we have to make sure that the structure remains the same. Like I said, this could be, let's say, sales data coming for 12 different months, but each of the files has the same structure. So now you can combine all of them, merge all of them using the concat method. If we have, let's say, structure is not identical, then what will happen? Let's say we have these two data frames. One has a column by the name key, and the second column is lval, and a second data frame which has a column by the name key, but the second column by the name rval, not lval. So you see here the structure is not identical. So you can still combine them, but then the way they get combined or merged is somewhat like this. So it takes the key as a common parameter between them. Some common column has to be there, otherwise this will not work. And then we have to use merge instead of concatenate. And when we do a merge, then we get the result will be in this format. What it does is it uses the key as a common thread between them, and then it kind of populates the values accordingly. So if you see here, the first one had foo and bar for key, and then it had L values of 1 and 2, right? So if we go back, foo and bar had 1 and 2 L values. So that's what we see here, 1 and 2. Whereas in the right data frame, we had foo, bar, and bar as a second time, and then R values are 3, 4, and 5. So what it has done for foo, it has put for the existing, right? For foo is already existing because it has come from left. So it will just put the value of R val here, which is 3. Similarly, it will put 4 here because for bar, if you go back, for bar it is the value is 4. And since it has one more value of bar, it will go and add this 5 as well. The only thing here is that this one had, for example, left had only 2 values and only 1 value for bar. But since we are appending or merging, and there are 2 key values with the bar, therefore it will kind of repeat the value of lval here. So that's what we are seeing in this case, right? So L value appears twice, the number 2 appears twice, but that is because R value, there are 2 of them. Okay. All right. So that is how, when you don't have identical structure, that is how you merge. Now we will talk a little bit about scikit-learn. So scikit-learn is a library which is used for doing machine learning or for performing machine learning activities. So if you want to do linear regression, logistic regression, and so on, there are easily usable APIs that you can call. And that's the advantage of scikit-learn, and it provides a bunch of algorithms. So I think that is the good part about this library. So if you want to use scikit-learn, obviously you need to import these modules, and also there are some sub modules you may have to import based on what you're trying to use. Like for example, if we know if we want to use logistic regression, again, people who are probably not very familiar with machine learning, there is a separate module for machine learning. You may want to take a look at that, but we will just touch upon the basics here. So machine learning has some algorithms like linear regression, logistic regression, and random forest classification, and so on. So that is what we are talking about here. So those algorithms are available, and if you want to use some of them, you need to import them, and from the scikit-learn library. So scikit-learn is the top level library, which is basically sklearn, right? And then it has a kind of subparts in it. You need to import those based on what exactly you will be or which algorithm you will be using. So let's take an example as we move, and we will see that whenever we perform some machine learning activity, those of you who are familiar with machine learning will already know this. We split our labeled data into two parts, training and test. Now, there are multiple ways of splitting this data. How do we some people do it like 50-50, some people do it 80-20, which is training is 80 and test is 20, and so on. So it is an individual preference. There are no hard and fast rules. By and large, we have seen that training data set is larger than the test data set. And again, we will probably not go into the details of why do we do this at this point, but that's one of the steps in machine learning. So scikit-learn offers a readily available method to do this, which is train test split. All right, so in this example, let's say we are taking the values x and y are our values. X is the independent variables and y is our dependent variable. Okay, and we are using these two, and then I want to split this into train and test data. So what do? We import the train test split submodule from within scikit-learn, which is sklearn, right? So within that we import train test split, and then you call this train test split method or function or whatever you call it and pass the data. So x is all the values of the independent variables and y is our labels. So you pass x and y, and then you specify what should be your size of the test data. So only one you need to specify. So if you say test size is 0.25, it is understood that train size will be 0.75. So you're telling what should be the ratio of the split. So technically nothing prevents you from giving whatever you like here. So you can give test as 80 and train as 20, so whichever way, but then the normal practice is you will have the training data set would be larger than the test data set, and typically it would be 80-20, 75-25 or 65-35, something like that, right? So that is the second parameter, and this is just to say that the data has to be randomly split. So it shouldn't be like you take the first 75% and put it in training and then the next 25% and put it in test, so such a thing shouldn't happen. So we first set the state, random state, so that the splitting is done in a very random way. So they are randomly picked up the data and then put it into training and test, and then this results in these four data frames. So x train and x test and y train and y test. Okay, so that is basically the result it will return. Now that the splitting is done, let's see how to implement or execute logistic regression. So in logistic regression, what we try to do is try to develop a model which will classify the data. Logistic regression is an algorithm for supervised learning for performing classification. So logistic regression is for classification, and usually it is binary classification. So binary classification means there are two classes. So either like a yes, no, or for example, customer will buy or will not buy. So that is a binary classification. So that's where we use logistic regression. So let's take a look at the code, how to implement something like that using scikit-learn. So the first thing is to import this logistic regression submodule or subclass, whatever you call it, and then create an instance of that. So our object is classifier. So we are creating an object by the name. This is a name, by the way. You can give any name. In our case, we are saying classifier. We say classifier is equal to logistic regression. So we are creating an instance of the logistic regression variable or class or whatever. Okay. And you can pass a variable or a parameter rather, which is the random state is equal to 0. And once you create the object, which in our case is named classifier, you can then train the object by calling the method fit. So this is important to note. We don't call there is no method like train here, but we call what is known as, there is a method called fit. So you're basically, by calling the fit method, you're training this model. And in order to train the model, you need to pass the training data set. So x underscore train is your independent variables, the set of independent variables, and y underscore train is your dependent variable or the label. So you pass both of these and call the fit function or fit method, which will actually result in the training of this model classifier. Now, this is basically showing what are the possible parameters that can be passed or initiated when we are calling the logistic or the instance of logistic regression. So this is, but you can also look up the help file if you have installed Python. So some of these are very intuitive, but some you may want to take a look at the details of what exactly they do. All right, so moving on. Once we train the model by calling fit, then the next step is to test our model. So this is where we will use the test data. You need to pay attention here. Here I am calling, so there are two things. One is, in order to test our data, we have to actually call what is known as the method known as predict. Right? So here, this is where, so the training is done. Now is the time for inference, isn't it? So we have the model. Now we want to check whether our model is working correctly or not. So what do? You have your test data. Remember, we split it, 25% of our data was stored here, right? We split it into test and training. So that 25% of the data we pass to and call the method predict, so that the model will now predict the values for y. Right, so that's why here we are calling it as y_predict. And if we display here, as I said, this is a logistic regression, which is basically binary classification. So it gives us the results like yes or no in this particular case. And then you can, so this is what the model has predicted or model has classified. Now, but we also know we already have the labels for this. So we need to compare with the existing labels, with the known labels, whether this classification is correct or not. So that is where is the next step, which is basically calculating the accuracy and so on will come into play. Okay, so in this case, the first thing, most important thing to note is we do the prediction using predict, and here we are passing x_test and not train, right? In this case, we did x and y train. So again, one more point to be noted here. In case of training, we will pass both the independent variables and also the dependent variables, because the system has to internally, it has to verify. That is what is the training process. So what it will do, it will take the x values, it will try to come up with the y value and compare with the actual y value, right? So that is what is the training method. So that's why we have to pass both x as well as y. Whereas in case of predict, we don't pass both, we only pass because we are pretending as if this is the actual data. So in actual data, you will not have the labels, isn't it? So we are just passing the independent variables, and the system will then come up with the y values, which we will then, okay, remember, we also know the actual value. So we will compare this with the actual values and we will find out whether how accurate the model is. So how do we do that? We use what is known as a confusion matrix. So this is also readily available in the Python library. So we import this confusion matrix, and some of you who already know machine learning will find this familiar, but those who are new to machine learning, this confusion matrix is nothing but this matrix, this kind of a matrix, which basically tells how many of them are correctly predicted and how many of them are incorrectly predicted. So some of the characteristics, let's quickly spend some time on this confusion matrix itself. The total numbers out here, these are just the numbers, these are like number of observations. Then the accuracy is considered to be highest when the numbers or the sum of the numbers across the diagonals is maximum, okay, and the numbers outside of the diagonals should be minimum. So which means that if this model was 100% accurate, then the sum of these two, there would have been only numbers in these two along the diagonal, this would have been 0 and this would have been 0. Okay, so that is like 100% accurate model. That is very rare, but just that you are aware. So just to give an idea. Okay, all right. So once you have the confusion matrix, you then try to calculate the accuracy, which is in a percentage. So there are two things that we can do from a confusion matrix, or that we can calculate from a confusion matrix. One is the accuracy and the other is the precision. What is the accuracy? Accuracy is basically a measure of how many of the observations have been correctly predicted. Okay, so let's say this is a little bit more detailed view of the confusion matrix. It looks very similar like as we saw in this case, right? So this is a 2x2 matrix. That's what we are seeing here, 18, 27, 2, 103. So 18, 27, 2, 103. Now, but what are these values? That is what is kind of the labels are shown here in this. So there are altogether 150 observations. So as I said, the sum of all these four, right? 18 plus 27 plus 103 plus 2 is equal to 150. That's the first thing we have to observe. The sum of all these values will be equal to the sum of test observations, number of test observations. We have 150 test observations, because remember we had about 500. We split that into 2575. So that is why we have 150 here and I think 350 in the training data set. Okay, so that we get the numbers correct. So that's the first thing. Now the next thing is, let's take a look at the actual values. This view is the actual view. So there are actually, right, in the actual data we have labels yes and no. So as per the actual data, there are 45 observations tagged as no, and similarly there are 105 observations that are tagged as yes or labeled as yes. Okay, now I know for the first time when you're seeing this it may be a little confusing, but just stay with me. Okay, so this is the actual part of it, and this side tells us the predicted part of it. So our model has predicted, and it has totally predicted 20 of them as no, right? So that is what this is. Totally 20 of them it has predicted as no, and it has predicted 130 of them as yes. Okay, I hope this part is clear. So before we go into the middle part, let us first understand what exactly are these numbers. So actually tagged as no, there are 45 total. Actually tagged as yes, there are 105. And predicted no, there are 20. Predicted as yes, there are 130. This is the result from our model. Okay, this is the result from our model, and this is the actual value which we already know because this is our label data. That's the first thing. Now let us take a look at each of these individually. Okay, now what are the options we have? Once again, okay, so now what is happening here? Let us look at these values. So this 18 says that these are actually tagged as no, and the model has also predicted as no, which means this is what is known as a true positive, right? Or true negative, sorry, right? Which means that our model has predicted it correctly. It is negative because it says no, so, and it has also predicted no, so it is known as what is known as true negative. Okay, now let's come to this side of it. That way we are talking about the diagonal. Remember I said most of the values should be in the diagonal. Okay, so that means these 18 are correctly tagged. They are labeled as no, and our model has predicted as no, so these are correctly tagged, and these are known as true negative. Okay, similarly if we come diagonally down, there are 103 observations which are labeled as yes, actual value is yes, and our model has also predicted as yes, and these are known as true positive values. Positive because of this yes. Okay, right? So what is important is this is true, this is also true. So we have to make sure that the maximum number of values are in the true section. Okay, true positive and true negative. That's the reason I said the sum along the diagonal should be maximum. Now let's say if our model was 100% accurate, this sum, in this case it is only 103 plus 18, which is 121. But if our model was accurate, the sum of these two would have been 150. That means it's a perfect model. Okay, all right. Now what else? Since we covered these two, let's also cover these two. So here this says that 27 of them were actually labeled no, but our model has predicted as yes. That means this is wrong, right? Similarly, these are two of them where the actual value is yes, but our model has predicted as no. That means it's a wrong prediction. So you get the point? So therefore, along the diagonals are the correct values, whereas in other places it is all wrong values or wrong predictions. Okay, now how do we calculate accuracy from this information? So the way to calculate accuracy is, so we say, okay, there are total observations are 150, and what are the correctly predicted values? These are the correctly predicted values, which is 18 plus 103. So this will give us our accuracy. So 103 plus 18, which is 121, divided by our total observations, which is 150, is our accuracy, which is 0.8, or we can say it is 80%. Okay. Now there is another concept called precision. So precision is given by the formula true positives divided by the predicted positives, totally predicted positives. Okay, what do we mean by that? Which are the true positives here? Remember, which are the true positives? We just recall, we just talked in the previous slide. Which are the true positives you see here? So this 103 are the true positives, which means that the value is positive, actual value is positive, predicted value is also positive. So that's why it's called a true positive. So 103 divided by, so that is our true positive, 103 divided by totally predicted as yes. Now what is totally predicted as yes? Remember, 130 of them have altogether been predicted as yes. Not that they are correctly predicted, only 103 have been correctly predicted, but 130 of them have been predicted as yes. So precision is basically the ratio of these two. Out of the totally predicted, how many of them are actually true? That ratio. So 103 by 130, which is again about 80%, is the precision. That's how you calculate precision. So this is just a simple formula and a term that you need to remember. So accuracy is, you need to take total of true positive and true negative divided by the total number of observations, whereas precision is true positives divided by the totally predicted positives. Okay, so that is our accuracy and precision. Now what we did, the accuracy calculation was manual, but we can also use some libraries which are already existing and the functions within that library. So Scikit-learn provides one such method. So for example, accuracy underscore score is one such method. So if you use that and pass your test and predicted values, only the y you need to pass, right? The dependent variable values. So if you pass that, it will calculate it for you. So in this case, again, as you can see, it still calculates the same, which is 80%, which we have seen here as well. Okay, so this can be done using the method. Great. So that's pretty much what we have done here. Before we conclude, let me take you into the code and show you how it actually looks. Okay, so this is our code. Let me run it. Okay, one by one. We have already seen most of the steps in the slides, so I will run this in the actual Jupyter Notebook. Some of you, if you are not yet familiar with Jupyter Notebook, again, there are other videos we created on how to install Jupyter Notebook and how to set up Jupyter Notebook and so on. In this tutorial also, there was one slide on how to install Python and Jupyter Notebook. If you have not yet done, please do that, so that then you can actually walk through this code while you're watching this. Okay, so what are we doing here? We are importing the libraries, required libraries. Recall here we have pandas, we have numpy, and for visualization we have matplotlib, and this line is basically reading the CSV file. So we have the CSV file locally on our local drive, and this is where I'm checking the data. So I'm starting with my exploratory analysis, how the data is looking. So it looks good. There are no major missing values or anything like that. So it will display all the columns, and it will show me the first 5 rows when I'm using this head function. And then I want to see a kind of a summary of each of the numerical columns. So that's what I'm doing here. So these are the numerical columns, and it gives a summary like how many observations are there, what is the mean, standard deviation, minimum, maximum, and so on and so forth for each of them. And then you can do some visualization. So this is the visualization for this. Okay, the next step is to view the data visualization, and we will do that using a histogram for a couple of these columns. So in this case, I'm taking a look at the loan amount, and if I create the histogram, it displays the data here in the form of a histogram. One thing that we gather from this, as I mentioned in the slides as well, is how the data is kind of scattered. So while most of the values are in this range 0 to 300 range, there are a few extreme values around the 700 range. So that is one information we get from this histogram. Similarly, for the applicant income, if we draw a histogram, something similar we can see that while most of the values are in this range 0 to 20,000 range, there are a few in the range of 80,000 and probably 65,000 and so on. Okay, so the next step is to perform data wrangling, where we will check if any data is missing and how to fill those missing values and so on. So in this case, we will just check for all the columns, how many data or how many entries are there with missing values. So this is the result. So loan ID has all the columns or all the cells filled. Gender has 13 missing values. Marital status has 3 missing values, and so on and so forth. Loan amount has 21. And this is what we are going to show you how to remove these missing values. So when you have missing values, as I mentioned during the slide, bytes, there are a couple of ways of handling that. One is you can completely remove those, or you fill in with some meaningful values. So in this case, we will fill the missing values with the mean value of the loan amount. So let's go ahead and do that. And now if we check here, now loan amount, number of missing values is 0, because what we did was for all these 21 cells where the values were missing, we filled with the mean value of the loan amount. So now there are no more missing values for loan amount. We can do this for other columns as well, but this was just one example, so we have shown it here. Okay, so we will run this for credit history and loan amount term as well. And then if we calculate the mean of pretty much all the numerical columns, that's the method call. So df.mean will give us the mean of all the numerical values. And another thing that we can do is if you want to find out what are the data types of each of these columns, so you can call df.dtypes and get the data types. Of course, it may not be that very useful. Most of the cases is an object, but for example, this one it shows as int 64 and there are float 64 and so on and so forth. Now, in addition to doing the exploratory data analysis, we can do some machine learning activity as well. So in this case, we are going to do logistic regression. So this is the example that I have shown you in the slides as well. This is the actual code for that. All right. So the first step here is to import the libraries. And then the next step is to separate the independent variables and the dependent variables. So X is our independent variable and Y is our dependent variable. So we separate the data into two parts, and this will be our target as well, right? So that's how we separate it. Now we have to split the data into training and test data sets. As I mentioned during the slides, we use the train test split method, and when we call this and pass the independent variables and the dependent variables, and we specify the test size to be 0.25, which means the training size will be 0.75, which is nothing but you split the data into training data set, which is 75%, and test data set which is 25%. Okay, so once you split that, you will have all your independent variables data in xtrain, the training data, which is 75% of it. Similarly, independent variables for test will be in x underscore test, and dependent variables train will be in y underscore train, and dependent variable test will be y underscore test. Once we do this, we have to do a small exercise for scaling. Remember, we had some data which was kind of very scattered. There were some extreme values and so on. So this will take care of that, so that the data is normalized, so that before we pass to our algorithm, the data is normalized so that the performance will be much better. The next step is to create the instance of logistic regression object. So that's what we are doing here. So classifier is our logistic regression instance, right? Classifier is equal to logistic regression, we are saying. So one instance of logistic regression is created, and then we call the training method. The name of the method actually is fit, but what it is doing is it is taking the training data. X is the training data, the independent variables, and Y is the dependent variables. So we are taking both of these and the model gets trained. So the method for calling the training is fit. Okay, so it gives us the output, and then once we are done with the training, we do the testing. And once again, just to recall, in the slides when I was showing you the slides also I mentioned, we don't pass Y here while we are testing. While for training we do pass Y, but right, so for fit we are passing X and Y, but for test we are only passing X, something you need to observe, because Y will be calculated by the model, and we will then compare that with the known value of Y to measure the accuracy. So that's what we will do here, and the method that is called here is predict. So this will basically create or predict the values of Y. Now we have in this case a binary classification, so the outputs are yes or no. Y indicates yes and N indicates no, so Y or N is the output. Now how do we measure the accuracy? As we have seen earlier, I described how confusion matrix works and how we can use confusion matrix for calculating the accuracy. That's what we are seeing here. So this is the confusion matrix, and then you want to do the measure the accuracy, you can directly use this method, and we find that it is 80%. So we, in the slides we have seen, when we calculate manually as well, we get an accuracy of 80%.
Before we move ahead with the session, Let's hear from our learners about their personal experience and their success story after graduating from the Data Science Postgraduate Program offered by Simplilearn.
Hi, my name is Priya. I'm an Associate Vice President with a leading MNC bank, a proud mother of 2 kids, a Simplilearn and a Purdue alumni. After working for 15 plus years and understanding the rapid change in technology and the dynamic disruption, the way data is going to be handled, I realized it was time for me to upskill. So when I started actively looking for data science courses in January last year, I came across the PGP data science course from Simplilearn in collaboration with the Purdue University. And then I firmed my decision that this is where I want to do it from. Because I have a family and a job, moving at that point in time in my career was not feasible at all. Simplilearn was offering me the chance to get myself graduated from a premier university without having to travel all the way to the US. Going in, my main goal was to upskill, and after completing the course from Simplilearn, I can proudly say that now I have upskilled myself in data science. Upskilling has helped me to bring in better solutions to my organization and has broadened my perspective to the way I now handle work. Do you know, the great thing about the course was it gave me an option to choose when I wanted to take the class. So every Saturday and Sunday, when I was doing the course, my husband would take the responsibility of the kids from 6 p.m. to 11 p.m. so I could concentrate on the work. With the liberty to choose my own batch, I picked up the night classes during the weekends, and in that way, it did not impact my day or my work as such.
Mama, I am very proud of you that when I was studying, you were studying. You are such an inspiration to the other mothers out there who want to get back and study.
Feeling inspired already? Consider checking the Data Science Postgraduate Program offered by Simplilearn from Purdue University in collaboration with IBM. For more details, use the link in the description box below. So we will be learning the data science algorithms today by going through the following docket. At first, we will learn the logistic regression in R. Then we will move ahead and know what is a decision tree. Followed by that, we will understand what is clustering. Next, we will learn divisive clustering. Later, the support vector machine. Advancing ahead, we will have the k-means clustering. And lastly, we will wind up the session by learning time series analysis. I hope I made myself clear with the agenda. Now, escalating over to our training experts.
Hello and welcome to Logistic Regression in R. My name is Pete Ferrari and I am with the Simplilearn team, and today we're going to cover logistic regression in the R programming language. Logistic regression is kind of a misnomer in that when most people think of regression, they think of linear regression, which is a machine learning algorithm for continuous variables. However, logistic regression is a classification algorithm, not a continuous variable prediction algorithm. Logistic regression is also sometimes called logic regression. In this video, we are going to learn why we would use regression as a predictive algorithm, what is regression, the different types of regression. As I've already mentioned, some regression algorithms are classification algorithms, and some are continuous variable algorithms. Why use logistic regression? What is logistic regression? And then we'll look at a use case, a college admission using logistic regression. So why would we use regression? Well, let's say we had a website and our revenue was based on the traffic that we could drive to that website, whether through R&D or marketing, and we wanted to predict the revenue based on site traffic. And the website traffic would be related to the revenue we could generate. The more traffic driven to our website, then the higher our revenue, or at least that's what we would intuitively assume. And so we need to predict the revenue based on our website traffic. Here we have the plot of revenue versus website traffic. Traffic would be considered the independent variable and revenue would be the dependent variable. Often the independent variable or variables, if we had more than one, could be called the explanatory variables, and the dependent variable would be called the response variable. However, we typically refer to them as independent and dependent variables. So our intuition tells us that the independent variable drives the dependent variable, and if there is some relationship between the two variables, variables, then we would say that there is a correlation between the two variables. And then we may be able to use the independent variable to make predictions about the dependent variable. If you look at the chart on the right, you'll see there is a clear trend between website traffic and revenue. As website traffic increases, the revenue increases, and we could draw a line to show that relationship. And then we could use that line as a predictor line. So for example, what will revenue be if our traffic is 4.5K? And we see that when the traffic is around 4,500, the revenue is around 13,000. And if we could draw a perpendicular line from 4.5K on the x-axis, the traffic axis, up to the orange regression line, sometimes called the line of best fit, then we could draw another line over to the y-axis, the revenue axis, and we could see where it lands. And that would be the prediction. So in this example, when the traffic is around 45,000 hits, the predicted revenue is around 13,000. Normally, we wouldn't actually draw those lines. We would generate an equation, and we would call that equation a model, and we could plug the independent variable into the equation to generate the dependent variable output, which we would call our prediction. So what is regression? Regression is a statistical relationship between two or more variables where a change in the independent variable is associated with a change in the dependent variable. It's important to note that not all variables are related to each other. For example, a person's favorite color may not be related to revenue from a website. Here, the change in one variable, height, is closely associated with the change in the other variable, age. This makes intuitive sense. As you get older, from when you're born, you get taller. And it seems to make sense if we plot that data, we would see those green points on the graph, up to some certain age where growth would taper off. In the plot in the middle of the screen, we see the clear linear relationship between age and height, which is indicated by the solid red line. We sometimes call that line a trend line or a regression line, or the line of best fit. And we see that the height is the dependent variable and age is the independent variable. Of course, you might ask, doesn't height depend on other factors? Of course it does. But here we're looking at the relationship between two variables, one independent and one dependent, age and height. There are various types of regression: linear regression, logistic regression, multiple linear regression, polynomial regression, and there are others: decision tree regression, random forest regression. But linear regression is probably the most well known. And by definition, when there is a linear relationship between a dependent variable, which is continuous, and an independent variable, which is continuous or discrete, we would use linear regression. When the y value in the graph is categorical, such as yes or no, true or false, they voted, they did not vote, they purchased something, they did not purchase something, it depends on the x variable. Logistic regression is when the y value in the graph is categorical in nature. For example, yes, no, purchased, don't purchase, voted, did not vote, and it depends on the x variable. Notice the trend line for linear regression and the line for logistic regression. They're different. More on that later. And there's polynomial regression as well, when the relation between the dependent variable y and the independent variable x is in the nth degree of x. Sometimes we say an nth degree polynomial of x. In this picture, you can see that the relationship is not linear. There's a curve to that best fit trend line. So why would we use logistic regression? And we need to understand why we would use logistic regression and not linear regression. Picking the machine learning algorithm for your problem is no small task, and it really behooves us to understand the difference between these machine learning algorithms. Linear regression answers the question, how much? So in our earlier example, if website traffic grows, then how much would revenue grow? Whereas logistic regression would answer what will happen or not happen. Linear regression, in general, is used to predict a continuous variable, like height and weight. Logistic regression is used when a response variable only has two outcomes, yes or no, true or false. Often we refer to logistic regression as a binary classifier, since there are only two outcomes. So let's try to understand this with an example. Let's say we have a startup company and we are trying to figure out whether the startup will be profitable or not. That's binary with two possible outcomes, profitable or not profitable. And let's use initial funding to be the independent variable. Here we have a graph that shows funding versus profit, and it appears linear. Once again, our intuition tells us that the more funding a startup has, the more profitable it will be. But of course, data science doesn't depend on intuition, it depends on data. But this graph does not tell whether the startup will be profitable, yes or no. It only states that with an increase in funding, the profit also increases. That's not binary. If we wanted to predict how much profit, then linear regression would be useful. But that's not what we are being asked. Hence, we need to make use of logistic regression, which has two outcomes, in our case, profitable and not profitable. So let's draw a graph again. The x-axis will be our independent variable, funding, and the y-axis will no longer be the dependent variable, profit, but it will be the probability of profit. For example, if you look at a company with a funding of, say, 40, then the probability that that company will be profitable is around 0.8 or 80% based on the best fit line called a sigmoid curve. In the example, we plotted several companies, some with 10, 15, 20, some with 50, 60, or 70, or 65, and we indicated whether they were 0, not profitable, or a 1, profitable, on the graph, and this is how we should think of logistic regression. In this example, given the amount of funding, we calculate the probability that a company will be profitable or not profitable, and if we use the threshold line of 50%, then we have our classifier. If the probability is 50% or higher, the company is profitable. If the probability is lower than 50%, it's not profitable. So what is logistic regression? This is a linear regression graph. So let's compare linear regression to logistic regression and take a look at the trend line that describes the model. It's a straight line, which is why we call it linear regression. But using linear regression, we can't really divide the output into two distinct categories, yes or no. To divide our results into two categories, we would have to clip the line between 0 and 1. If you recall, probabilities can only be between 0 and 1, and if we're going to use probability on the y-axis, then we can't have anything that is below 0 or above 1. Thus, we would have to clip the line. And once we clip the line, we see that the resulting curve cannot be represented in a linear equation. So for logistic regression, we will make use of a sigmoid function, and the sigmoid curve is the line of best fit. Notice that it's not linear, but it does satisfy our requirement of using a single line that does not need to be clipped. For linear regression, we would use an equation of a straight line. Y equals b sub 0 plus b sub 1 times x being the independent variable, y being the dependent variable. But as we've said, we cannot use a linear equation for binary predictions, so we need to use the sigmoid function, which is represented by the equation p equals 1 divided by the quantity 1 plus e to the minus y, e being the base of the natural logs. Then taking the log of both sides and solving, we get our sigmoid function. And graphing it, we get our logistic regression line of best fit. The applications for logistic regression are endless. Here, we might have a couple of gardeners or farmers, and one farmer says, I am planning to grow plants in my backyard, and I want to know whether my trees will get infested with bugs, which I'm sure is a huge problem. And these days, the fewer pesticides we use, the better off we are for health reasons. The young lady says, I can use logistic regression in a model to predict it for you. And the other farmer says, well, how is logistic regression going to help? But we know that healthy versus not healthy is a binary classification, and we can use a binary classifier like logistic regression to solve this problem, which is what the young lady has in mind. If we have the data, we can model the data and generate a sigmoid function that best fits our data, and then use the probability of a healthy tree versus a not healthy tree or an infested tree. Once again, we see our sigmoid line of best fit and some points that represent healthy trees and not healthy trees. Once again, we plot our sigmoid curve, scratch that. And once again, once our sigmoid curve is plotted and our threshold is set almost always at 50%, we can use the sigmoid curve and calculate the probabilities, and here the independent variable of width, which I assume is an application of pesticides or no pesticides, to determine whether or not the probability of healthy is greater than 50%, the threshold, or less than 50% the threshold. And now let's take a use case of a college admission problem. Of course, we can't solve anything using data science if we don't know what the problem is. So we need a problem statement. And here, the problem statement is simple. We are given a data set and we need to predict whether a candidate will get admission in a desired college or not based on their GPA and college rank. So the very first thing we need to do is import the data set. And if it's a small enough data set and it can fit into our computer memory, then we are golden. Otherwise, we have some work to do. The data set that we were given is in CSV format, comma separated values. CSV files are easily imported into our environment. Once we import the data, we next need to select and import the libraries that we will need. Although R is a great programming language with a lot of built-in functions, it is easily and powerfully extended by the use of libraries and packages. Then we need to split the data set into a training set and a test set. It's important to note that the data set that we've imported, that we were given, has the GPAs and college ranks for several students, but it also has a column that indicates whether those students were admitted or not. So what we're saying is that the data set has the answers. And if you think about it, it must. How could we possibly train a model, have a model learn, if we didn't know the answers already? That's why it's called machine learning. So we train the model and then we test the model. Once we split the data into training and test sets, we will apply our regression on the two independent variables, GPA and rank, generate the model, and then run the test set through the model. Once that is complete, we will validate the model to see how well it performed. So now it's demo time. So here we have our studio, my favorite IDE, or integrated development environment. And I have a script already composed to run our logistic regression on the problem at hand, which is our college admissions problem. So let's just walk down the script before I run it and talk about the various points in the script. So first, define the problem. Well, the problem was defined, and you really can't do anything in data science without a clear problem definition. Once the problem's defined, you can load your libraries, acquire your data, set the working directory. In my case, I'm on Windows. Explore the data, munge the data if necessary, and then prepare the data. Scale the data if necessary, split the data into train and test data sets. Then train the model using the training data and run the test data through the model, and then validate the model for accuracy and precision, etc. So here we are going to load our libraries. I'm going to use a package called CA Tools. And now that the library is loaded, I'm going to set my working directory. And if I come over here to the Files tab, you'll see that there is my working directory. In that working directory, there's a file called binary.csv, and that's the CSV, the comma separated value file that the college gave me. I'm going to ingest and then look at that data. And as you can see, it has 4 columns, GRE, GPA, rank, and then the answer column, admit, whether or not someone was admitted, which would be a 1, or not admitted, which would be a 0. And if we come over to the right, we can look and see some of the first few values of each of those 4 columns. Now let's split the data. We're going to take this my data frame and split it into 2, a training set and a test set. And the ratio we're going to use is 80-20. So 80% of the data will go into the training set and 20% will go into the test set. Now that ratio could be 60-40, it could be 70-30. Typically, it really depends on the size of your data, how much data you have. But this is, for our example and for our purposes, 80-20 is perfect. Next, we'll do a little data munging. In general, you munge the data early on after ingestion, and you really have to be careful. In this case, we don't have any missing values. We don't have any real outliers. Our data was pretty clean when we got it and ingested it. But in general, that's not the case, and a lot of work and a lot of attention needs to be paid to the munging process. Here, we're just going to take our data, the admission column and the rank column, and convert them to categorical variables. Right now, they're integers, as you can see on the right-hand side. And once I run these 2 lines, they will be converted to factors. And now the fun stuff. we're going to use the GLM function, the general linear model function, to train our logistic regression model. And the dependent variable is admit, and the independent variables are GPA and rank. And the little tilde sign here says the dependent variable will be a function of GPA and rank, the two independent variables. The data will be the training set, and the family will be binomial. And binomial indicates that it's a binary classifier. It's a logistic regression problem. There it is. We ran our model, and there's a summary of our model. You can see that there is some statistical significance in GPA and in rank by the coefficients and output of the model. So next, let's run the test data through the model. And once we have done all that, we can now set up a confusion matrix and look at our predictions versus the actual values. Again, this is important. We had the answers, and now we took and we predicted some answers. So hopefully our predicted answers match up with the actual answers. We'll run a confusion matrix. As you can see, the predicted values versus the actual values. And it's important here to note that if it was predicted false and it was actually false, and we see 189, or if it was predicted true and it was actually true, which is 27, we did well on those. But there are a few that were predicted incorrectly. Some were predicted true but were actually false. Some were predicted false that were actually true. And now we'll confirm what our percentage accuracy is, 72%. Not bad, but we could probably do better. How? We'll leave that to another video.
What is a decision tree? And here we have kind of a new looking front panel of a car driving down the street. And we have left or right. So you come into an intersection, you got to decide which way to go. Are you going to go left or are you going to go right? Wait or go? So do you go right away? We have a green light, so probably want to go right away after you check for cross traffic and make sure no one is asleep at the wheel or talking on their cell phone. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So another example is we have a shopkeeper. Very nondescript shopkeeper. Kind of a little spooky without the eyes. So we have a shopkeeper, and he wants to organize his stall. So I must organize my stall, and he's looking around trying to figure out what the best way to stack all his goods are. And he has some broccoli, some oranges, and some carrots. This is kind of a nice example because we can see where some of the colors and shapes overlap where others don't. And so you can create a tree out of this very easily. You can say, is it colored orange? If it's not, well, it goes into one stack. Well, that happens to be all their broccoli. And if it is colored orange, then it goes into another stack. And you're like, well, that's still kind of chaotic. You know, people are looking at carrots and oranges, a very strange combination to put in a box. So the next question might be, is it round? And if it is, then yes, you put the oranges into one box. And no, that means it's carrots, we put it in the other box. And you can see that a lot of stuff we do in life easily can fall into like a decision tree. How do you decide something? You know, does it go left? Does it go right? Yes or no? And even with this, we even have a number of different end choices: broccoli, carrots, and oranges. So what kind of problems does this solve? What problems can be solved by using a decision tree? Classification. We're dealing with a classification, identifying to which set an object belongs. And from our example we just looked at, a carrot is orange while broccoli is green. I guess it's nondescript day. It's kind of without the faces. I love it. Because a lot of times when you're looking at data, you really don't want to know what exactly the data is, but you're sorting it. So, you know, like this kind of represents data that you really don't know exactly where it's coming from. Just kind of a fun thing. Regression. Regression is another problem that can be solved. Regression problems have continuous or numerical valued output variables. Example, predicting the profits of a company. So we have two different primary problems we solve for. We solve for classification, is it green or is it orange? And we solve for regression, which is a continual number. So, you know, if you're doing stocks, this would be a dollar value that ranges anywhere from 0 to thousands of dollars. How does a decision tree work? Terms you must know first. So before we dive into the decision tree, let's look at some of the terminology for the decision tree. We have nodes. Each internal node in a decision tree is a test which splits the objects into different categories. And continuing with our vegetable stand example, we have broccoli, no, it's not orange, and oranges and carrots are, and so on. So you can see right there where it splits, that's a node, where the oranges split and the carrots split into each of their own groups. And each one of the splits is a node. The very top node of the decision tree is called the root node. So the very first one we started off where we split it is it colored orange. And you can see that pointed out nice and neatly there. This is a root node at the top. Each external node in a decision tree is called the leaf node. The leaf node is the output. And you can see down here we have our broccoli and we have our carrots and our oranges. Each one of those is a leaf node. So to quickly rehash our terms, we have anywhere there is a split, that's a node. And if it's at the very top of the tree, that's the root node. And if you're at the very bottom of the tree where you have a final answer, that is the leaf node. So you have a root node, a leaf node, and then everything else is just a generic node. So one of the most important terms or concepts that powers a decision tree is entropy. Entropy is a measure of the messiness of your data collection. The messier or more random your data, higher will be the entropy. So we can see here we have broccoli, oranges, and carrots are all mixed together, and it's very chaotic. And you could say this collection has high entropy. And if we sort out the carrots out of here, and I guess just one of the broccoli, I don't know where the other broccoli went. You could say if you have just the oranges and the broccoli, this is a lower entropy. They say this collection has low entropy, but really it's higher and lower. One is higher or lower than the other one. And from entropy, we get information gain. Information is the decrease obtained in entropy by splitting the data set U based on some conditioning. So we have our information 1, which we can actually, there's actual computations. And so we have our E1, which is put in there for our entropy value at the base node or root node. And we have A2, which is a leaf node. And so we can actually calculate, there's calculations for entropy. And we actually look at those two values, the entropy, and we take that, we have E1 is greater than E2. Therefore, the information gain equals E1 minus E2. So here we have another example, and we're actually going to attach some values to this one in just a moment. So we're going to move away from the fruit, and we're going to go to everybody's favorite thing, organizing a child's closet. And here we have a young lady waving at us, "Hi, my cupboard is a mess. I must organize my stuff." And we're going to classify the objects based on their attribute set using a decision tree. We can look at it, we have a shape, a size, and a label, and a number. And I'm going to go ahead and look at the labels, because that's really what's key on this one, is we have a couple balls in here, some books, cards, and blocks. And if you look at that, when you have something that's a ball, it's round, so it's a very different shape. The book, card, and blocks are all rectangular, but the books are a different size. So the books have like a size 6. I guess you think of them as very large. Cards a size 4, so they're not quite as big. And the blocks are little Lego blocks that looks like kind of fun to stack on there. And then we can actually quantify this, and we can actually say, hey, we have different numbers. We have 2 balls, 2 books, 1 card, 4 blocks. And we split at each level based on certain conditions on the attributes. So splitting aims at reducing the entropy. And we have a formula, our first actual formula that you'll see happens in the background when we're running these different modules in R. And it looks a little complicated, but we can break that up and simplify that for you. So we see this formula, the negative sum of I of x equals the probability of 1 value of x times the log of 2 probability value of x. The term probability value of x, it's probably easiest to understand if we go ahead and put the numbers in there so you can actually see what we're looking at. And so we plug the numbers in there, we look at the probability of the value of x. Well, if we do the number of balls, there's 2 balls, and the total number of items is 9. So we have a probability of any one object being 2 out of 9. So that's pretty straightforward math. When you look at the numbers, you can actually see that very easily. And so we can calculate our entropy of 2 over 9 times the squared log of 2 over 9 plus 1/9 the log squared of 1 over 9 plus 4 over 9 times the log squared of 4 over 9. So our whole group is the sum of all the entropies. And so when we look at that, we have the entropy of the balls, which is the 2 over 9, rectangles 2 over 9, books 2 over 9, cards 1 over 9, and the blocks 4 over 9. And we can just plug those numbers in there, and we get an actual value of 1.8282. So what the heck does a module do with that number? Well, now we must find the conditions for our split. Every split must give us the maximum achievable information gain. And so we have our first entropy value, 1.8282, and it turns out when you compare all the different individual entropy values for the balls, for the books, for the cards, for the blocks, rectangles, you find out that the biggest split is going to be in the shape. And it's going to be, our first split will be on the shape that will directly segregate the balls out. So they'll split up a huge group from the other. And so when we compute that, we end up with E2, which is all of our rectangles. And then we have a leaf node, which is the balls. And so with our E2, we see that 1.3784 is much less than the 1.8282. And so our second split will be on the size, as that will directly segregate the books. And so when we do that, we can see that if the size is greater than 5, all the books go to one side, while the cards and the blocks go to the other. And again, we have our E3, which equals 0.716, which is considerably less than 1.3784. So our entropy is dropping each time we do a split. And of course, our third split we look at, and we'll see that we're left with size again, and we split it with 4 and 2. In this case, if it's greater than 3, it's going to be a block. If it's less than 3, it's going to be a card. And at this point, each of our objects is looped into similarity, so they all look the same, and we end up with an entropy of 0. And so you can see as we go down, the entropy continues to get less. And because it hits 0, we can say all our objects are now classified with 100% accuracy. If it was only that easy to clean the kids' closets. And you can see we have a nice drawing that shows you where all the leaf nodes are in this, in which case we have the balls, the books, the blocks, and the cards are part of the leaf node. And the root node is our first split when we have all the objects and we're splitting them by rectangle by shape. So we're going to dive into the use case. And in this case, we're going to get a little morbid. There I am behind my desk. That's definitely not me. I don't have that big of a chin. But I do usually have a cup of coffee, and it looks kind of like that. It's sitting next to me on my desk. So the use case is going to be survival prediction in R. And let's implement a classification of data set based on information gain. This is going to use the ID3 algorithm. Don't let that scare you. That's the most common algorithm they use to calculate the decision tree. There's a couple different ways they can calculate the entropy, but the formula is all the same behind it. So ID3 is most common in R. And then we'll be using the RStudio for our interface, for our IDE. So the RStudio is free to download. There's the free version. Of course, there's an enterprise version, and there's all kinds of different choices in there. But one of the wonderful things about R is that it's been an open source for a very long time and is very well developed. And it's also very quick and easy to use on a lot of things. So this is going to be in the RStudio IDE. There's some other interfaces, but I would suggest using the RStudio. It's the most common one. And if I remember, I said this is going to be a little morbid because we're talking about how many people survived and died on these ships. So in this case, we have a nice vacation cruise ship going on there, or I'm not sure what that is with the tugboat. So we have a ship, and it had 20 lifeboats. The lifeboats were distributed based on the class, gender, and age of the passengers. We will develop a model that recognizes the relationship between these factors and predicts the survival of a passenger accordingly. So we want to predict whether the person is going to survive or die in a shipwreck. And we'll be using a data set which specifies if a passenger on a ship survived its wreck or not. So we're going to look at this data. And if you open it up into a spreadsheet, and don't forget you can always put a note on the YouTube video down below. And we will be monitoring that, and you can request the data set sent to you or more correspondence. You can also go to www.simplilearn.com and request this data set too. And it's just a simple CSV file we'll send out. And you can see right here we have survived. So 1 indicates a person survived the wreck. 0, they didn't make it. They were under the water. And the luxury class of the cabin, so if they were in, what value is like 1, 2, 3, depending on what luxury class they were. And then we have, this is kind of interesting, how many siblings they had. So it's kind of an interesting added statistic in there. Number of parents on board, and disembark location, so where the destination is. So here we've opened up RStudio. And if this is your first time in RStudio, you'll notice that it opens up standardly in 3 panes. The upper left is for text documents you're bringing in, and then the bottom left is the actual commands as they're processed. And then on the right-hand side, you have your environment set up on there. Now, I've zoomed in with my font a little oversized. In fact, we can even take that up one more size and see if we can get a larger setup view. Here we go. So I've set the font for 18, probably a lot larger than you need to work on a project. And the first thing I'm going to do is on the right-hand panel, we're going to be working with plots. So I'm going to click on the little plot tab up there. And I'm just going to collapse that over to the side for right now. And then I'm going to open up the bottom one. And you'll see on the top, I actually have 2 different tabs. Team in the back was really nice to set up the whole package for what we're working on here. And we'll go through this line by line, and then you'll see as we execute the different lines they're going to appear down below. So I'll be flipping between these two left panels. And let me go backwards just for a second here. We're going to do this part. So let's take a look at the installs. And if you look at the installs, and I'm not going to actually run the installs because I've already run them on my computer. So these are already installed in my R packages, and I don't have to rerun them. We have a number of packages we're bringing into R because that's how R functions. And the first number of packages are all part of our decision tree. So our F selector, our R part, our caret with the dependencies equal true, and our dplyr and our R part plot. Ooh, that's a mouthful. You'll need to import all of these in your setup. And the first one, which is your F selector, computes your chi-squared, your information gain, your entropy. All of those formulas are a part of the F selector. So when you bring it in, that's what that package is. The R part is your partitioning of your decision tree. So these are your primary two decision tree modules that we're bringing in. The caret is a part for actually splitting apart the data, because we always want to do a test set, a train set. So they built a package caret to kind of handle all those. You'll see caret used in a lot of other machine learning packages when you're doing the R. The dplyr is for mutating your data, so you can sum it, you can classify it, you can filter it. That's all part of the dplyr. And then our part has another piece called plot, and that's for helping us plot the data as we sort out the tree, because the R part creates the tree, but you still want to be able to plot it. And then we come down here and we have some additional tools. We're going to work with a spreadsheet. This is a Microsoft Access spreadsheet, so we're going to use the XLSX package to import it. And you might think that's a little outdated, because I know when I'm doing any new projects, I try to save my data into a comma-separated variable file or something more standardized. But a lot of times you'll end up with these old databases where they're exporting data, and their export comes in an Excel spreadsheet. And guess what? This is a time saver. Instead of opening up the spreadsheet, resaving it as a comma-separated variable file, you can just open it right up in R, which is really nice. And then we have our data tree, which goes right along with displaying the data. So we have our rpart.plot, and we're going to put that into the data tree so we have a nice visual. And finally, you need to install the package CA Tools. And CA Tools is another package used for general manipulation of your data and your vectors. So it also has a split function for training data. I know we have another package for that, but both those packages fit in there as far as the working with the data. So a lot of times you'll see these loaded in there together. And you'll see in a moment we'll import the elementary StatLearn package also, which is very generic, working with data setup as far as statistics and data processing. Now, because my Java setup is a little different because I use the developer package, well, the latest update of the developer package and the R are struggling to see each other. So I need to go ahead and add this in. Chances are you don't need to worry about this. But if you do get an R Java error, you'll need to go ahead and add in a line to set your environment. And I'm just going to set the Java home. I went ahead and looked up the last solid JRE folder, and you'll see under Program Files Java, you can look them all up to make sure it's the JRE and not the JDK. The difference between those is one is a standard executable, that's a JRE folder, it is a folder, not an actual file, and the JDK deals more with developer side on things. And I'm going to go ahead and run this, and if you're in R, you can run these lines individually by holding your control key down and hitting the enter button. So I've now loaded my workspace and set my environment here. And we can actually look and just make sure system.getEnvironment is the opposite one. And I can just look real quick and say, hey, what's my Java home set to? And if I run that, whoops, I forgot to put brackets around it. There we go. And if I do that, you'll see that it's set to the JDK 18025. And again, we're looking at the split screen, and let me just move this up here a little bit, and let me hit the enter key a bunch of times so it comes up on the screen. When I run it, and I'm running it line by line, the run text then appears down here, and this is what's actually being executed. So I could just as easily type it in down here as putting it up here on the top part. That's just a little bit of RStudio and working with RStudio. So I've shown you the installs. And again, I've already installed it on my computer, so it takes a minute or two to install it. we need to go ahead and then bring those libraries in to work with. So basically we're going through all the different libraries we're using. Elements.learn is a standard R library, so it should already be installed. You don't have to install that one. And I can just go right down them, and you'll see as I install them that they show up on the bottom. And every time you go to run a new setup, you need to go ahead and install these, pull the libraries in. You got to tell your R Studio these are the libraries you're using. And you can see right down here that as it executes them, it has all the different things. One of them had like a couple different parts to it, so it loaded the lattice and the ggplot2. Really nothing to worry too much unless you see errors down here. So if you start getting error codes, then you might have to go troubleshoot and find out why it's not installing correctly, or did it install correctly. But it's pretty straightforward. We've covered all the libraries. And again, if you want a copy of this code, simply add a comment down below on the YouTube video, or visit www.simplilearn.com and they'll be happy to send you a copy of the base code. The next step is we want to go ahead and load the Excel file after setting the working directory. So let's go ahead and set the working directory. SEWWD is a command for that in R. And then this is wherever you have downloaded your data to and your files to. A lot of times if you get the zipped framework sent to you, it will unzip all into one location. And then you got to look that location up and put that in here. A lot of times it automatically sets that for you if you're working in the same directory. In this case, you can see I've pasted in a very lengthy path because I have this as part of my documents, my business docs, and Simplilearn and marketing videos and so on. And I'll go ahead and do the Control Enter and run that. So now my working directory is set. And you can see down below it's executed this on the console down here. And if I open up that working directory, you can see I have a ship XLS file. That's the data we're going to look at. And we looked at that on the slide. You could also open this up, and I will want to go ahead and open it up with a notepad. By default, it'll open up as a spreadsheet. Oh, it is an Excel file, so I'd have to open it up as an actual spreadsheet. Wasn't thinking that one through. This is one of the problems with saving stuff as a proprietary ship file, even as something as widely used as Microsoft Excel spreadsheet. But when we open up the spreadsheet, you can see here the same data we looked at before. That's what's coming up in this file. And so I take this file, we can go ahead and let's create a variable. We'll call it add. And we're going to assign it. That's what the lesser than dash means if you've never used R before. And we're just going to assign it a ship XLS. And then I'll do my Control Enter and you'll see it run down here. Ship add is assigned ship.xls, or Excel spreadsheet on there. And then let's have another variable. We'll call it df for data frame. And we're going to assign this read XLSX. And that's from the library SLXX that we just imported. And we want to read the file add, because we just created that variable with the ship.xls. And I didn't catch this right away, but you'll see when we open it up in a spreadsheet, it might be hard to see in your video screen, it has the first sheet is called ship1. So this data is on the page ship1 in the Excel spreadsheet. And we got to make sure that we tell the reader to look for that. And so we can simply do that in our command line. Sheet name equals, and it was ship1 on there. So we go ahead and hit the Control Enter and run this line, and it brings it down below and executes it. It's now reading in that data from that spreadsheet. That's what's going on. And it takes it just a moment to go ahead and read it in. And then with any data processing, we need to select the meaningful columns for the prediction. So this is important that we sort through our data and set it correctly so that whatever we're feeding it into can read it correctly. We can do this with df. We're going to reassign it, and we're going to select, and from there we're going to select df as our main data frame going in, and then list the columns that we want. And if we look at the data, we have survived, we have a class, we have a name, sex and age, and then there's siblings and parents. We really don't want to know the name because we don't need the name to run this on here. And then we got to decide which one of these we want to work with. And the guys in the back played with the data a little bit, and they came up with the following columns. Survived, which we need definitely, because that's what we're actually trying to figure out is whether we're going to survive or not. What class which class of the boat they're riding in, whether first class, second class. Sex and age. And we went ahead and dropped the rest of them, at least for this example. And so I can go ahead and do my Control Enter, and you'll see it execute down below. And now DF equals these 3 columns, or 4 columns. Plus our answer is one of those. So I always think of it as 3 columns plus 1, but it is 4 columns. And then for the next step, we want to make sure the data is in the right format. So again, I'm going to reassign the DF, and we're going to mutate the data. And that means we're going to take each one of these columns, and we're going to let it know what kind of data that is. So our first one is we got to put the database in, or the data frame in there, DF. And then we want to go ahead and do survived equals a factor of survived. So this is a yes, no. It's letting us know that this is a 0 or a 1 on here. And then for the class and the age, those are as numeric. There's other ways to process class since it is a very restricted number on there, but for this we're just going to do it as a numeric value. Same thing with age. And you see we didn't do anything with sex. We're just going to leave that as male or female. And that's fine for this because it'll pick up on that when we run the decision tree. And we'll do our Control Enter. So now I've assigned the new DF, and you can see it comes down below as we run it on there. So this is now loaded, and DF now is a mutated data frame that we started with, and we've set it up with our specific columns we want to work with. In this case, survived, class, sex, and age. And we've formatted 3 of those columns to a new setup. So one of them is factor. That's what we use for survive, so it knows it's a 0 and 1. And then we switched class and age to make sure that it knows that those are numeric values. Now that we have our data formatted, we need to go ahead and split the data into a training and testing data set. And by now, if you've done any of our other machine learning tutorials, you know this is standard. You need to have your data that we train it with, and then you got to make sure it works on data that it hasn't trained on. So we'll go ahead and do the splitting. Let's take a look and see what that looks like. And when you're dealing with splitting the data, we're doing a little randomness. So we'll just go ahead and set the seed to 1, 2, 3. You can set that to whatever number you want. That's just setting the random variable seed. And we'll go ahead and hit enter on there. And to do this, we're going to create sample, and we're going to go equals sample.split. So we're splitting up the data. This is actually creating a whole new column, trues and falses. And it's all stored in sample. And we want our data frame, and we use a $sign to denote that we're going to be working with one of the different columns. A nice thing you can do in R. And it actually shows my survived. So DF survived. And then our split ratio, I wanted to add a period in there, which it doesn't have. Our split ratio is going to be equal to, and we'll do 0.70. So we're going to take 70% of the data of those that have survived, and we're going to just randomly select which one of those we're going to use for training and which one we're going to use for testing it out later. And we'll hit our enter and load that sample in there. And then we'll go ahead and create our train and our test data set. So I'm going to set train equal to, and this is where it kind of gets interesting because we're going to do subset, and then we're going to do a subset of our DF where sample, and then we're going to use equals, since this is a logic gate. So wherever it sets sample equal to true, we're going to use that line in DF. And this is, of course, R, so it's all capitalized for true. So here's our trained data frame we're creating. So when I execute this and it shows up down below, it goes up and says, hey, this sample created a whole bunch of trues and false. And we're going to take those trues and falses, and wherever we've created a true, which is 70% of the data randomly selected, that's what we're going to train the data with. And then we need our test set. and that's a subset, just the same thing we just did. And we need our data frame, and this is where the sample equals false. And again, when I hit Control Enter, it goes down this line of code and it runs it down here in our terminal window. So now we've nicely split our data up. We have our training data set and our test data set. And this is, of course, where we get to the point of what we're actually trying to do, which is create our decision tree. And we're going to do that by training the decision tree as a classifier. This always gets me. You spend all this work sorting through the data, reformatting it, in this case mutating it and filtering it, and creating a train set and a test set. And so we're going to go ahead and create our tree, and we're going to assign to it the R part. That's the module we imported. And for the R part, we need to go ahead and do what's called a survived, and this is kind of a little complicated to look at, so let's just take a quick look at this, and I'm going to go backward on it. The first part is we're importing the data, so data equals train. And then what we want to know is who survived. So the first part we put in here is the column we're looking for is survived. And you'll see that we have added the squiggly mark in the period because we're looking just for this prediction. We just want to know who survived on these boats for programming our decision tree. And I'll go ahead and hit Control Enter, and we've now created the tree. That tree with all those values is now in there. And if you remember from before, we've taken from when we did the closet full of clutter, we've done the same thing where we have our entropy, and that one line computes the entropy and the increase in information, and it brings the entropy down to 0. So it's the same thing, but instead of applying it here as we did visually to the closet, it's now applied it to the data on the ship. It's now looked at the survival of 0 or 1 based on female, male, what age they are, where the best split of the age is, and what class they were in. You can see we have first class. If we go down there, I think there's third, second. So I guess it's class 1, 2, and 3. But you can see that's how it split it up. So it's used these different variables to minimize the entropy and maximize the information gain. And that's all done in that one line of code. Boy, we worked on all that theory, and computer does it for you in one line of code. It's important to understand the theory behind it so you know what's happening. Because as they make changes to these, or if you add special settings on it, you have to know what they're doing. But in this case, you can see that once we get it formatted, the computer does all the heavy lifting for us. And it never ceases to amaze me just how advanced machine learning has become these days, and how easy it is for people to get into it and learn the basic setups and be able to compute your different machine learning models. Once we've computed our decision tree and we built it on there, we want to go ahead and start doing predictions with it. And what are we going to predict? Well, you remember that we created our data with the train and test. So we have our training data, which we programmed the tree for. Now we want to see what it does with the test data. So let's see what that looks like. And we can wrap that into tree.survived.predicted. We'll assign that to our prediction. And this is nice because we have the command predict from one of the modules, the rpart module that we brought in. And I can simply put in here that we're going to use the tree. We have our test data and type. And this happens to be classification or class. And this would also be if you were to distribute this tree, you could save the tree and send it someplace else to be used on new data. This would be the command line you would use to predict on here. Predict, you have your tree saved, you have whatever data you're putting through, and you let it know it's doing a classification on the tree. And we'll go ahead and run that. So now that's loaded up. And now that we've gone through, we've trained our tree, we've run a prediction on our test data. Remember, the tree had never seen the test data till now. So we've already built the tree and we're just testing it out. And to do that, we're going to use a confusion matrix for evaluating the model. And let's see what that looks like. And that is simply confusion matrix. So once we have the confusion matrix, which came in from our caret, we need to compare the two different pieces of data. And the first one's going to be the value we generated up here. We have tree.survived.predicted. So I'm just going to copy that and paste it down here. And then the second one is the tree. We're comparing that to Let's see, survived. And it's not the tree. It's easy to get confused sometimes when you're moving these things around. We're going to compare it to test, the test group of data, specifically the survived column. And let's go ahead and run this and see what that looks like. And so let's go ahead and scroll up a little bit here to where it first executed the confusion matrix. And the most important part of this is that we have our prediction and our reference. And so 0 means they didn't survive, 1 means they survived. We had our prediction on here versus the actual. And that's what these two columns mean. And so when you read this little chart, we have 0, 0. So both the prediction and the actual reference said we agreed on 218 values for people who did not survive. A little grim there for data. Remember I talking about this is morbid data, talking about death rates of people on boats. And it says that they both agreed on 93. So 93 of them where we predicted the value that they would survive, and the reference came up the same. Likewise, the predicted, where it predicted 1, and the reference said, no, these people didn't survive, well, our prediction got 25 wrong. And where it says they didn't survive, and they actually did, it got 57 wrong. And we can come on down with the confusion matrix, and we can look at the accuracy. It comes up with the 0.7913 or 95% CI. So yeah, you're looking at pretty high accuracy. Information ratio, p-value. When you get in statistics, the p-value is one of the things we look at. Remember that there are certain values, if it's over 0.95, it's considered highly valuable variable. 0.5 means maybe, anything less than that means it's probably not connected. You have to look up the p-value a little bit more on that. And then they just have more information down here, which you can go through and But the important part is that we have a very high accuracy. That's what we're looking at. This is a very accurate model. And again, always remember the domain you're working with. Certainly this is an example, and this is a good little piece of data you can play with. But if I was, say, betting money, and my accuracy came up as 79% or over 95% CI, I'd be like, yes, let's bet on that. That's a good bet. But if I was betting on a life or death situation, I might kind of rethink that a little bit if it's going to affect my life that way. You can also look at this as if you're trying to figure out where the boats go in this particular example and where to put the lifeboats. That's actually pretty good. Be able to say, hey, we can increase the chances of people surviving this accident by putting the lifeboats in the appropriate places. And then, this is always fun. Let's visualize the decision tree. One of the cool things you can do inside of R real easily. And if you remember, one of the modules we brought in has a rpart.plot. We're going to take that and we're going to dump that into the PRP for the tree. And we'll just go ahead and hit enter. And this is fun. Let me move this over so you can get a nice view. You can see how it actually split it up. And let me just rerun that again. Now that I expanded the right, you'll see right here where one of the biggest splits was whether the person was male or female. Didn't know that was probably one of the biggest breaks as far as lowering the entropy and increasing the information gain. And then once sex is male, it came down here and it said you're not going to survive. I guess the men were throwing themselves overboard on the boat. I don't know. Maybe they're being very gallant and letting the women and children survive, which is what I hope that means. So once you know that it's not a male and it's a female passenger, if you were in class 3 or above, you had a high chance of surviving. If you were less than class 3, class 1 or 2, then it was based on age. And so you can see where age was greater than 19. So anybody over 19 had a high chance of surviving. And then if they were, or less than 19, I'm sorry, if the age was a little confusing on that one. But if the age was one side of 19, they probably survived. If not, then it said, hey, if your age is less than 60, you probably survived. And if not, people who are older probably didn't make it out of the boat in time. So elderly have a much higher risk, which you would expect. You'd expect that to be the case, that elderly would have a hard time getting off into the lifeboats. And they would probably step aside for the younger generation. I know I would. So that might be more of a social norm statistic as opposed to a survival rate. Let's go ahead and put this back on over here and see what else we can do with this data. If you're working with the shareholders, it's good to have a lot of tools as far as how to display. They'll want to see this number here where you say, hey, this is what the confusion matrix looks like, and we got a 0.79 accuracy. That would be like the number one thing you would talk to the shareholders about. Other data scientists care about the p-value and the information rate and information like that, but this is really the core right here. This is how much data, and this also shows them how much data was looked at. So you can actually just add these numbers together and you can see how many different people were in this particular data set, or how many lines in the data set. But we go ahead and visualize the 2D decision boundary. So let's take a look at that. That's kind of fun. It's a little bit more complicated, so I'm not going to go into it in too much detail today. Now, the guys in the back put this code together for me, which is great. So I'm just going to paste that in, because like I said, we're not going to go into it in too much detail. I want to just show you that there's some other ways to display the data that is not just this nice little tree over here, which gives us a little bit more maybe view of what's going on. As you dig deeper into data, that becomes very important. It might not be something so simple where you can look at, in this case, 1, 2, 3, 4 nodes. So they have 4 major nodes that they split the data in. So when we're looking at this, we're going to go ahead and create a set test equal to test, comma, C241. We're just assigning color column to go with the data. Okay? That's what that is. And then we're going to take set and have it equal to test. And we'll do x1, and we're going to set that equal to minimum set of 1 minus 1, max set of 1 plus 1 by equals 0.01. They had to play with these numbers a little bit to get this to look right. So we're creating a sequence on here from the set we created, so our test set. And then x2 is also creating a sequence based on different values. And then we're going to put that all into a grid. So let's go ahead and run that through all the way down to the grid. And they'll make a little more sense when we add the column names to the grid, okay? So we'll set our test. We'll create our x1 sequence and our x2 sequence. Remember, a sequence is just like, in this case, starting with 0.1, it's like 0.01, 0.02, 0.03, 0.04. So we're going to create a grid with all these values separated by 0.01. So that's all we're doing right now. And let's go ahead and set that up. There's our grid. And then we want to go ahead and create some column names. And for our grid set, we're going to have our C class and age. So we're just doing the class and the age on here. Remember, we did sex also before, so it's just class and age on this chart that we're pulling out. And we're going to create a Y grid, and the Y grid is going to equal tree survived predicted. Okay, so here's our Y grid and our predicted values on there. Now we're actually going to do something. We're going to plot, and we're going to plot the Y grid. Oops, hold on, let me see what's in here. And let me go ahead and just run the plot. It's got to be the there we go. So let's take a look at this and see if we can make a little sense of this code and what's going on here, because there's a couple of things going on. What we've done is we've plotted a decision tree classification data set. We've done our plot, and we have our set. So our set's equal to our test data. And then we have our main. We went ahead and give it a name, decision tree. And then we have our xlab and our xlimit, and we've set those up as class, with our ylab equals age, and our xlimit equals range, x1 comma ylimit equals range of x2. And when you look over here, you can see that we have age on the left and class on the bottom. And so based on age and class, and so once we put in this nice graph here, we want to go ahead and add our contours and our points. So let's go ahead and run that, and I'm going to run all 3 of these so we can see all the colors come in on the graph. And this is actually going to take a little bit, because remember, you can make it go a little faster by changing a couple of the notes up here. When we did 0.01 from the min to max, by changing that to 0.1 or other values, you can actually, it'll run a little quicker. And we're going to create a nice little decision tree classification test set just to see what that looks like and how that data displays. Now, that was taking so long to run with 0.01, I went ahead and just did a 0.1. So instead of filling the whole page with different colors for a really pretty view, now I just have these different colored lines coming across. It gives us another model that we can show for whoever you're working with in this case, your shareholders of the company or the individuals who you're posting to the web for. And you can see where we have the green and the red, and we've set those up to identify from the decision who's going to make it and who's not based on age and class. Now, my favorite one on this, and I'm going to go back and just highlight this really quick, was, let me just rerun that, go back to PRP tree where we display the tree. And that's where we split it in part, because this information gives us some keys that we can then use in other models. So it's good to know that sometimes what you're taking comes out, and maybe you create a bucket for people under 19, between 19 and 60, and over 60, and different things like that, so you can actually put people in buckets in a class age split. Just a quick note on there. Again, lots of different things from which you can display the data, and you can see how we use the decision tree to figure out chances of somebody surviving based on their class and their age. What is a random forest? And welcome to Raphael's vineyard in, I don't even know how to pronounce that, in Alsace, France, the largest wine production region in the world. So they have centuries of wine production and data they've collected on how to make their grapes and grow them, and how to properly get the right grapes and ferment them. Like Raphael, winemakers around the world are facing a grave problem. So let's meet the man himself and try helping him out. What is a random forest? We're going to come back to the vineyard, but we're going to look at some other examples along the way too. Open up the door, and of course here comes Raphael. I'd probably look closer to Raphael than I do to the young lad with the beard. Hey Raphael, so tell us how it's going. Not as good as before. Not many people work in this profession anymore, so every stage of production has gone slower. If only we could somehow speed up the process. Well, lucky for you, I'm a machine learning engineer. How about we automate the quality prediction process for wine? Let me begin by telling you what machine learning and random forest is. Machine learning is the science of applying algorithms that allow a computer to predict the outcome without being explicitly programmed. Random forest is an ensemble machine learning algorithm. So we're bringing in different pieces and then putting those pieces together. It operates by building multiple decision trees. Remember I told you we don't want just a lone tree out there, we want a forest? They work for both classification. If you remember from part 1, we had our vendor with his broccoli and oranges. I think he also had carrots. And it also, the output given by the majority of its decision trees is the forest final output. So if you have a number of decision trees, you have 5 decision trees and 4 of them say it's broccoli, then it's probably broccoli. And you can also use it as a regression model. The output given by the majority of decision trees is a forest final output, just like you do in classification. You can also come up with actual values and numbers as a regression model. Could you explain how a random forest works in layman terms? It's always a good thing to explore the information on something a little bit easier to understand and see. Sure, let's consider the case of Sam, a high school student. This so reminds me of my own high school student who's just started his first year in college, asking all his friends. So Sam is confused on which course to take up. So he's trying to figure out what his next class is going to be at school. Should he take music lessons, dance lessons, math, science, maybe social studies? So he decides to ask a couple of his friends for suggestions. And Sam approaches Jane first. So he comes up to Jane and says, hey, which of these classes should I take? And Jane asks Sam a few questions based on which she can suggest. Theoretical? Do you like theory? No, he doesn't like the theory part. Calculative? Do you like calculative? He goes, yes, I like doing calculations. And so Jane, based on a couple questions, she has her little decision tree there going. She goes, mathematics sounds good. So Jane forms a decision tree based on Sam's response and gives her suggestion. And of course, this is based on Jane's views and her history and the data that she's collected over her years in high school. Next, Sam approaches Bella. Bella asks him, hey, do you like the field of science? And Sam goes, yes. And then Bella goes, do you like new in industry? You like new things coming up in industry? And Sam goes, yes. And Bella goes, you should, similar to Jane, Bella also forms a decision tree based on Sam's response and gives her suggestion and says, hey, how about artificial intelligence? Sam's like, oh, artificial intelligence. So Sam next asks Terry for his suggestion. And Sam goes, do you like scoring things? And he goes, yes. And he goes, do you like theoretical? And he goes, no. And he comes up and says, mathematics. So you have 2 people saying mathematics and 1 person suggesting artificial intelligence. Since 2 out of 3 friends suggested math, Sam decides to take mathematics. And there's a lot of subtleties in this example. It's actually a really good example. Some of the things we run into in data science is when we collect data, and we collect from different sources, we might have data from one source that measures one thing or one set of instruments. And we might have data from another source that measures something else. We saw that with each of his friends are measuring different things and asking different questions. That's a little bit beyond the scope of this particular tutorial. So let's go back to our wine cellar. So you see, more the number of decision trees, more accurate will be the prediction. Random forests have a number of applications in market already. If you've been watching any of our other tutorials, you'll see that these are very common. We have in banking, it can be used to predict fraudulent customers. It is used to analyze symptoms of patients and detecting the disease. In e-commerce, the recommendations are predicted based on customers' activity. Stock market trends can be analyzed to predict profit or loss. Most recently, I was watching a review on weather here in the United States and the data they pull in for that. And one of the top weather places actually uses 5 different models. Random Forest was one of them, I believe. They use 5 different models to predict the weather, and depending on what the models come up with and what's going on, some of the models do better than others. I thought that was really interesting. It's important to note. So when you see us repeat the same things over and over, and you're looking at the different machine learning tools, you realize that we use multiple tools to solve the same problem, and we can find the best one that fits for that particular situation. So let's see how that fits back in our wine production. To help speed up the process of wine production, we will automate the prediction of wine quality. Suppose our random forest builds 3 decision trees. We have the first decision tree, which is going to divide everything by chlorides, less than 0.08, and it's either yes or no, and then it's going to look at alcohol greater than 6, yes or no, quality equals high, quality not so good, and if the chlorides were greater than 0.08, quality equals low. So there's our first tree. And then our second tree is going to split it on sulfates less than 0.6, and pH less than 3.5. And again, we have it coming down here that if the pH is low and the sulfites are low, the quality equals high. If the pH is a little higher but the sulfides are low, it's not so good. And if the sulfides are greater than 0.6, we have a quality equal to low. And then we'll do a third decision tree. We'll split it based on pH, and we can see below how that tree looks like with our sugar less than 2.5. If not, it's a quality equals low. It's a real low quality. And if it is less than 2.5, then the pH decide whether it's going to be a quality high or not so good. And if we track one of our wines down the list, we'll look at it and we'll say, oh, 2 out of 3 decision trees indicate the quality of our wine to be high. The forest predicts the same. So this sounds promising. So let's go ahead and dive in and see what that actually looks like. So this is the data set that holds all the attribute values required to predict the wine's quality. And I'll pull this up in a spreadsheet in just a moment. But you can see here we have fixed acidity, volatile acidity, citric acid, all the way to quality. And then quality is like a 4, 5, 6, or 7, I believe. And this will be done in R. So let's go ahead and get started on our coding. We'll be using RStudio. Before we dive into RStudio, I always like to open up the data in the spreadsheet and look at the actual data that I have. And they've called it winequality-red.xls, so it's a spreadsheet, a Microsoft spreadsheet. And when we open it up, we'll see that it matches what we had before, as far as the slide was showing us. We have 12 different columns. The first 11 are our features, our fixed acidity, volatile acid, citric acid, things you always want to look at when you're looking at your data. And we've done this before in the part 1, but just a reminder, we want to note that we have decimal places here, float values, in a lot of these things, especially the first number of columns. Our free sulfur dioxide looks to be an integer, but it varies a lot. So we have, I see some values all the way up to 51, 7, 4. So we'd probably keep this as a linear model kind of thing. Same thing with the sulfur dioxides, densities again, decimal places, sulfides, alcohol. Quality. I want you to note in the quality that we only have a few qualities here. This isn't like a spread between 0 and 100. It looks to be 3, 4, 5, 6, and 7. And so when we start looking at the process, we can have the option of either doing this as a series of integers or float values going from 3 to 7, or we can convert that to a categorical, 3, 4, 5, 6, and 7 being the categories. But we'll look at that in the coding here in just a minute. And finally, you'd want to go ahead and scroll down through the data and just look for missing data or anything weird. Obviously, working with big data, you wouldn't be able to do that. If this was spread across numerous computers and you had millions of rows. We have, 1,687 rows here, so it's a nice size spreadsheet, still considered a small data set. Let's go ahead and switch over, and let's take a look at this in the R. So here we are in our R Studio, and if you remember, it comes up automatically in 3 panels. I have my font on fairly large to help out. The upper left panel is a file that's open. You can have multiple files and tabs open, as you can see on mine right now. I'll probably close most of those in just a minute. And this is where you can put in your commands. Then you can execute these commands by either clicking on the run box or Control-Enter is the hotkeys for that. And all that does is then puts that down in the console and executes that line of command. You could just paste these directly in the console. I've certainly been known to do that if I'm loading up some data and I just want to take a quick look at it in R because I'm doing the coding in something else. Or if I just want to do a quick explore before I dive in and figure out what needs to be done. That's one of the tricks you can do. And then on the right hand side, we have our environment, history connections. We mainly are going to just be sitting on plots, and I'm just going to minimize this for right now out of the way while we dive in. If you haven't yet, you do need to go ahead and install the package Random Forest. I'm not actually going to do that because I've already run that. We don't need to rerun that. But I am going to go ahead and import it into our project with the library and then Random Forest. And we'll do the Control-Enter. You can always hit the Run button up there too. And then now the library has been uploaded in there, and you can see down below it takes this and just copies it and pastes it down below and runs it in our console. And then just a quick troubleshooting thing. My Java happens to be the developer's Java. The latest release of the developer's Java from last week is clashing with my R and rerouting my Java files. So chances are you don't need to look this up or find out where your Java is. But there's a JRE folder. If you do have an error that comes up in the next library, you look that up. It's usually under Program Files, Java, and you'll see JDK, depending on what version you have on there, and then find that JRE folder. And I'm just going to set the environment on there. You have to do that every time you run the script. So with R, there is a place in R where you can set it permanently, but generally it's set to whatever your system variables are set to, so you don't want to mess with that. So you just want to put this in your code if you're having problems, and you can always take it out. And then we need to go ahead and bring in another library. And we're going to be importing the spreadsheet, so it's the XLSX, since it's a Microsoft spreadsheet. And I'll go ahead and run that. Now let's go ahead and create a variable path. We're going to assign to variable path the location of our folder. So this is a very lengthy one. You'll have to copy and paste it off your computer. My name is Richard, and you can see it's under C column users, Richard's documents, Docs Business, Simplilearn Marketing, Random Forest, and then the actual file, which is winequality-red.xls. So I put in the whole path in here. And you could also set the computer path to whatever folder you have it in, and then just use the name of the file. But I went ahead and did this because a lot of times it's good to be aware where your paths are going and where you're pulling your data from. And again, I went the Control-Enter, so you'll see that pushed the line down below and ran that line, so our path is now set. And then let's create a variable called data. And we'll assign that to a read. And we're going to be reading, let's see, where is it? There it is, on spreadsheet. And before I put in, we need the path. But we also need one more thing on the spreadsheet. Because it is an Excel spreadsheet, we need to know which page we're on. So let's go look that up. And in the spreadsheet, it might be a little hard to see because it's a very tiny font down there. But you'll see the page tabs on the bottom. This actually has 2 different pages, and we want page 1 for this project. So let's flip back over and put that in our code. And the term they use is sheet index. I always have to look that stuff up. And it was sheet index of 1. We'll go ahead and execute this. So at this point, we've now loaded the data into the variable data. And it's reading those in. I think there was a couple thousand rows of data in there, so it takes it just a moment to pull it in. Once I have my data in there, I always like to do something like this. Data, and I always forget in R it's head data, and we can run that, and you'll see it prints out what we looked at in the spreadsheet. So we have our fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur, all the different things. We're actually looking for quality, so you want to keep that in mind, that quality is the final setting. Is it a 3, 4, 5, 6? What is the quality on there? And the first thing we need to do is we're actually going to take the data quality, and let me see, quality, there it is. In R, the $ means that you're looking at one of the columns in here, or features as it is. So we see data $quality in R, that means that's what we're going to be editing. And what we want to do is we want to change the quality just a little bit. And so we're going to set it equal to. Now we're not assigning a variable, we're altering it. So data $quality equals, and we want to do as is one of the functions in R, and we're going to do as a factor. And then data quality, because that's what we're actually editing on there. And let's stop just for a second and look at this. Factor takes this and looks at the data as a categorically. So instead of it being on a continual scale of 0 to 100 or something like that, it actually looks at it as category of 5, category of 6, category of A, category of cat, category of dog. They're yes or no categories versus a continual. Now there's a lot of different things in here that we could do the same thing with, but all of these really are linear numbers, 7.4, 0.70, sulfur dioxide 3467. So we really don't need to mess with any of the other variables in there, but we do want to go ahead and set this up. And we'll come up here and we'll do our control enter, and it'll run it down below. And you'll see data quality equals as factor data quality. So we've now turned that into a factor, or into a categorical data. And so let me just bring this down a little bit. The guys in the back did the rest of this next piece of code. There are so many different ways, and if you have been looking at any of our tutorials, this should look kind of familiar. This is one way to do it. And you'll see we have our training data and our testing data. And so what we've done here is we have a data set size equals, and we're just going to do by the row. And so we want 0.8, or 80% of the data is going to be our training set to train our forest. And if you train a forest or any machine learning model, of course want to test it. So we're going to save 20% of the data for testing. And when you look at this, we have the index, which we set at 80%, comma, and then a negative index. So that's the remaining setup. So it goes from that index on. This is our notation for sorting out that data. And then we create the index, and we use the term sample. And this is just going to go in there and set our different samples for our in-row size, data set size, and everything. So we have an index now. So the data is indexed, and we're just going to pull off the first set of index and the end of the index for our data. And we can run all of this in one shot. We'll go into code, and we'll run selected lines. And so now we have our data in here. We have our training set and our testing set. That's what we wanted to get to. So once we've formatted all the data, then we get to the next real easy step, which is a single line to bring in our random forest. So let's go ahead and we'll use the variable rf, standing for random forest, and we're going to assign, if you remember correctly, we brought in our library random. If you wonder why I go up here all the time, it's because I'll forget which letters are capitalized in some of these because I switch between packages so much. But it's random with a capital F for forest, random forest. So the RF is going to equal random forest, and of course we start by telling it which column we're trying to predict. And of course you can always go down here and double check. We're running this on the quality. There we go, quality. And we're using just that column all the way to the end. And then we've added, our team in the back has gone in and played with this a little bit, and we'll go a little bit over what they did. But I'm going to put in the values that they have set for the different options in the random forest. Before I do that, it would help if I tell it what data to use. Data is going to equal our training set. And then we have the variables that they've put together, and let's just talk a little bit about what these different variables mean. So, mtry and ntry, these are some of the variables you play with the random forest. The mtry, not so much. When they first put it out, I think mtry was very common. 4 is a good value. I can't remember what the default is, but it's probably 3, 4, or 5 or something like that, depending. I think it depends on how many features you have going in there. So you could even just leave this as a default without too much troubles. The ntry, this is where it gets important, and I'm going to make this 2001. One of the suggestions is to always make this odd, like a tiebreaker, just in case. The default is like 500 or 501. And then finally we have importance equals true. I can't remember what it defaults to, but generally you want to set the importance equals to true. It actually looks at the correlation between the different features to make sure that there is some kind of correlation as it's doing its calculations. So our one line of code is going to assign our random forest and go ahead and train our random forest all in one execution. So this whole thing has been centered around getting to RF set to the random forest. And let's go ahead and execute this variable, or this line of code. And you'll see it takes a little bit down here to execute as it goes through and sets it up. And you'll see it probably takes a minute or so to execute the code, depending on the size of the data and how good your machine is. And then with all of our data, we can start looking at the answers. We'll just do RF, and we'll execute that. And you'll see that the random forest does a nice job. You can see right here it has our data equals training. It basically goes over everything we talked about. And you come down here and it has a confusion matrix, which is nice. We always like our confusion matrix when we're talking to our shareholders and explaining what the data comes out with and how it trains. And we can go ahead and plot our RF. Let's see what that looks like. And as the number of forests grows, remember we set it to 2001 forest, you can also see how the error comes in, how the different error on the different variables. This is kind of a nice graph that gives you an idea. It might help you adjust whether you really want to do 2,000 different forests. You might actually truncate this off at around maybe 800, because you notice the lines kind of continue on. Again, this is just still on the plot. And of course the next step is we need to go ahead and predict. Remember we split our data into 2 groups. So let's go ahead and get a result. We'll call it result, and we'll assign this one. There we go. We'll set this to a data frame. There we go, there's our data frame. And then, let's call this, we have our test quality, because that's what we're setting up on our test group with the quality on there. And then we want to have a predict, nice little keyword there to go ahead and run our random forest. And then we tell it that we're going to predict using our RF, our random forest, our testing group. 1 to 11 is what we're using. Type equals response. So let's go ahead and execute it. That's a mouthful on there. Somewhere I left out a comma in there, so it gave me an error. But you can see right here, we've set in there, now we have a result. And just real quick, we could do the head of the result, comma 5, and just take a look at the first 5 lines. And you'll see we have the actual value and what we predicted over here. And we could also just do all of the result and just see what that looks like. Oops. And print that out. And so it has all the different data we're going through on there. And finally, let's just go ahead and plot. There we go. We'll put plot up here, plot. And let's plot the result and just see what that looks like. Maybe not the best one to show to the shareholders, but it does give you an idea. On the left, on the y-axis, you'll see that it predicted 8. And this tells you that a lot of the 8 and the 8 scale was probably gave us about 50% came up there at 8. Really, maybe 50% it didn't guess right, but it did come up there and say that it was at least a 4, 5, or 6, even where it was considered an 8, and so on. You can see these different blocks coming in, so that if you line up the 3 with the 3, 4 with the 4, and you kind of cross-index them, a heat map would probably do better. But for this example, we'll just do a quick plot of the data. as far as how it works. And you can again see the results that we predicted over here, and you can look those over. Of course, back in the wine cellar, we're talking to our vineyard owner. And if you remember from before, we looked at this chart right here. The error rate is 29.05%. Therefore, our accuracy is 70.95%. If you're doing a vineyard, that's probably pretty good accuracy. And always check your domain when you're sharing this stuff, because if you're doing something that's life or death, maybe 70% accuracy might not be so good. But if you're looking at where you're going to distribute the bottles to for the wine and who's going to drink it, 70% accuracy is pretty good for that. That's probably a lot better than having no accuracy whatsoever and not even knowing what wine's going out to who. So we have automated the process of predicting the quality of wine. I myself prefer to predict it by sampling it. That's great, thank you. I'd like to visit this guy and sample his wine and find out just how good his different vineyards are. What is clustering? So we'll have a group of people here hanging out at a table or local coffee shop. I'm guessing coffee shop since they all have the same mugs. And one of them is trying to figure out what they're going to do. I have 20 places to cover in 4 days. I guess he's going traveling. That sounds fun. One of those breeze through Costa Rica or visiting the U.S. or going to Europe to go visit all the highlights. So he's got 20 places he wants to go, and he wants to hit them in 4 days. Very ambitious. And how will I manage to cover all of them? That's the question that he's coming up. How am I going to get to all these different places in the short time I have? Maybe he's a sales team, so he has 20 places he's got to do demos for. You can make use of clustering by grouping the places into 4 clusters. Each of these clusters will have places which are close by. So we're going to cluster them together by what is closest to the other one. Then each day you can visit one cluster and cover all the places in the cluster. Great! That's a great idea. If you're going to hit 4 different places, maybe you're going to cluster whatever streets are closest together so you don't have to travel, spend all your time traveling. The method of dividing the objects into clusters, which are similar between them and are dissimilar to the objects belonging to another cluster. So this is a formal definition of clustering. And we have here what we call hierarchical clustering and partial clustering. And we're going to go more into detail on hierarchical clustering, and you'll see the difference between the two, where partial clustering doesn't have the descending graph. It just has groups of things. And under hierarchical clustering, we're going to go over agglomerative and divisive. And you can think of agglomerative of bringing things together and divisive as dividing them apart. And then partial clustering, the 2 most common ones are k-means. That's probably the most common used for partial clustering. And there's also fuzzy c-means. And there's other ways of clustering and other algorithms out there. But these are the 2 big ones, k-means really being the most common one used. But we're not going to dig too deep into partial clustering because we're studying hierarchical clustering today. So what is clustering? Well, the applications of clustering are pretty numerous. We have things like customer segmentation, what people kind of belong together, how do we group them together? We have social network analysis. So social networks, we might look at sentiments. What group of people like something? What group of people don't like something? And then we can use that sentiments to suggest new sales for them. This whole group is into Harley-Davidson motorcycles, so we cater to them to sell them Harley-Davidson motorcycle parts. And we find out that people in that group also like leather jackets, they also like motorcycle boots, and they like bandanas. My brother's into Harley-Davidson, so that's why I picked that kind of funny example. But you can kind of see we look for similarities between these people, and then we group them together accordingly. And that's a good sentimental clustering is very common in so many things today, where we want to know the sentiments on stocks. Who is interested in stocks, who's not. Sentimental analysis, we talked about customer segmentation and sales. Well, we want to know what kind of sentimental view people have on different restaurants if we're going to open up a new restaurant or a new putting stores in. And of course, city planning. A lot of this I just kind of aimed at the city planning side. City planning is big with clustering. We want to cluster things together so that they work. We don't want to put an industrial zone in the middle of somebody's neighborhood where they're not going to enjoy it, or have a commercial zone right in the middle of the industrial zone where no one's going to want to go next to a factory to go eat a high-end meal or dinner. So it's very big in city planning. And it's also very big in just pre-processing data into other models. So when we're exploring data, being able to cluster things together, reveal things in the data we never thought about. And then once we have it clustered, we can put that into another model to help us figure out what it is we want for our solution. So let's go a little deeper into hierarchical clustering. Let's consider we have a set of cars and we have a group similar. We want to group similar ones together. So below we have, you'll see 4 different cars down there. And we get 2 clusters of car types, sedan and SUV. So if you're just looking at it, you can probably think, oh yeah, we'll put the sedans together and the SUVs together. And then at last we can group everything into one cluster. So we just have just cars. So you can see as we have this, we make a nice little tree. This is very common when you see anybody talks about hierarchical clustering. This is usually what you see and what comes out of it. We terminate when we are left with only one cluster. So we have, as you can see, we bring them all together. We have one cluster. We can't bring it together anymore because they're all together. Hierarchical clustering is separating data into different groups based on some measure of similarity. So we have to find a way to measure what makes them alike and what makes them different. Agglomerative clustering is known as a bottom-up approach. Remember I said think of that as bringing things together. You see, I think the Latin term agglo is together because you have your agglomerate rocks where all the different pieces of rocks are in there. So we want to bring everything together. That's a bottom-up. And then divisive is we're going to go from the top down. So we take one huge cluster and we start dividing it up into 2 clusters, into 3, 4, 5, and so on. Digging even deeper into how hierarchical clustering works, let's consider we have a few points on a plane. So this plane is 2D, so we have an XY coordinates, kind of makes it easy. We're going to start with measure the distance. So we want to figure a way to compute the distance between each point. Each data point is a cluster of its own. Remember, if we're going from the bottom up, agglomerative, then we have each point being its own cluster. We try to find the least distance between 2 data points to form a cluster. And then once we find those with the least distance between them, we start grouping them together. So we start forming clusters of multiple points. This is represented in a tree-like structure called dendrogram. So there's another key word, dendrogram. And you can see it's just the branch that we've looked at before. And we do the second group the same. So it gets its own dendrogram. And the third gets its own dendrogram. And then we might group 2 groups together. So now those 2 groups are all under one dendrogram because they're closer together than the P1 and P2. And then we terminate when we are left with one cluster. So we finally bring it all together. You can see on the right how we've come up all the way up to the top. Whoops. And we have the gray hierarchical box coming in there and connecting them. So we have just one cluster, and that's a good place to terminate because there is no way we can bring them together any further. So how do we measure the distance between the data points? I mean, this is really where it starts getting interesting. Up until now, you can kind of eyeball it and say, hey, these look together. But when you have thousands of data points, how are we going to measure those distances? And there is a lot of ways to get the distance measure. So let's go ahead and take a look at that. Distance measures will determine the similarity between 2 elements, and it will influence the shape of the clusters. And we have Euclidean distance measure. We have squared Euclidean distance measure, which is almost the same thing but with less computations. And we have the Manhattan distance measure, which will give you slightly different results. And we have the cosine distance measure, which again is very similar to the Euclidean, playing with triangles. And sometimes it can compute faster depending on what kind of data you're looking at. So let's start with the Euclidean distance measure. The most common is we want to know the distance between the 2 points. So if we have point P and point Q, the Euclidean distance is the ordinary straight line. It is the distance between the 2 points in Euclidean space. And you should recognize D equals, in this case, we're going to sum all the points. So if there was more than 1 point, we could figure out the distance to the not more than 1 points. This is the sum of more than 2 dimensions. So we can have the distance between each of the different dimensions squared, and that will give us, and then take the square root of that, and that gives us the actual distance between them. And they should look familiar from Euclidean geometry. Maybe you haven't played too much with multiple dimensions, so the summation symbol might not look familiar to you. But it's pretty straightforward as you add the distance between each of the 2 different points squared. So if your y difference was 2 minus 1 squared would be 2, and then you take the difference between the x, again squared, and if there was a z coordinates, it would be z1 minus z2 squared, and then take the square root of that and sum it all together, and then take the square root of it. So to make it compute faster, since the difference in distances, whether one is farther apart or closer together than the other, we can do what's called the squared Euclidean distance measurement. This is identical to the Euclidean measurement, but we don't take the square root at the end. There's no reason to. It certainly gives us the exact distance, but as far as doing calculations as to which one's bigger or smaller than the other one, it won't make a difference. So we'll just go with so we just get rid of that final square root. It computes faster, and it gives us pretty much the Euclidean squared distance on there. Now, the Manhattan distance measurement is a simple sum of horizontal and vertical components, or the distance between 2 points measured along axes at right angles. Now this is different because you're not looking at the direct line between them. And in certain cases, the individual distances measured will give you a better result. Now generally that's not true. Most times you go with the Euclidean squared method because that's very fast and easy to see. But the Manhattan distance is you measure just the y value and you take the absolute value of it. And you measure just the x difference and you take the absolute value of it and just the z. And if you had more, different dimensions in there, A, B, C, D, E, F, however many dimensions, you would just take the absolute value of the difference of those dimensions. And then we have the cosine distance. Similarity measures the angle between the two vectors. And as you can see, as the two vectors get further and further apart, the cosine distance gets larger. So it's another way to measure the distance. Very similar to the Euclidean, so you're still looking at the same kind of measurement, so it should have a similar result as the first two. But keep in mind the Manhattan will have a very different result, and you can end up with a bias with the Manhattan if your data is very skewed, if one set of values is very large and another set of values is very small. But that's a little bit beyond the scope of this. It's just important to know that about the Manhattan distance. So let's dig into the agglomerative clustering. And agglomerative clustering begins with each element as a separate cluster, and then we merge them into a larger cluster. How do we represent a cluster of more than 1 point? So we're going to kind of mix the distance together with the actual agglomerative and see what that looks like. And we're actually going to have 3 key questions that are going to be answered here. So how do we represent a cluster of more than 1 point? So we want to look at the math, what it looks like mathematically and geometrically. How do we determine the nearness of clusters? When to stop combining clusters? Always important to have your computer script or your whatever you're working on have a termination point so it's not going on eternally. We've all done that if you do any kind of computer programming or writing a script. Let's assume that we have 6 data points in a Euclidean space. So again, we're dealing with x, y, and z. In this case, just x and y. So how do we represent a cluster of more than 1 point? Let's take a look at that. And first we're going to make use of centroids. Very common terminology in a lot of machine learning languages when we're grouping things together. So we're going to make use of centroids, which is the average of its points. And you can see here we're going to take the 1, 2 and the 2, 1 and we're going to group them together because they're close. And if we were looking at all the points, we'd look for those that are closest and start with those. And we're going to take those two and we're going to compute a point in the middle. And we'll give that point 1.5, 1.5. And that's going to be the centroid of those 2 points. And next we start measuring like another group of points. We got 4, 1, 5, 0. When they're pretty close together. So we'll go ahead and set up a centroid of those 2 points. In this case it would be the 4.5 and 0.5 would be the measurements on those 2 points. And once we have the centroid of the 2 groups, we find out that the next closest point to a centroid is over on the left. And so we're going to take this and say, oh, 0, 0 is closest to the 1.5, 1.5 centroid. So let's go ahead and group that together. And we compute a new centroid based on those 3 points. So now we have a centroid of 1.1 or 1, 1. And then we also do this again with the last point, the 5, 3, and it computes into the first group. And you can see our dendrogram on the right is growing. So we have each of these points become connected and we start grouping them together. And finally we get a centroid of that group too. And then finally the last thing we want to do is combine the 2 groups by their centroids. And you can see here we end up with one large group and it'll have its own centroid, although usually they don't compute the last centroid, we just put them all together. So when do we stop combining clusters? Well, hopefully it's pretty obvious to you. In this case when they all got to be 1, but there are actually many approaches to it. So first, pick a number of clusters k up front. And this is done in the fact that we don't want to look at 200 in clusters. We only want to look at the top 5 clusters or something like that. So we decide the number of clusters required in the beginning and we terminate when we reach the value k. So if you looked back on our clustering, let me just go back a couple screens. You'll see how we clustered these all together, and we might want just the 2 clusters. And so we look at just the top 2. Or maybe we only want 3 clusters. And so we would compute which one of these has a wider spread to it or something like that. There's other computations to know how to connect them. And we'll look at that in just a minute. But to note that when we pick the K value, we want to limit the information that's coming in. So that can be very important, especially if you're feeding it into another algorithm that requires 3 values, or you set it to 4 values, and you need to know that value coming in. So we might take the clustering and say, okay, only 3 clusters. That's all we want for K. So the possible challenges, this only makes sense when we know the data well. So when you're clustering with K clusters, you might already know that domain and know that that makes sense. But if you're exploring brand new data, you might have no idea how many clusters you really need to explore that data with. Let's consider the value of K to be 2. So in this case, in our previous example, we stop when we are left with 2 clusters. And you can see here that this is where they came together the best while still keeping separate the data. The second approach is stop when the next merge would create a cluster with low cohesion. So we keep clustering till the next merge of clusters creates a bad cluster low cohesion setup on there. That means the point is so close to being between 2 clusters, it doesn't make sense to bring them together. But how is cohesion defined? Oh, let's dig a little deeper into cohesion. The diameter of a cluster. So we're looking at the actual diameter of our cluster, and the diameter is the maximum distance between any pair of points in the cluster. We terminate when the diameter of a new cluster exceeds the threshold. So as that diameter gets bigger and bigger, we don't want the 2 circles or clusters to overlap. And we have radius of a cluster. Radius is the maximum distance of a point from centroid. We terminate when the radius of a new cluster exceeds the threshold. Again, we don't want things to overlap, so when it crosses that threshold and is overlapping with other data, we stop. So let's look at divisive clustering. Remember, we went from the bottom up, now we want to go from the top down. Divisive clustering approach begins with a whole set and proceeds to divide it into smaller clusters. So we start with a single cluster composed of all the data points. We split it into different clusters. This can be done using monothetic divisive methods. What is a monothetic divisive method? And we'll go backwards and let's consider the example we took in the agglomerative clustering to understand this. So we consider a space with 6 points in it, just like we did before, same points we had before. And we name each point in the cluster. So we have, in this case, we just gave it a letter value, A, B, C, D, E, F. Since we follow top-down approach in divisive clustering, obtain all possible splits into 2 columns. So we want to know where you could split it here. And we could do like a AB split and a CDEF split. We could do BCE, ADF, and you can see this starts generating a huge amount of data. ABCDEF. And so for each split, we can compute cluster sum of squares. And we can see here actually have the formula out for us, BJ12 equals N1 of absolute value of x minus absolute value of x squared. So again, we're computing all the different distances in there squared, back to your kind of Euclidean distances on that. And so we can actually compute B of j between clusters 1 and 2. And we have the mean of the cluster and the grand mean, depending on the number of members in the cluster. And we select the cluster with the largest sum of squares. Let's assume that the sum of squared distance is largest for the third split we had up above, and that's where we split the ABC out. And if we split the ABC out, we're left with the DEF on the other side. We again find the sum of squared distances and split it into clusters. So we go from ABC, we might find that the A splits into BC and D into EF. And again, you start to see that hierarchical dendrogram coming down as we start splitting everything apart. And finally, we might have A splits in B and C, and then each one gets their own DEF. And it continues to divide until we get little nodes at the end and every data has its own point. Or until we get to K, if we have set a K value. So we've kind of learned a little bit about the background and some of the math in hierarchical clustering. Let's go ahead and dive into a demo. And our demo today is going to be, for the problem statement, we're going to look at U.S. oil. So a U.S. oil organization needs to know its sales in various states in U.S. and cluster the states based on the sales. So what are the steps involved in setting this problem up? So the steps we're going to look at, and this is really useful for just about any processing of data, although I believe we're going to be doing this in R today. We're going to import the data set. So we'll explore our data a little bit there. Create a scatter plot. It's always good to have a visual if you can. So once you have a visual, you can know if you're really far off in the model you choose to cluster the data in or how many splits you need. And then we're going to normalize the data. So we're going to fix the data up so it processes correctly. We'll talk more detail about normalization when we get there. And then calculate the Euclidean distance. And finally, we'll create our dendrogram so it looks nice and pretty, and we have something we can show to our shareholders so that they have something to go on and know why they gave us all that money in salary for the year. So we go ahead and open up R, and we're actually using R Studio, which is really it has some nice features in it. It automatically sets up the 3 windows where we have our script file on the upper left, and then we can execute that script and it'll come down and put it into the console bottom left and execute it. And then we have our plots off to the right, and I've got it zoomed in, hopefully not too large a font but large enough that you can see it. And let's just go ahead and take a look at some of the script going in here. It's clustering analysis, and we're going to we'll call it my data, and we're going to assign it in R. This is a symbol for assigning, and we're going to go read CSV. Read CSV file, and we'll put that in brackets. And before we go any further, let's just look at the data outside of R. It's always nice to do if you can. And the file is going to be called utilities.csv. This would also be the time to get the full path so you have the right path to your file. And remember that you can always post in the comments down below. And when you post down there, just let us know you want to connect up with Simplilearn so that they can get you this file. So you can get the same file we're working on and you can repeat it and see how this works. This is utilities.csv. It's a comma-separated variable file, so it's pretty straightforward. And you can see here they have the city, fixed charge, and a number of different features to the data. And so we have our ROR, cost, load, demand, cells, nuclear fuel cost on here. And then going down the other side, we have U.S. cities, Arizona, Boston. They have central U.S., so I guess they're grouping a number of areas together. The Commonwealth area, you can see down here, Nevada, New England, northern U.S., Oklahoma, the Pacific region, and so on. So we have a nice little chart of different data they brought in. And so I'm going to take that complete path that ends in the utilities.csv, and we're going to import that file. Let me just enlarge this all the way. Oops, I had an extra set of brackets here somehow. Or maybe I missed a set of brackets. This can happen if you're not careful. You can get brackets on one side and not the other, or in this case, I got double brackets on each side. There we go. And then the magic hotkeys in this case are your Control-Enter, which will let me go ahead and run the script. And so I've now loaded the data, and as you can see, I went ahead and shrunk the plot since we're going to be looking at the window down below. And we can simply convert the data to a string. Now, all of us do this automatically the first time. We say, hey, just print it all out as a string. And then we get this huge mess of stuff that doesn't make a whole lot of sense. So, and you can see here they have, you can probably kind of pull it together as looking at it. But let's go ahead and just do the head. And we'll do the head of my data. There we go. And Control-Enter on that. And the head shows the first 5 rows. You'll see this in a lot of different scripts. In R, you type in head, and then in brackets you put your data. And it comes through and lists the first 5 rows, as you can see below. And it shows Arizona, Boston, Central, and it has the same columns we just looked at. So we have the fixed charge, the ROR, the cost, the load, the D demand. I'm not an expert in oil, so I'm not even sure what D demand is. Cells, I'm guessing nuclear, how much of it's supplied by nuclear, and the actual fuel cost. And then the different states that it's in or different areas. And one of the wonders of R is all these cool, easy to use tools that are so quick. So we'll do pairs. And pairs creates a nice graph. So let me go ahead and run this. Whoops. The reason it gave me an error is because I forgot to resize it. So let me bring my plot way out so we can see it. And let's run that again. And you'll see here that we have a nice graph of the different data and how it plots together, how the different points kind of come together. This is neat because if you look at this, I would look at this and say, hey, this is a great candidate for some kind of clustering. And the reason is when I look at any 2 pairs, let's go down to, say, cells and fuel cost towards the bottom right. And when you look at them where they cross over, you sort of see things how they group together, but it's a little confusing. You can't really pinpoint how they group together. You could probably look at these two and say, yeah, there's pretty good commonalities there. And if you look at any of the other pairs, you'll start seeing some patterns there also. And so we really want to know what are the patterns on all of them put together, not just any two of them, but the whole setup. Let me go ahead and shrink my this down for just a second, just a notch here. And let's create a scatter plot. Oops. And this is simply just use the term plot in brackets, and then which values do we want to plot. And if we remember when we looked at the data earlier, let me just go back this way. In this case, let's go ahead and compare just two values to see how they look. And we'll do fuel cost and cells, and it's in my data. So we got to let her know which two columns we're looking at next to each other. And it will open up our plot thing and then go ahead and execute that. And we can see on those close up of what we were just looking at in the pairs. And if I was eyeballing this, I would say, oh look, there's a kind of a cluster up here of 5 items, and this one is hard to tell which cluster it'd be with, but maybe it's 6 to go in the top one, and you have a middle cluster and a bottom cluster, maybe 2 different clusters. So you can sort of group them together, fuel cost and the cells, and see how they connect with each other. And again, that's only 2 different values we're looking at. So in the long run, we want to look at all of them. And then the people in the back, they sent me the script so we can go ahead and add labels. So with my data text, fuel cost cells, the labels equals city, position 4. These are numbers you can kind of play with till they look nice. And oops, again, I forgot to resize my plot. It doesn't like having it too small. And we'll run that. I mistyped something in here. Oh, I did a lowercase d and they did a capital D. There we go. So now we can go in here and do this with my data. And you can see, a little hard to see on my screen with all the different things in there. It plots the actual cities. So we can now see where all the cities are in connection with, in this case, fuel cost and cells. So you have a nice label to go with the graph. And then we can also go ahead and plot, in this case, let's do, the ROR, oops. And we'll do that also with the cells, and do my data. Remember to leave it lowercase this time. So when we plot those two, we'll come over here, and it's gonna, I'm surprised it didn't give me an error. And then we'll also add in the with statement, so we put some nice labels in there. And it's going to be the same as before, except instead of doing the fuel cost cells, we want the R cells. And we'll execute that. Oops, and of course it gives me an error because I shrunk it down. So let's redo those two again. There we go. And we can see now we have the ROR with cells. And we'd probably get a slightly different clustering here if I was looking at these cities. They're probably different than what we had before. But you could probably look at this and say, these kind of go together and those kind of go together. But again, we're going to be looking at all of them instead of just 1 or 2. And so at this point, we want to dive into the next step. We're going to start looking at a little bit of coding or scripting here. This is very important because we're going to be looking at normalization. We put that in there, normalization. And if you've done any of the other machine learning skills and setup, this should start to look very normal in your pre-processing of data. Whether you're in R or Python or any of these scripts, we really want to make sure you normalize your data so it's not biased. Remember, we're dealing with distances, and if I have, let's say the ROR is, even look at this graph here on the right, you can see where my ROR varies between 8 and 14. That's a very small variable. And our cells varies between 4,000 and 16,000. So you can imagine the distance between 4,000 and 8,000, which is the distance of 4,000, versus 8 to 10 versus 2, the cells is going to dominate. So if we do any kind of special work on this, it's going to look at cells and it's going to cluster them just by the cells alone. And then ROR might have a little tiny effect of 2 versus 4,000. We want to level the playing field. Turns out there's actually a number of ways in script to normalize. So I'm just going to put in the code that they put together in the back for me. And let's talk about it a little bit. So we have Z, we're going to assign it to my data. And it's go ahead and we're going to do a little reshaping across all rows. Or across all columns. So each of the rows is going to have a little reshaping there. And then we're going to get M, which stands for means. And we're going to apply it to my data. So again, we want to go ahead and create the most common variable in there. And then S is going to be, SD stands for standard deviation. So instead of just doing, a lot of times what they do with normalization of data is we just reshape the data everything between 0 and 1. So that if the lower end is 8, that now becomes 0, and if the upper end is 14, that now becomes 1. That doesn't help if it is not a linear set of data. So with this, we're going to look for the means and the standard deviation for reshaping the data. And that way the most common values now become the kind of like the center point, and then the standard deviation is how big the spread. So we want the standard deviation to be equal amongst all of them. And then finally we go ahead and take Z, and with the Z we're going to reassign it, and we're going to scale the original my data, which we reshaped, based on M and based on the standard deviation. And the 2 in here, that just means we're looking at everything in kind of a XY kind of plot. And we can quickly run these. Control Enter, Control Enter, Control Enter, Control Enter. So now we have Z, which is a scaled version of my data. And now we can go ahead and calculate the Euclidean distance. Oops, calcu. There we go. And in R, this is so easy. Once you've gotten to here, we've done all that pre-data processing. We'll call it distance. And we'll assign this to dist. So dist is the computation for getting the Euclidean distance. And we can just put Z in there because we've already reformatted and scaled Z to fit what we want. Let me go ahead and just hit enter on that. And I'm going to widen my left-hand side again. I'm always curious, what does this data look like? So let's just type in distance, which will print the variable down below. Oops. You have to hit Control Enter. And this prints out a huge amount of information. As you can see, it just kind of streams down there. And let's go ahead and enlarge this. And I don't know about you, but when I look at something like this, it doesn't mean a whole lot to me, other than I see 2, 3, 4, 5, 6, and then you kind of have the top part, 6, 17, 18. So imagine this is like a huge chart, is what we're looking at. And we can go ahead and use print, distance, digits, equal 3. And let's run that. Oops, I keep forgetting that it has to go through the graph on the right. And we see a slightly different output in here. Let me just open this up so we can see what we're looking at. And by cutting down the distance, you can start to see the patterns here of it's looking at the different distances. So if I go to the top, we have the distance between 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, and then 2 and 3, and so on. Obviously, the distance between itself is 0, and it doesn't repeat the data, so we don't care to see 2 versus 1 again, because we already know the distance between 1 and 2. And so we have a nice view of all the distances in the chart, and that's what we're looking at right here. And it's a little easier to read. That's why we did the print statement up here to do digits equals 3. Make it a little bit smaller. We could even just do digits. Oh, let's just do 2. See what that looks like. We might lose some data on this one if something's way off. But we have a nice setup and we can see the different distances, and that's what we were computed here between each of the points. And then the whole reason we're doing this is to get ourselves a nice dendrogram going, a nice clustering dendrogram. We'll do a couple of these looking at different things. We'll take a variable hc.l and we're going to assign it h cluster and then distance. That easy. We've already computed the distances. So the H clustering does all the work for us. And let me hit enter on there. So now we have our HCL, which is assigned the H clustering computation based on distances and apart. And then I'm going to expand my graph because we would like to go ahead and see what this looks like. And we can simply plot that and hit the control enter so it runs. And look at that, we have a really nice clustering dendrogram. Except when I look at it, the first thing I notice is it really shows like numbers down below. Now, if you were a shareholder and some data scientist came up to you and said, look at this is what it means, you'd be looking at that going, what the heck does 3, 9, 14, 19, 1, 18 mean? So let's give it some words there. So let's do the same plot with our HCL. There we go. And let's add in labels. And this is just one of the commands in plots. So we have labels equals my data. And then under my data, we want to know the city. And we'll have it hang -1. That's just the instructions to make it pretty. So we'll run that. Oops, I accidentally ran just hang my 1. Let me try that again. There we go. Okay, so now you can see what it's done. And the hang my 1 turns it sideways. That way we can see central, which is central US and Kentucky. And we start to actually get some information off our clustering setup. And the information you start looking at is that when we put all the information together, you probably want to look at Central America and Kentucky together. Oklahoma and Texas has a lot of commonality, as does Arizona and southern US. And you could even group all 5 of those: Florida, Oklahoma, Texas, Arizona, and southern US. These regions, for some reason, share a lot of similarities. And so we want to start asking what those similarities are. But this gives us a place to look. It says, hey, these things really go together. You should be grouping these together as far as your cells and what you're doing. And then one of the things you might want to do is we can do the dendrogram average. And this changes how we do the clustering. So it looks very similar like we had before. And there's our HCL. We're going to assign it. We're going to do an H cluster. We're still doing it on distance. Oops, distance. And this time we're going to set the method to average. So we can change the methodology in which it computes the values. And before, if you remember correctly, we did median. Median's a little bit different than means. We did the most common one, and then we want the average of the median. And let's go ahead and run that. And then we can plot. And here's our HCL. Oops, there we go. Here's our HCL, and I can run that plot. And you can see that it's changed a little bit. So our way it computes and groups things looks a little different than it did before. And let's go ahead and put the cities back in there and do the hang. Control copy. Let me just real quickly copy that down here, because we want the same labels. And again, you can see Nevada, Idaho, Puget. I remember we were looking at southern US and Arizona, Texas and Oklahoma, Florida. So the grouping really hasn't changed too much. So we still have a very similar grouping. It's almost kind of flipped it as far as the distance based on average has. But this is something you could actually take to the shareholders and say, hey, look, these things are connected. And at which point you want to explore a little deeper as to why they're connected, because they're going to ask you, okay, how are they connected and why do we care? But that's a little bit beyond the actual scope of what we're working on today. But we are going to cover membership, what's called clustering membership on there. And let's create a member. We'll just call it member 1. Oops, there, member.1. And we're going to assign to this, we're going to do cut tree. And cut tree, it limits it. So what that means is I take my hc.l in here. Oops, there we go, .l. And so I'm taking the cluster I just built, and we want to take that cluster, and we want to limit it to just a depth of 3. So we go ahead and do that, and run that one. Oops, let me go run. There we go. So now I've created my member 1. And then, whoops, let me just move this out of the way. We're going to do an aggregate, and we're going to use Z, remember Z from above, and we're going to turn member 1 into a list, and then we're going to aggregate that together based on the mean. Let me go ahead and hit enter, run that. Oops, I did member L, it's actually member 1. There we go. And if we take a look at this, we now have our group 1 fixed charge and then all your different columns listed there. And most of them should come up kind of looking between 0 and 1, but you'll see a lot of variation because we're varying it based on the means. So it's the means and standard deviation, not just forcing it in between 0 and 1, which is a much better way usually to normalize your data than just doing the 0-1 setup. And finally, we can actually look at the actual values, and the same chart we just did. Oops. I made a mistake on there with my data. There we go. Okay. And again, we now have our actual data. Instead of looking at just if you looked up here, it's all between 0 and 1. And when we look down here, we now have some actual connections and how far distance this different data is. Again, because more of a domain issue and understanding the oil company and what these different values means. And you can look at these as being the distances between different items. So a little bit different view, and you have to really dig deep into this data. What we really want you to take away from this is the dendrogram and the charts that we did earlier. And that is the cluster output and our nice dendrogram. So this would be stage 1 in data analysis of the cells. Again, you'd have to have a lot more domain experience to find out what all the individual numbers we looked at mean and what the distance is and what's difference between Central America and Kentucky and why they're similar and why it groups all of Central Kentucky, Florida, Oklahoma, Texas, Arizona, and Southern U.S. together into one larger group. So that'd be way beyond the scope of this. But you can see how we start to explore data and we start to see things in here where things are grouped together in ways we might not have seen before. And this is a good start for understanding and giving advice for sales and marketing, maybe logistics, city development. There's all kinds of things that kind of come together in the hierarchical clustering as you begin to explore data. And we just want to point out that we get 3 clusters of regions with the highest cells, region with average cells, region with the lowest cells. Again, those are some of the things that they clustered it around, and you could actually see where things are going on or lacking. In this case, if you're the lowest cells, no one wants to be in the region of the lowest cells.
Support vector machine is a binary classifier, a supervised machine learning algorithm, and in this video we will learn what all that means. Machine learning algorithms come in 3 major flavors: supervised learning algorithms, unsupervised learning algorithms, and reinforcement learning. And today we'll cover classification under supervised learning. Supervised meaning the data set has known outcomes. If it were unsupervised, it would not have known outcomes, and we wouldn't have the categories or classes necessary for the machine to learn. But under supervised learning, we do have the known outcomes in the data set. And under supervised learning, there are 2 major types of machine learning algorithms: classification, which we'll cover today, support vector machine, and regression. Classification, you predict categories, and in regression, you generally predict values. So while we look at supervised learning, keep in mind that classification can really be considered multidimensional in the sense that sometimes you only have 2 classes, yes or no, true or false, and sometimes you have more than 2 classes. Sometimes you have, say, under risk management or risk modeling, low risk, medium risk, or high risk. And SVM is a binary classifier. It is a classifier used for those true, false, yes, no types of classification problems. And in supervised learning, features are important. If there are a lot of features, SVM may be the better classification algorithm choice, as opposed to, say, logistic regression. So with supervised learning, the computer is presented with example inputs and their desired outputs, those known outcomes. And the goal is to learn a general rule that maps inputs to those outputs. For example, bug detection, or customer churn, or stock price prediction. Not the value of the stock price, but whether or not it will rise or fall. And weather prediction, sunny, not sunny, rain, no rain. The classification algorithms generally take past data that we have those known outcomes, train the model, take new data once the model is trained, ingest it into the model, and create predictions. Is it a truck or is it a car? And keep in mind that I said features are important, and the number of features, whether or not those features are applicable to your problem, is a whole different discussion. But in some sense, you know, probably intuitively, that the color of a car really isn't indicative of whether or not it's a car or a truck, but the length of the vehicle, or the number of axles, or the weight, or the amount of seating may be more applicable to the algorithm and to training the model. So what is support vector machine? Support vector machine, or SVM, is a type of classification algorithm which classifies data based on its features. And SVM will classify any new element into one of those two classes. So we'll give it some inputs, the algorithm will segregate and classify the data, and then create the outputs. And next, when we ingest new data, an unknown fruit variable in this example, the algorithm will correctly classify the fruit, apple versus orange. So now let's understand what an SVM is. And if you want to understand support vector machine, you really need a good example. And I know that cricket is a wonderful game. I don't know a lot about it, but I know it's very popular around the world, and we're going to use cricket as an example of SVM. So we'll classify cricket players into batsmen or bowlers using the runs to wicket ratio. So a player with more runs would be considered a batsman, and a player with more wickets would be considered a bowler. And if we could take a data set, say of people, cricket players, with runs and wickets in columns next to their names, we could create a plot, a two-dimensional plot. In this example, clear separation between cricket players considered bowlers and those cricket players considered batsmen. And you don't always have a data set this clean where there is a clear segregation of data, bowlers versus batsmen. But for the sake of understanding SVM, this example does well. So before we do any separation, before we apply any high-level mathematics, let's just take a look at an unknown value, a new data coming into our data set. And that datum, we don't know what class it belongs to. That datum is a bowler or a batsman, we know that much, but we don't know, should we consider that cricket player a batsman or a bowler? And so we want to draw a decision boundary, some type of line separating the two classes, so that we can use that decision boundary to classify the new data point. Of course, we could draw lines. There's a yellow line, a green line, a blue line. There's actually not just 3 lines, but an infinite number of lines that we could draw between those two classes. So which one do we pick? And this is kind of reminiscent of simple linear regression, where we find the line of best fit. We want the line of best separation. We want a line that clearly separates those two groups as much as possible. Once we have the correct line, we would be able to classify the new data point. But in this example, you can see if we pick yellow, the new data point would be a bowler. But if we picked green or blue, the new data point would be a batsman. So we need the one that best separates the data. What line best separates the data? We'll find the best line by computing the maximum margin from equidistant support vectors. Now, support vectors in this context simply means the 2 points, one from each class, that are closest together, but that maximize the distance between them, or the margin. So the word vector here, you may think, well, he really means points, data points. Well, in 2-dimensional space, yes. And maybe even in 3-dimensional space. But once you get into higher dimensional spaces, when you get more and more features in your data set, you have to consider these as vectors. You can no longer really describe them as points, so we call them vectors. And the reason they're support vectors is because the 2 vectors that are closest together, that maximize the distance between the 2 groups, support the algorithm. So that's why we call them support vectors. So if you look at our example, there are a couple of points at the top that are pretty close to one another, and a couple of points at the bottom of that graph that are pretty close to each other. And I'm not really sure looking at the graph which two are closest, but clearly those points are the ones we need to consider. The rest of the other points are too far away from the rest of the other points. In other words, the bowler points are far to the right and the batsman data points are far to the left. So we'll look at these 4 points to begin with. Mathematically, we would calculate the distance among all of these points and we would minimize that distance. Once we pick the support vectors, we'll draw a dividing line and then measure the distance from each support vector to the line. The best line will always have the greatest margin or distance between the support vectors. If we consider the yellow line as a decision boundary, the player with the new data point would be considered a bowler. The margins don't appear to be maximum though, so maybe we can come up with a better line. So let's take 2 other support vectors and we'll draw the decision boundary between those, and then we will calculate the margin. And notice now that the unknown data point, the new value, would be considered a batsman. We would continue doing this, and obviously a computer does it much quicker than a human being, over and over and over again until we found the correct decision boundary with the greatest margin. And in this case, if you look at the green decision boundary, the green line appears to have the maximum margin compared to the other two. And so let's consider this the boundary of greatest margin, and now classify our unknown data value, and now clearly it belongs in the batsman's class. The green line divides the data perfectly because it has the greatest margin or the maximum margin between the support vectors. And now we can have confidence in our classification that the new data point is indeed a batsman. Technically, this dividing line is called a hyperplane. And the reason it's called a hyperplane will become a little bit more evident in a few minutes. Generally, in 2-dimensional space, we consider those lines. But in 3-dimensional space and higher dimensional spaces, they're considered planes or hyperplanes. So we always tend to refer to them as hyperplanes. And the hyperplane that has the maximum distance from the support vectors is the one we want. So, sometimes called the positive hyperplane, D plus is the shortest distance to the closest positive point, and D minus, sometimes called the negative hyperplane, is the shortest distance to the closest negative point. And the sum of D positive and D negative is called the distance margin. So if you calculate those two distances and add them up, that's the distance margin. And we always want to maximize that. If we don't maximize it, we can have a misclassification. And you can see the yellow margin is much smaller than the green margin. So this problem set is 2-dimensional because the classification is only between 2 classes. And so we would call this a linear SVM. Now we're going to take a look at kernel SVM. And if you notice in this picture, this is a great depiction of a plane, not a line. This is 3-dimensional space. So that's the plane that separates those 2 classes. So what if our 2-dimensional data looks like this? What if there's no clear linear separation between the 2 classes? In machine learning parlance, we would say that these are not linearly separable. How could we get support vector machine to work on data that looks like this? Since we can't separate it into 2 classes using a line, what we're going to do, and clearly there's no line, convince yourself, there's no line that goes and separates those 2 classes. So what we would do is we would apply some type of transformation to a higher dimension. We would apply a function called a kernel function to the data set such that the data set would be transformed into a higher dimension, a dimension high enough where we could clearly separate the 2 groups, the 2 classes, in this case with a plane, much the same way you saw the picture a few slides ago where the plane was separating the 2 classes. Here we clearly could draw some planes between the green dots and the red dots. And of course, we could draw an infinite number of planes separating those 2 classes, but we would draw the one that would maximize the margin. So if we let R be the number of dimensions, then the kernel function would convert a given 2-dimensional space to a 3-dimensional space. And as I said, once the data is separated in 3 dimensions, we can apply SVM, and separate the two groups using a two-dimensional plane. And this is analogous in the higher dimensions. And that last picture on the right-hand side would be some type of depiction of a higher dimension hyperplane. And there are more than one type of kernel function. There's Gaussian RBF kernel, sigmoid kernel, polynomial kernel, depending on the dimension and how you want to transform the data. There are more than one choice for kernel functions. So now let's go through a use case. Let's take a look at horses and mules and see if we can use SVM to classify some new data. So the problem statement is classifying horses and mules, and we're going to use height and weight as the two features. And obviously, horses and mules typically, in general, tend to weigh differently and tend to stand taller. So we'll take a data set, we'll import the data set, we'll make sure we have our libraries. The E1071 library has support vector machine algorithms built in. We'll compute the support vectors using the library. Once the data is used to train the algorithm, we'll plot the hyperplane, get a visual sense of how the data is separated, and if it's two-dimensional or three-dimensional, that's great. Remember, if it's higher dimensional, it's tough to plot those. And then we'll use the new model, the trained model, to classify new values. In general, we would have a training set, a test set, and then ingest the new data. But for our example, we're just going to use the whole data set to train the algorithm and then see how it performs. And once we see how it performs, we'll see, did we get a horse? Did we predict a horse when we had a horse? Did we predict a mule when we had a mule? So here's the R code. Of course, if you want to run this R code, you'll have to install R and then R Studio. Then you'll have to ingest the data, and then you'll have to create an indicator variable to help us with our plots. We'll install our libraries, install the package if you don't already have it installed. I do. And then call the library up into the R session that you're working. We'll create the data frame from the data that was ingested. We will then view the data frame, and of course we have to explore the data frame hoping that we don't have missing values or we don't have outliers. If we do have missing values or outliers, we'll have to either impute those values or delete those values. But in this case, let's hope we don't have any. And now for a quick demo on support vector machines. So we have a working directory where my data is stored, and I'm going to set the working directory to that data source and read the data file into R. And now I'm going to create a vector that really is just an indicator variable. It's the -1s and the 1s that indicate whether it's a mule or a horse, -1 for mule, +1 for a horse. So I'll create that vector. And SVM, there's a great package, E1071, great library that has the support vector machine functions that we're going to use. And now I'm going to create the data frame. I'm going to take my data and I'm going to add to it the isHorse vector. And now let's just take a peek, and as you can see, there's the height, weight, and whether or not the animal was a mule or a horse. So remember, machine learning, we take a data source with known outcomes, and we apply our algorithm to that data source, in this case a data frame of heights, weights, and the indicator variable. And then we use the machine learning algorithm to learn from that data with those known results. So now let's plot the data, the height versus weight. And as you can see, the horses tend to be a lot taller and weigh a lot more than the mules. So now let's run our algorithm, our SVM model against the data. And the key here is that it's a linear model, and we've run it, and great, now we have a model. Let's look at the summary of the model, and as you can see, there's the formula that it ran and some of the information about the vectors and the classes. And there are two support vectors. So now let's find those two support vectors on our graph. And this might be a little hard to see. The orange outline around this point and this point indicate that those are the two vectors that will support this model. And thus we call them the support vectors. Now let's get the parameters of the hyperplane from the model, and let's plot a line that will be our hyperplane. There's our hyperplane line, and therefore to the left and below are mules, and to the right and above are horses above that line. Let's take a few new observations, and I've encoded these so that it would be illustrative. We'll take these new observations and we'll plot them And I'm going to generate a new plot, red being the horses, black dots being the mules. I'll create an X and Y axis. I'm going to plot 3 dots, and you can see one of them, the green dot, the first one, kind of falls near the mules. The blue one kind of falls near the horses. And visually, we might conclude, hey, one's a mule, one's a horse. But what about the orange dot? Well, for the orange dot, we really need our hyperplane. We really need something to clearly indicate which side it's on. And of course, by looking at this data visualization, you can tell that the orange dot is probably a mule. And let's verify those results by sticking those observations into our model and predict some outcomes. And down below, you can see that for the 3 data points, 1, 2, and 3, the first one, the green one, was -1. That's a mule. The second one was a +1. That's blue. That's the blue point, which was a horse. And the third one, which we weren't sure about, but clearly the SVM model correctly predicted that that third point would be a -1, would be a mule. And we can visually see that by the hyperplane on the graph. So that's a quick example of SVM. In general, support vector machines are binary classifiers. We don't use them for higher level classification. If you had 3 or more classes, you might want to use something like random forest. What applications? You can use it for face detection, text categorization, image classification, and bioinformatics. Really anywhere that you have the need to classify things into 2 groups.
Today we're going to cover the K nearest neighbors, a lot referred to as KNN. And KNN is really a fundamental place to start in the machine learning. It's a basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor K? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, the use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values. Our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those 2 characteristics. Now tell me if it is a cat or a dog. An odd question. Usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or it's not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about k in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose k? How do we know k equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor k? KNN algorithm is based on feature similarity. Choosing the right value of k is a process called parameter tuning and is important for better accuracy. So at k equals 3, we can classify, we have a question mark in the middle, as either a square or not. Is it a square, or is it, in this case, a triangle? And so if we set k equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put k equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the k changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of k? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right k? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of k, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your k is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing k, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your k value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the k value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where you might get into a gig of data if it's really clean, it doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the 3 closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know, if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. You know, at 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import numpy as NP. Pandas is the pandas data frame, and numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results, so we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this, so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put it in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, the dataset 1 head, dataset 2 head, it only prints out the last one. So I always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those, you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do it direct. There's also one that you look for your NAN. A lot of different options in here. But the NAN, numpy NAN is what that stands for, is doesn't exist. So the first thing we're doing here is we're replacing the 0 with a numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column dot mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NAN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way you can still use the rest of those values to do your computation, and it kind of just brings that particular value, those missing values, out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you wanted to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle, because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set, we want to look at the I location, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there, but the actual running of our KNN, we need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our X train equals sc_x dot fit transform. So we're creating the scaler on the X train variable, and then our X test, we're also going to transform it. So we've trained and transformed the X train, and then the X test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replaced that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using k-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. That's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the k-neighbors classifier. In neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2 because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean is the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score, and finally accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the two values we're going to put in there. And let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED, predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column, and it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
Introducing Naive Bayes Classifier. Have you ever wondered how your mail provider implements spam filtering, or how online news channels perform news text classification, or how companies perform sentimental analysis of their audience on social media? All of this and more is done through a machine learning algorithm called Naive Bayes Classifier. We'll start with what is Naive Bayes, a basic overview of how it works. We'll get into Naive Bayes and machine learning, where it fits in with our other machine learning tools. Why do we need Naive Bayes? And understanding Naive Bayes Classifier, a much more in-depth of how the math works in the background. Finally, we'll get into the advantages of the Naive Bayes Classifier in the machine learning setup. And then we'll roll up our sleeves and do my favorite part. We'll actually do some Python coding and do some text classification using the Naive Bayes. What is Naive Bayes? Let's start with a basic introduction to the Bayes theorem, named after Thomas Bayes from the 1700s, who first coined this in the Western literature. Naive Bayes classifier works on the principle of conditional probability as given by the Bayes theorem. Before we move ahead, let us go through some of the simple concepts in the probability that we will be using. Let us consider the following example of tossing two coins. Here we have two quarters, and if we look at all the different possibilities of what they can come up as, we get that they could come up as head-heads, they can come up as head-tail, tail-head, and tail-tail. When doing the math, math on probability, we usually denote probability as a P, a capital P. So the probability of getting 2 heads equals 1/4. You can see on our data set we have 2 heads, and this occurs once out of the 4 possibilities. And then the probability of at least 1 tail occurs 3/4 of the time. You'll see on 3 of the coin tosses we have tails in them, and out of 4 that's 3/4. And then the probability of the second coin being head given the first coin is tail is 1/2, and the probability of getting 2 heads given the first coin is a head is 1/2. We'll demonstrate that in just a minute and show you how that math works. Now when we're doing it with 2 coins it's easy to see, but when you have something more complex you can see where these formulas really come in and work. So the Bayes theorem gives us the conditional probability of an event A given another event B has occurred. In this case the first coin toss will be B and the second coin toss A. This can be confusing because we've actually reversed the order of them and go from B to A instead of A to B. You'll see this a lot when you work in probabilities. The reason is we're looking for event A. We want to know what that is. So we're going to label that A since that's our focus. And then given another event B has occurred. In the Bayes theorem, as you can see on the left, the probability of A occurring given B has occurred equals the probability of B occurring given A has occurred times the probability of A over the probability of B. This simple formula can be moved around just like any algebra formula. And we could do the probability of A after a given B times probability of B equals the probability of B given A times probability of A. You can easily move that around and multiply it and divide it out. Let us apply Bayes' theorem to our example. Here we have our 2 quarters, and we'll notice that the first 2 probabilities of getting 2 heads and at least 1 tail we compute directly off the data. So you can easily see that we have one example, HH, out of 4, 1/4, and we have 3 with tails in them, giving us 3/4 or 3/4, 75%. The second condition, the second set, 3 and 4, we're going to explore a little bit more in detail. Now we stick to a simple example with 2 coins because you can easily understand the math. The probability of throwing a tail doesn't matter what comes before it, and the same with the heads. So it's still going to be 50% or 1/2. But when that probability gets more complicated, let's say you have a D6 dice or some other instance, then this formula really comes in handy. But let's stick to the simple example for now. In this sample space, let A be the event that the second coin is head and B be the event that the first coin is tails. Again, we reversed it because we want to know what the second event's going to be, so we're going to be focusing on A. And we write that out as the probability of A given B. And we know this from our formula that equals the probability of B given A times the probability of A over the probability of B. And when we plug that in, we plug in the probability of the first coin being tails given the second coin is heads, and the probability of the second coin being heads given the first coin being over the probability of the first coin being tails. When we plug that data in, and we have the probability of the first coin being tails given the second coin is heads times the probability of the second coin being heads over the probability of the first coin being tails. You can see it's a simple formula to calculate. We have 1/2 times 1/2 over 1/2, or 1/2 equals 0.5, or 1/4. So the Bayes theorem basically calculates the conditional probability of the occurrence of an event based on prior knowledge of conditions that might be related to the event. We will explore this in detail when we take up an example of online shopping further in this tutorial. Understanding naive Bayes and machine learning. Like with any of our other machine learning tools, it's important to understand where the naive Bayes fits in the hierarchy. So under the machine learning, we have supervised learning, and there is other things like unsupervised learning. There's also reward system. This falls under the supervised learning. And then under the supervised learning, there's classification. There's also regression, but we're going to be in the classification side. And then under classification is your naive Bayes. Let's go ahead and glance into where is naive Bayes used. Let's look at some of the use scenarios for it. As a classifier, we use it in face recognition. Is this Cindy or is it not Cindy or whoever? Or it might be used to identify parts of the face that they then feed into another part of the face recognition program. This is the eye, this is the nose, this is the mouth. Weather prediction, is it going to be rainy or sunny? Medical recognition, news prediction. It's also used in medical diagnosis. We might diagnose somebody as either as high risk or not as high risk for cancer or heart disease or other ailments. And news classification. When you look at the Google News and it says, well, is this political or is this world news? Or a lot of that's all done with the naive Bayes. Understanding naive Bayes classifier. Now, we already went through a basic understanding with the coins and the two heads and two tails and head, tail heads, etc. We're going to do just a quick review on that and remind you that the naive Bayes classifier is based on the Bayes theorem, which gives a conditional probability of event A given event B. And that's where the probability of A given B equals the probability of B given A times probability of A over probability of B. Remember, this is an algebraic function, so we can move these different entities around. We can multiply by the probability of B, so it goes to the left-hand side, and then we could divide by the probability of A given B, and just as easily come up with a new formula for the probability of B. To me, staring at these algebraic functions kind of gives me a slight headache. It's a lot better to see if we can actually understand how this data fits together in a table. And let's go ahead and start applying it to some actual data so you can see what that looks like. So we're going to start with the shopping demo problem statement. And remember, we're going to solve this first in table form so you can see what the math looks like, and then we're going to solve it in Python. And in here we want to predict whether the person will purchase a product. Are they going to buy or don't buy? Very important if you're running a business, you want to know how to maximize your profits, or at least maximize the purchase of the people coming into your store. And we're going to look at a specific combination of different variables. In this case, we're going to look at the day, the discount, and the free delivery. And you can see here under the day, we want to know whether it's on the weekday. You know, somebody's working, they come in after work, or maybe they don't work. Weekend, you can see the bright colors coming down there, celebrating not being in work, or holiday. And did we offer a discount that day? Yes or no? Did we offer free delivery that day? Yes or no? And from this, we want to know whether the person's going to buy based on these traits so we can maximize them and find out the best system for getting somebody to come in and purchase our goods and products from our store. Now, having a nice visual is great, but we do need to dig into the data. So let's go ahead and take a look at the data set. We have a small sample data set of 30 rows. We're showing you the first 15 of those rows for this demo. Now, the actual data file you can request. Just type in below under the comments on the YouTube video, and we'll send you some more information and send you that file. As you can see here, the file is very simple, columns and rows. We have the day, the discount, the free delivery, and did the person purchase or not. And then we have under the day whether it was a weekday, a holiday, was it the weekend. This is a pretty simple set of data, and long before computers, people used to look at this data and calculate this all by hand. So let's go ahead and walk through this and see what that looks like when we put that into tables. Also note, in today's world, we're not usually looking at 3 different variables in 30 rows. Nowadays, because we're able to collect data so much, we're usually looking at 27, 30 variables across hundreds of rows. The first thing we want to do is we're going to take this data and based on the data set containing our 3 inputs, day, discount, and free delivery, we're going to go ahead and populate that to frequency tables for each attribute. So we want to know if they had a discount, how many people buy and did not buy. Did they have a discount, yes or no? Did we have a free delivery, yes or no? On those days, how many people made a purchase and how many people didn't? And the same with the 3 days of the week. Was it a weekday, a weekend, a holiday? And did they buy, yes or no? As we dig in deeper to this table for our Bayes theorem, let the event buy be A. Now remember, when we looked at the coins, I said we really want to know what the outcome is. Did the person buy or not? And that's usually event A is what you're looking for. And the independent variables, discount, free delivery, and day, be B. So we'll call that probability of B. Now let us calculate the likelihood table for one of the variables. Let's start with day, which includes weekday, weekend, and holiday. And let us start by summing all of our rows. So we have the weekday row, and out of the weekdays there's 9 plus 2, so it's 11 weekdays. There's 8 weekend days and 11 holidays. Wow, that's a lot of holidays. And then we want to sum up the total number of days. So we're looking at a total of 30 days. Let's start pulling some information from our chart and see where that takes us. And when we fill in the chart on the right, you can see that 9 out of 24 purchases are made on the weekday, 7 out of 24 purchases on the weekend, and 8 out of 24 purchases on a holiday. And out of all the people who come in, 24 out of 30 purchase. You can also see how many people do not purchase. On the weekday, it's 2 out of 6 didn't purchase, and so on and so on. We can also look at the totals, and you'll see on the right we put together some of the formulas. The probability of making a purchase on the weekend comes out at 11 out of 30. So out of the 30 people who came into the store throughout the weekend, weekday, and holiday, 11 of those purchases were made on the weekday. And then you can also see the probability of them not making a purchase. And this is done for, doesn't matter which day of the week. So we call that probability of no buy. It would be 6 over 30 or 0.2. So there's a 20% chance that they're not going to make a purchase no matter what day of the week it is. And finally, we look at the probability of B if A. In this case, we're going to look at the probability of the weekday and not buying. 2 of the no buys were done out of the weekend out of the 6 people who did not make purchases. So when we look at that, probability of the weekday without a purchase is going to be 0.33 or 33%. Let's take a look at this at different probabilities, and based on this likelihood table, let's go ahead and calculate conditional probabilities as below. The first 3 we just did. The probability of making a purchase on the weekday is 11 out of 30, or roughly 36 or 37%, 0.367. The probability of not making a purchase at all, doesn't matter what day of the week, is roughly 0.2 or 20%. And the probability of a weekday no purchase is roughly 2 out of 6. So 2 out of 6 of our no purchases were made on the weekday. And then finally we take our P of AB. If you look, we've kept the symbols up there. We got P of probability of B, probability of A, probability of B if A. We should remember that the probability of A if B is equal to the first one times the probability of no buys over the probability of the weekday. So we could calculate it both off the table we created. We can also calculate this by the formula, and we get the 0.367, which equals, or 0.33 times 0.2 over 0.367, which equals 0.179, or roughly 17 to 18%. And that'd be the probability of no purchase done on the weekday. And this is important because we can look at this and say, as the probability of buying on the weekday is more than the probability of not buying on the weekday, we can conclude that customers will most likely buy the product on a weekday. Now, we've kept our chart simple and we're only looking at one aspect. So you should be able to look at the table and come up with the same information or the same conclusion. That should be kind of intuitive at this point. Next, we can take the same setup. We have the frequency tables of all 3 independent variables. Now we can construct the likelihood tables for all 3 of the variables we're working with. We can take our day like we did before. We have weekday, weekend, and holiday. We filled in this table. And then we can come in and also do that for the discount, yes or no. Did they buy, yes or no? And we fill in that full table. So now we have our probabilities for a discount and whether the discount leads to a purchase or not, and the probability for free delivery. Does that lead to a purchase or not? And this is where it starts getting really exciting. Let us use these 3 likelihood tables to calculate whether a customer will purchase a product on a specific combination of day, discount, and free delivery, or not purchase. Here, let us take a combination of these factors. Day equals holiday, discount equals yes, free delivery equals yes. Let's dig deeper into the math and actually see what this looks like. And we're going to start with looking for the probability of them not purchasing on the following combinations of days. We are actually looking for the probability of A equal no buy, no purchase. And our probability of B we're going to set equal to, is it a holiday? Did they get a discount? Yes. And was it a free delivery? Yes. Before we go further, let's look at the original equation. The probability of A if B equals the probability of B given the condition A and the probability times the probability of A over the probability of B occurring. Now this is basic algebra, so we can multiply this information together. So when you see the probability of A given B, in this case the condition is B, C, and D, or the 3 different variables we're looking at. And when you see the probability of B, that would be the conditions. We're actually going to multiply those 3 separate conditions out. Probability of, you'll see that in just a second in the formula, times the full probability of A over the full probability of B. So here we are back to this, and we're going to have let A equal no purchase, and we're looking for the probability of B on the condition A, where A sets for 3 different things. Remember that equals the probability of A given the condition B. And in this case, we just multiply those 3 different variables together. So we have the probability of the discount times the probability of free delivery times the probability is the day equal a holiday. Those are our 3 variables of the probability of A if B. And then that is going to be multiplied by the probability of them not making a purchase. And then we want to divide that by the total probabilities, and they're multiplied together. So we have the probability of a discount, the probability of a free delivery, and the probability of it being on a holiday. When we plug those numbers in, we see that 1 out of 6 were no purchase on a discounted day, 2 out of 6 were a no purchase on a free delivery day, and 3 out of 6 were a no purchase on a holiday. Those are our 3 probabilities of A if B. multiplied out. And then that has to be multiplied by the probability of a no purchase. And remember, the probability of a no buy is across all the data. So that's where we get the 6 out of 30. We divide that out by the probability of each category over the total number. So we get the 20 out of 30 had a discount, 23 out of 30 had a yes for free delivery, and 11 out of 30 were on a holiday. We plug all those numbers in, we get 0.178. So in our probability math, we have a 0.178 if it's a no buy for a holiday, a discount, and a free delivery. Let's turn that around and see what that looks like if we have a purchase. I promise this is the last page of math before we dig into the Python script. So here we're calculating the probability of the purchase using the same math we did to find out if they didn't buy. Now we want to know if they did buy. And again, we're going to go by the day equals a holiday, discount equals yes, free delivery equals yes, and let A equal buy. Now right about now you might be asking, why are we doing both calculations? Why would we want to know the no buys and buys for the same data going in? Well, we're going to show you that in just a moment, but we have to have both of those pieces of information so that we can figure it out as a percentage as opposed to a probability equation. And we'll get to that normalization here in just a moment. Let's go ahead and walk through this calculation. And as you can see here, the probability of A on the condition of B being all three categories. Did we have a discount with a purchase? Did we have a free delivery with a purchase? And is a day equal to holiday? And when we plug this all into that formula and multiply it all out, we get our probability of a discount, probability of a free delivery, probability of the day being a holiday, times the overall probability of it being a purchase, divided by, again multiplying the three variables out, the full probability of there being a discount, the full probability of being a free delivery, and the full probability of there being a day equal holiday. And that's where we get this 19 over 24 times 21 over 24 times 8 over 24 times the P of A, 24 over 30, divided by the probability of the discount, the free delivery times the day, or 20 over 30, 23 over 30 times 11 over 30, and that gives us our 0.986. So, what are we going to do with these two pieces of data we just generated? Well, let's go ahead and go over them. We have a probability of purchase equals 0.986. We have a probability of no purchase equals 0.178. So, finally, we have a conditional probabilities of purchase on this day. Let us take that, we're going to normalize it, and we're going to take these probabilities and turn them into percentages. This is simply done by taking the sum of probabilities, which equals 0.986 plus 0.178, and that equals the 1.164. If we divide each probability by the sum, we get the percentage. And so the likelihood of a purchase is 84.71%, and the likelihood of no purchase is 15.29%, given these three different variables. So if it's on a holiday, if it's with a discount and has free delivery, then there's an 84.71% chance that the customer is going to come in and make a purchase. Hooray! They purchased our stuff. We're making money. If you're owning a shop, that's is the bottom line, is you want to make some money so that you can keep your shop open and have a living. Now, I promised you that we were going to be finishing up the math here with a few pages. So we're going to move on and we're going to do two steps. The first step is I want you to understand why you want to use the naive Bayes. What are the advantages of naive Bayes? And then once we understand those advantages, we'll just look at that briefly, then we're going to dive in and do some Python coding. Advantages of naive Bayes classifier. So let's take a look at the 6 advantages of the naive Bayes classifier, and we're going to walk around this lovely wheel. It looks like an origami folded paper. The first one is very simple and easy to implement. Certainly you could walk through the tables and do this by hand. You got to be a little careful because the notations can get confusing. You have all these different probabilities, and I certainly mess those up as I put them on, is it on the top or the bottom? You got to really pay close attention to that. When you put it into Python, it's really nice because you don't have to worry about any of that. You let the Python handle that, the Python module. But understanding it, you can put it on a table and you can easily see how it works, and it's a simple algebraic function. It needs less training data, so if you have smaller amounts of data, this is a great, powerful tool for that. handles both continuous and discrete data. It's highly scalable with number of predictors and data points. So as you can see, you can just keep multiplying different probabilities in there, and you can cover not just 3 different variables or sets. You can now expand this to even more categories. Number 5, it's fast. It can be used in real-time predictions. This is so important. This is why it's used in a lot of our predictions on online shopping carts, referrals, spam filters, is because there's no time delay as it has to go through and figure out a neural network or one of the other many setups where you're doing classification. And certainly there's a lot of other tools out there in the machine learning that can handle these, but most of them are not as fast as the naive Bayes. And then finally, it's not sensitive to irrelevant features. So it picks up on your different probabilities, and if you're short on data on one probability, you can it automatically adjust for that. Those formulas are very automatic, and so you can still get a very solid predictability even if you're missing data or you have overlapping data for 2 completely different areas. We see that a lot in doing census and studying of people and habits, where they might have one study that covers one aspect and another one that overlaps, and because the 2 overlap, they can then predict the unknowns for the group that they haven't done the second study on, or vice versa. So it's very powerful in that it is not sensitive to the irrelevant features, and in fact you can use it to help predict features that aren't even in there. So now we're down to my favorite part. We're going to roll up our sleeves and do some actual programming. We're going to do the use case text classification. Now, I would challenge you to go back and send us a note on the notes below underneath the video and request the data for the shopping cart. So you can plug that into Python code and do that on your own time so you can walk through it, since we walked through all the information on it. But we're going to do a Python code doing text classification, very popular for doing the naive Bayes. So we're going to use our new tool to perform a text classification of news headlines and classify news into different topics for a news website. As you can see here, we have a nice image of the Google News, and then related on the right, subgroups. I'm not sure where they actually pulled the actual data we're going to use from. It's one of the standard sets. But certainly this can be used on any of our news headlines in classification. So let's see how it can be done using the naive Bayes classifier. Now we're at my favorite part. We're actually going to write some Python script. We'll roll up our sleeves. And we're going to start by doing our imports. These are very basic imports, including our news group. And we'll take a quick glance at the target names. Then we're going to go ahead and start training our data set and putting it together. We'll put together a nice graph, because it's always good to have a graph to show what's going on. And once we've trained it and we've shown you a graph of what's going on, then we're going to explore how to use it and see what that looks like. Now, I'm going to open up my favorite editor, or inline editor for Python. You don't have to use this. You can use whatever your editor that you like, whatever interface IDE you want. This just happens to be the Anaconda Jupyter Notebook. And I'm going to paste that first piece of code in here so we can walk through it. Let's make it a little bigger on the screen so you have a nice view of what's going on. And we're using Python 3, in this case 3.5. So this would work in any of your 3x. If you have it set up correctly, it should also work in a lot of the 2x. You just have to make sure all of the versions of the modules match your Python version. And in here, you'll notice the first line is your percentage matplot library in line. Now, 3 of these lines of code are all about plotting the graph. This one lets the notebook know, since it's an inline setup, that we want the graphs to show up on this page. Without it in a notebook like this, which is an Explorer interface, it won't show up. Now, a lot of IDEs don't require that. A lot of them, like if I'm working on one of my other setups, it just has a pop-up and the graph pops up on there. So you have that setup also. But for this, we want the matplot library inline. And then we're going to import NumPy as NP. That's NumberPython, which has a lot of different formulas in it that we use for both of our sklearn module. And we also use it for any of the upper math functions in Python. And it's very common to see that as NP, NumPy as NP. The next 2 lines are all about our graphing. Remember I said 3 of these were about graphing? Well, we need our matplotlibary.pyplot as PLT, and you'll see that PLT is a very common setup, as is the SNS, and just like the NP. And we're going to import Seaborn as SNS, and we're going to do the SNS.set. Now, Seaborn sits on top of pyplot, and it just makes a really nice heat map. It's really good for heat maps. And if you're not familiar with heat maps, that just means we give it a color scale. the term comes from the brighter red it is, the hotter it is in some form of data, and you can set it to whatever you want. And we'll see that later on. So you'll see that those 3 lines of code here are just importing the graph function so we can graph it. And as a data scientist, you always want to graph your data and have some kind of visual. It's really hard just to shove numbers in front of people and they look at it and it doesn't mean anything. And then from the sklearn.datasets, we're going to import the fetch 20 news groups. Very common one for analyzing, tokenizing words and setting them up and exploring how the words work and how do you categorize different things when you're dealing with documents. And then we set our data equal to fetch 20 news groups. So our data variable will have the data in it. And we're going to go ahead and just print the target names, data.target names. And let's see what that looks like. And you'll see here we have alt atheism, comp graphics, comp OS, MS, Windows.miscellaneous. And it goes all the way down to talk politics.miscellaneous, talk religion.miscellaneous. These are the categories they've already assigned to this news group. And it's called fetch 20 because you'll see I believe there's 20 different topics in here, or 20 different categories as we scroll down. Now, we've gone through the 20 different categories, and we're going to go ahead and start defining all the categories and set up our data. So we're actually going to go ahead and get the data all set up and take a look at our data. And let's move this over to our Jupyter Notebook, and let's see what this code does. First, we're going to set our categories. Now, if you noticed up here, I could have just as easily set this equal to data.target_names, because it's the same thing. But we want to kind of spell it out for you so you can see the different categories. It kind of makes it more visual so you can see what your data is looking like in the background. Once we've created the categories, we're going to open up a train set. So this training set of data is going to go into fetch 20 news groups, and it's a subset in there called train, and categories equals categories. So we're pulling out those categories that match. And then if you have a train set, you should also have the testing set. We have test equals fetch 20 news groups, subset equals test, and categories equals categories. Let's go down one size so it all fits on my screen. There we go. And just so we can really see what's going on, let's see what happens when we print out one part of that data. So it creates train, and under train it creates train.data, and we're just going to look at data piece number 5. And let's go ahead and run that and see what that looks like. And you can see when I print train.data number 5 under train, it prints out one of the articles. This is article number 5. You can go through and read it on there. And we can also go in here and change this to test, which should look identical because it's splitting the data up into different groups, train and test. And we'll see test number 5 is a different article, but it's another article in here. And maybe you're curious and you want to see just how many articles are in here. We could do length of train.data. And if we run that, you'll see that the training data has 11,314 articles. So we're not going to go through all those articles. That's a lot of articles. But we can look at one of them just so you can see what kind of information is coming out of it and what we're looking at. And we'll just look at number 5 for today. And here we have it. Rewording the Second Amendment IDs, VTT, lines 58, in article, etc. And you can scroll all the way down and see all the different parts to there. Now, we've looked at it, and that's pretty complicated when you look at one of these articles to try to figure out how do you weight this. If you look down here, we have different words, and maybe the word from. Well, from is probably in all the articles, so it's not going to have a lot of meaning as far as trying to figure out whether this article fits one of the categories or not. So trying to figure out which category it fits in based on these words is where the challenge comes in. Now that we've viewed our data, we're going to dive in and do the actual predictions. This is the actual naive Bayes. And we're going to throw another model at you, or another module at you here in just a second. We can't go into too much detail, but it deals specifically working with words and text and what they call tokenizing those words. So let's take this code and let's skip on over to our Jupyter Notebook and walk through it. And here we are in our Jupyter Notebook. Let's paste that in there. And I can run this code right off the bat. It's not actually going to display anything yet, but it has a lot going on in here. So at the top, we had the print module from the earlier one. I didn't know why that was in there. So we're going to start by importing our necessary packages. And from the sklearn features extraction.txt, we're going to import tf-idf vectorizer. I told you we're going to throw a module at you. We can't go too much into the math behind this or how it works. You can look it up. The notation for the math is usually tf.idf. And that's just a way of weighing the words. And it weighs the words based on how many times they're used in a document, how many times or how many documents they're used in. And it's a well-used formula. It's been around for a while. It's a little confusing to put this in here, but let's let it know that it just goes in there and weights the different words in the document for us. That way we don't have to wait. And if you put a weight on it, if you remember I was talking about that up here earlier, if these are all emails, they probably all have the word from in them. From probably has a very low weight. It has very little value in telling you what this document's about. Same with words like in article, in articles, in, cost of, un, maybe cost might, or where words like criminal, weapons, destruction, these might have a heavier weight because they describe a little bit more what the article's doing. Well, how do you figure out all those weights in the different articles? That's what this module does. That's what the TF-IDF vectorizer is going to do for us. And then we're going to import our sklearn.naive Bayes, and that's our multinomial NB. Multinomial naive Bayes. Pretty easy to understand that, where that comes from. And then finally we have the Sklearn pipeline import make pipeline. Now, the make pipeline is just a cool piece of code because we're going to take the information we get from the TF-IDF vectorizer and we're going to pump that into the multinomial NB. So a pipeline is just a way of organizing how things flow. It's used commonly. You probably already guessed what it is if you've done any businesses. They talk about the sales pipeline. If you're on a work crew or a project manager, you have your pipeline of information that's going through, or your projects and what has to be done in what order. That's all this pipeline is. We're going to take the TF-ID vectorizer and then we're going to push that into the multinomial NB. Now, we've designated that as the variable model. We have our pipeline model. And we're going to take that model, and this is just so elegant. This is done in just a couple lines of code. Model.fit. And we're going to fit the data, and first the train data, and then the train target. Now, the train data has the different articles in it. You can see the one we were just looking at. And the train.target is what category they already categorized that particular article as. And what's happening here is the train data is going into the TF-ID vectorizer. So when you have one of these articles, it goes in there, it weights all the words in there. So there's thousands of words with different weights on them. I remember once running a model on this and I literally had 2.4 million tokens go into this. So when you're dealing like large document bases, you can have a huge number of different words. It then takes those words, gives them a weight, and then based on that weight, based on the words and the weights, and then puts that into the multinomial NB. And once we go into our naive Bayes, we want to put the train target in there. So the train data that's been mapped to the TF-ID vectorizer is now going through the multinomial NB, and then we're telling it, well, these are the answers. These are the answers to the different documents. So this document that has all these words with these different weights from the first part is going to be whatever category it comes out of. Maybe it's the talk show or the article on religion, miscellaneous. Once we fit that model, we can then take labels and we're going to set that equal to model.predict. Most of the sklearn use the term .predict to let us know that we've now trained the model and now we want to get some answers. And we're going to put our test data in there because our test data is the stuff we held off to the side. We didn't train it on there and we don't know what's going to come up out of it, and we just want to find out how good our labels are. Do they match what they should be? Now, I've already run this through. There's no actual output to it to show. This is just setting it all up. This is just training our model, creating the labels so we can see how good it is, and then we move on to the next step to find out what happened. To do this, we're going to go ahead and create a confusion matrix and a heat map. So the confusion matrix, which is confusing just by its very name, is basically going to ask how confused is our answer. Did it get it correct, or did it miss some things in there or have some missed labels? And then we're going to put that on a heat map so we'll have some nice colors to look at to see how that plots out. Let's go ahead and take this code and see how that, take a walk through it and see what that looks like. So back to our Jupyter notebook, I'm going to put the code in there, and let's go ahead and run that code. Take it just a moment. And remember, we had the inline, that way my graph shows up on the inline here. And let's walk through the code and then we'll look at this and see what that means. So, make it a little bit bigger. There we go. No reason not to use the whole screen. Too big. So we have here, from sklearn metrics, import confusion matrix. And that's just going to generate a set of data that says the prediction was such, the actual truth was either agreed with it or is something different. And it's going to add up those numbers so we can take a look and just see how well it worked. And we're going to set a variable mat equal to confusion matrix. And we have our test target, our test data that was not part of the training. Very important in data science, we always keep our test data separate. Otherwise, it's not a valid model if we can't properly test it with new data. And this is the labels we created from that test data. These are the ones that we predict it's going to be. So we go in and we create our SN heat map. The SNS is our seaborne, which sits on top of the pie plot. So when we create a SNS.heatmap, we take our confusion matrix, and it's going to be mat.t. And do we have other variables that go into the SNS.heatmap? We're not going to go into detail what all the variables mean. The annotation equals true. That's what tells it to put the numbers here. So you have the 166, the 1, the 0001. Format D and C bar equals false have to do with the format. If you take those out, you'll see that some things disappear. And then the X tick labels and the Y tick labels, those are our target names. And you can see right here, that's the alt atheism, comp graphics, comp OS, MS, Windows, miscellaneous. And then finally, we have our plt.x label. Remember, the SNS, or the seaborne, sits on top of our matplot library, our PLT. And so we want to just tell it x label equals a true is true. The labels are true, and then the y label is prediction label. So when we say a true, this is what it actually is, and the prediction is what we predicted. And let's look at this graph, because that's probably a little confusing the way I rattled through it. And what I'm going to do is I'm going to go ahead and flip back to the slides, because they have a black background they put in there that helps it shine a little bit better so you can see the graph a little bit easier. So in reading this graph, what we want to look at is how the color scheme has come out. And you'll see a line right down the middle, diagonally, from upper left to bottom right. What that is if you look at the labels, we have our predicted label on the left and our true label on the right. Those are the numbers where the prediction and the true come together. And this is what we want to see, is we want to see those lit up. That's what that heat map does. As you can see that it did a good job of finding those data. And you'll notice that there's a couple of red spots on there where it missed. You know, it's a little confused when we talk about talk religion miscellaneous versus talk politics miscellaneous, social religion Christian versus alt atheism. It mislabeled some of those. And those are very similar topics, so you could understand why it might mislabel them. But overall, it did a pretty good job. If we're going to create these models, we want to go ahead and be able to use them. So let's see what that looks like. To do this, let's go ahead and create a definition, a function to run. And we're going to call this function, let me just expand that just a notch here. There we go. I like mine in big letters. Predict categories. We want to predict the category. We're going to send it S, a string. And then we're sending it train equals train. We have our training model. And then we had our pipeline, model equals model. This way we don't have to resend these variables each time. The definition knows that because I said train equals train, and I put the equal for model. And then we're going to set the prediction equal to the model.predictS. So it's going to send whatever string we send to it. It's going to push that string through the pipeline, the model pipeline. It's going to go through and tokenize it and put it through the TF, IDF, convert that into numbers and weights for all the different documents and words, and then it'll put that through our naive Bayes. And from it, we'll go ahead and get our prediction. We're going to predict what value it is. And so we're going to return train.targetNamesPredict of 0. And remember that the train.targetNames, that's just categories. I could have just as easily put categories in there .predict of 0. So we're taking the prediction, which is a number, and we're converting it to an actual category. We're converting it from, I don't know what the actual numbers are, but let's say 0 equals alt atheism. So we're going to convert that 0 to the word, or 1, maybe it equals comp graphics. So we're going to convert number 1 into comp graphics. That's all that is. And then we got to go ahead and then we need to go ahead and run this. So I load that up. And then once I run that, we can start doing some predictions. I'm going to go ahead and type in predict category. And let's just do predict category Jesus Christ. And it comes back and says it's social, religion, Christian. That's pretty good. Now note, I didn't put print on this. One of the nice things about the Jupyter Notebook Editor and a lot of inline editors is if you just put the name of the variable out as returning the variable train.target_names, it'll automatically print that for you. In your own IDE, you might have to put in print. Let's see where else we can take this. And maybe you're a space science buff. So how about sending load to International Space Station? And if we run that, we get science space. Or maybe you're a automobile buff. And let's do, they were going to tell me Audi is better than BMW, but I'm going to do BMW is better than an Audi. So maybe you're a car buff. And we run that, and you'll see it says recreational. I'm assuming that's what REC stands for. Autos. So I did a pretty good job labeling that one. How about if we have something like a caption running through there? President of India. And if we run that, it comes up and says talk, politics, miscellaneous. So when we take our definition or our function and we run all these things through, kudos, we made it. We were able to correctly classify texts into different groups based on which category they belong to using the naive Bayes classifier. Now, we did throw in the pipeline, the TF idea vectorizer. We threw in the graphs. Those are all things that you don't necessarily have to know to understand the naive Bayes setup or classifier. But they're important to know. One of the main uses for the naive Bayes is with the TF IDF tokenizer or vectorizer, where it tokenizes the word and adds labels. And we use the pipeline because you need to push all that data through, and it makes it really easy and fast. You don't have to know those to understand naive Bayes, but they certainly help for understanding the industry and data science. And we can see our categorizer, our naive Bayes classifier. We were able to predict the category religion, space, motorcycles, autos, politics, and properly classify all these different things we pushed into our prediction and our trained model.
Most of you must be using Snapchat to apply filters on your photos. But do you know how Snapchat recognizes your photo on the screen and puts filters on it? Even if there are multiple faces on the photo, it applies filters in the appropriate position. Snapchat actually does this using a technique called facial recognition, which in turn uses machine learning. The machine learning algorithm detects the features on your face, like the nose, the eyes, and it knows where exactly your eyes are, where exactly your nose is, and accordingly it applies the filters. We will take a few more examples as we move along and try to understand how machine learning algorithms can be applied to solve some of our real-life problems. So what will you learn from this video? We will talk about some real-world applications of machine learning. We will also see and understand what exactly is machine learning and how it works. We will also see the process involved in machine learning, the types of machine learning algorithms, and we will also see a few hands-on, including some code, Python code, of the following algorithms: linear regression, logistic regression, decision tree and random forest, and k-nearest neighbors. Okay, so let's get started. So let's consider some of the real-world applications of machine learning. It's no longer just a buzzword. Machine learning is being used in a variety of industries to solve a variety of problems. Facial recognition is one of them. It's becoming very popular these days for security, for police, for solving crime. A lot of areas facial recognition is being used. Voice recognition is another area. It's becoming very common these days. Some of you must be using Siri. That's an example of machine learning and voice recognition. Healthcare industry is another big area where machine learning is adopted in a very big way. As you all may be aware, diagnostics needs analysis of images, let's say like X-ray or MRI, and increasingly because of the shortage of doctors, machine learning and artificial intelligence is being used to help and support doctors in analyzing these images and identifying the advent of any diseases. Weather forecast is another area. And in fact, Netflix has actually come up with a very interesting use case. You all must be aware of the House of Cards show on Netflix. So they did an analysis on their customer behavior. They got data of their 30 million customers, information about where they pause, where they fast forward a video, and they used this information. They provided this information to their playwrights and told them that this is what we want. This is what our audience is looking for. These are the areas that interest them, and these are the areas where they get bored. And the playwrights wrote the scripts accordingly. This is really, really interesting, and it actually brings a new era. So, what is machine learning? Machine learning is a science of making computers learn and act like humans. So here, when we say computers, very often what comes to our mind is writing a piece of code or program and telling the computer step by step what to do. But in machine learning, we don't do that. The system learns on its own. We just provide past data, historical data, what we call as labeled data, and the system learns. During the process, what is known as training process, we tell the system whether the outcomes are right or wrong, and that feedback is taken by the system and it corrects itself, and that's how it learns till it gives the correct output for most of the cases. Obviously, it won't be 100% correct, but the aim is to get as accurate as possible. So let's take you through step-by-step process of machine learning. The first step in machine learning is data gathering. Machine learning needs a lot of past data, especially we will see a little later, supervised learning. We will see what that is in a little while, but that's the most common form of learning. So the first step there is data gathering. You need to have sufficient historical data. Then the second step is pre-processing of this data so that this can be used for the machine learning process. The raw data cannot be used directly, so it needs to be pre-processed before it is fed into the machine learning system. The next step is to choose a model. So what kind of algorithm and what kind of model within that algorithm are we going to use? And then we need to train this model. So before training the model, it's just like a blank model, and after training it becomes a trained model. And once we train the model, we need to also test it to make sure it is predicting correctly. It's working fine with minimum errors. And subsequently it will be deployed, and once again it may have to be tuned from time to time or fine-tuned from time to time to improve the accuracy and so on and so forth. After training the model, we have to test the model. And during testing, we may find out that the accuracy is not good enough, so we may have to tune the model, we may change some parameters and run through this process once again, perform the training once again. So it can be an iterative process. And once the model is ready, then we deploy it to do the predictions. What are the different types of machine learning algorithms? Machine learning algorithms are broadly classified into three types: the supervised learning, the unsupervised learning, and reinforcement learning. Supervised learning in turn consists of techniques like regression and classification, and unsupervised learning, we use techniques like association and clustering. And reinforcement learning is a recently developed technique, and it is very popular in gaming. Some of you must have heard about AlphaGo. So this was developed using reinforcement learning. Primary difference between supervised learning and unsupervised learning. Supervised learning is used when we have historical data and we have labeled data, which means that we know how the data is classified. So we know the classes if we are doing classification, or we know the values when we are doing regression. So if we have historical data with these values, which are known as labels, then we use supervised learning. In case of unsupervised learning, we do not have past labeled data, historical labeled data. So we use techniques like association and clustering to maybe form clusters or new classes maybe, and then we move from there. In case of reinforcement learning, the system learns pretty much from scratch. There is an agent and there is an environment. The agent is given a certain target and it is rewarded when it is moving towards that target, and it is penalized if it is moving in a direction which is not achieving that target. So it's more like a carrot and stick model. So what is the difference between these three types of algorithms? Supervised algorithms or supervised learning algorithms are used when you have a specific target value that you would like to predict. The target could be categorical, having two or more possible outcomes or classes, if you will. That is what is classification. Or the target could be a value which can be measured. And that's where we use regression. Like for example, weather forecasting, you want to find the temperature. Whereas in classification, you want to find out whether this is a fraud or not a fraud, or if it is email spam, whether it is spam or not spam. So that is a classification example. So if you know, or this is known as labeled information, if you have the labeled information, then you use supervised learning. In case of unsupervised learning, we have input data, but we don't have the labels or what the output is supposed to be. So that is when we use unsupervised learning techniques like clustering and association, and we try to analyze the data. In case of reinforcement learning, it allows the agent to automatically determine the ideal behavior within a specific context. And it has to do this to maximize the performance. Like for example, playing a game. So the agent is told that you need to score the maximum score possible without losing lives. So that is a target that is given to the agent. And it is allowed to learn from scratch, play the game itself multiple times, and slowly it will learn the behavior which will increase the score and keep the lives to the maximum. That's an example of reinforcement learning. So we will discuss about some of the most popular algorithms in machine learning. A few of them are listed here. This is by no means an exhaustive list. There are really a lot of algorithms available out there, but these are some of the most common ones. What are these algorithms? Linear regression, logistic regression, decision tree, random forest, and k nearest neighbors. So let's look at each of these in detail. Linear regression. A little history about linear regression. Sir Francis Galton is credited with the discovery of the linear regression model. So what he did was he started studying the heights of father and son to predict the son's height or the child's height even before he or she is born. So he collected enough data of the heights of father and the respective sons. He plotted this data on the x and y axis, and he drew a line in such a way that the distance of these points from the line was the least, which is now what we call it as mean square error. So at that time this term was probably not there, but that's what he did. And then he was able to use this line to predict the height of the child which was yet to be born based on the height of the father. So that was the very beginning or very initial phase of linear regression algorithm. So that was a little bit of history, but what is linear regression? So linear regression is a way of modeling a linear model, creating a linear model to find the relationship between one or more independent variables denoted by x and a dependent variable which is also known as the target and denoted as y. A few examples are shown here. Let's say we are going to plot the sales of ice cream and the temperature. So temperature on the x-axis and the sales on the y-axis, and this is how the data would look. And if we draw a line in such a way that the distance of each of these points from this line is minimum, that is known as a regression line or the best fit line. So regression is all about finding this line. And it is called linear regression because it is a straight line, linear, and the equation doesn't have any non-linear component, which means we do not have x to the power of 2 or 3 or any of this. So this is simple linear regression, and simple linear regression is when there is only one independent variable. So there is only one x. So that is simple linear regression. So let's see how this is actually done. So linear regression is all about finding the best fit line, and the way it is done is in a recursive manner. So first a random line is drawn and the distance is calculated from this line of all the points, as you can see in this example, and that distance is known as the error. And to ensure that there are no negative values, this is squared. So we actually take the square of the distance of the point from the line and add it up, and we make sure that at the end this sum, which is known as the sum of squared errors, is the minimum. So as you can see, this is where we start, and then we keep changing the line in such a way and calculate the distance once again, the sum of the squares once again, and here again you will see that this is probably not minimum. And we keep changing this until we get a line where this value is minimum. So here we find that the sum of the squares of the distance, which is also the sum of squared errors, capital D, denoted by capital D, is minimum. So now we found the best fit regression line. So this is a recursive process, it's an iterative process, and this is what behind the scenes, this is what happens when we try to do linear regression. Now we'll take an example of a linear regression, and we will actually demonstrate this using Python, and we will be using Jupyter Notebook for this. In case you're familiar with Jupyter Notebook, I think that would be very helpful, and if you need the data set, please put a comment under this video so that we can provide you with the data set. Before we go there, just let's try to understand what this example is all about. Let's say there is a new joinee joining the company, and we want to determine what should be the pay or the salary for this new joinee. And for that, we already have the labeled data, which is the details of our employees based on their years of experience and their salaries. And for the new joinee, we have the experience, and we need to determine what should be the salary. So let's take a look at the demo. So before we go into the Jupyter Notebook, let's quickly review the code, what the code is doing. The first section is about importing the libraries. Some of you who are familiar with Python will already be knowing this. We don't have to go into details. And then we import the data set, and then we visualize the data just to get a quick idea about how the data is looking. And then we split the data into training and test data sets. This is a common procedure in machine learning process, any machine learning process. And the overall training and test process we do with two different data sets. So that's what we're doing here. And then we build or train our model, the linear regression model. And then we do the testing, and we find out what is the errors and visualize our results. And this is how the test results look, and this is how the training result looks. All right, and then we calculate the residuals. Residuals are nothing but the errors. There are a couple of ways of measuring the accuracy. The root mean square error is the most common one, RMSE, and in this case we got root mean square error of 58, which is pretty good, and that's our best fit. Alright, so now let's go into Jupyter Notebook and take a look at by running it live. Okay, so this is our code for the linear regression demo, and this is how the Jupyter Notebook looks, and this code in the Jupyter Notebook looks. I will walk you through the code pretty much line by line, and let's see how this works, the linear regression. So the first part is pretty much a standard template in pretty much all our code we will see. This is importing the required libraries. So NumPy is a library, Matplotlib is a library, pandas, and so on. So these libraries are required. Each of these libraries have a different purpose. So some of them are required for manipulating your data, some for plotting, as the name suggests, Matplotlib, and so on and so forth. Okay, so let's go ahead and import all these libraries, and then we will import our data. So in this example, what we are trying to do, the use case in this particular example is we have some historical value of salary data, and now we want to build a model so that we can predict the salary for new employee, a person who is joining new, and we will use the characteristics that were available to us, or the features that were available to us, and we will try to predict what will be this salary of this new person. Okay, so that's the kind of the use case. So let's go ahead and load the data, and let me introduce a cell and see how the data looks. So salary underscore data. So we have basically two features, right? So it's pretty much like a simple linear regression we are trying to do. So we have years of experience and salary, and in this case what we are trying to do is this is our predictor. So years of experience is our predictor, and we are trying to predict what the salary would be. So once again, so X is what is known as the predictor and Y is the target. So number of years of experience we are taking as input, and we will try to find what will be the salary of this person based on that. Okay, so that's what we are going to do. So I have shown what is how the overall how the data that has been imported looks. Now let's take a quick look at these extracted values or extracted columns as well. So let me put in X here and see how it looks. So there's basically one column, and same way if we put Y here, we will see what exactly, I'm sorry, this has to be in small lowercase. So this is the salary information. Okay, so this is how our data is, and then we can do a little bit of plotting of the data to play around a little bit, because we imported the data. Typically we want to do some exploratory analysis, how they compare with each other and so on and so forth, how they are correlated. So let's draw a quick plot, a bar plot, and see how the years of experience are being seen here, right? So this is how the bar plot looks. Similarly, let's do one more, which is basically more like this is horizontal bar plot. Okay, so how many people and with what experience and so on and so forth. So what this shows is the count, how many records are there with a given experience and things like that. Okay, so this is another way of visualizing the data, and this is a third view, and this is one more view, and then we can do a quick heat map. So there's only one, or actually there are only two variables, so there's not a lot of plotting that we can do, or not a lot of visualization that we can do, since there are only two variables. But nevertheless, whatever is possible, we can do a quick to get a quick idea about how the data is looking and how the variables are related to each other. Is there a correlation and things like that? All right, so once we are done with that, this is the most important part of our demo here, which is basically this is the beginning of our training process. So the first thing before we start the model building and model training process is to split the data into training and test data sets. Okay, now whenever we do any machine learning exercise, especially supervised learning, we never use the entire labeled data for training purpose. The reason being, then we will not be able to correctly evaluate how well the training has happened. Okay, so what we do is we split the data, we take a portion of the data, we call that as the training data set, and we set aside some portion of the data, we call that as the test data set. We use the training data set to actually perform the training, to train our model, and once that is done, we use the test data set to check how well the model has been trained, how accurately it is able to predict. Okay, now the reason is with our test data set also, since that is also labeled, we allow the model to predict the values, and we compare it with the labeled information to see whether it has predicted correctly or not. Okay, so that is the reason in all machine learning activities, whenever we perform machine learning, especially training of a model, we split this data into training and test data set, and that's what we are going to do here. Now there is no need to write any separate code for that. There is a readily available function for that, train _ test _ split. So that's what we are going to use here. It takes the data set, the X and Y is the data set, and in addition it takes a parameter which tells how the data has to be split. So for example, here it says test size is equal to 1/3. That means it is 33%, right? 33.33%. So 1/3 of the data you want to set aside for test. Now there are no hard and fast rules as to what should be the split of test and training data set. It is a matter of individual preferences. Some people would like to have 50-50, some people would prefer 80-20, and so on and so forth. So it is completely up to the individuals to decide on that. So in this particular case, what we are doing is we are setting aside 1/3 of the data set for testing purpose and 2/3 of the data set for training purpose. Okay, so that's exactly what we are doing here. Now the next step is to create an instance of linear regression. So linear regression model is readily available. So we create an instance of the linear regression model and give it a name like LR, and then we call the fit method of the linear regression model. Now this fit method is common across all the algorithms. So any algorithm you use, if you want to start the training process, you call the fit method. Okay, and then we pass the training data set. Now training data set, we send the predictor, as I was saying, or the independent variable, and also the dependent variable. We pass both of them. Okay, and the system will basically learn based on this. So now the training has happened, training is completed, and now we need to see whether it is predicting correctly or not. We need to test it, right? So for testing, we have another method called predict. Again, this is common across all algorithms. Any algorithm you use, you will have this predict method for testing your model, okay, or for actually predicting the values, whether during testing or when you actually deploy the model. Okay, now here predict will take only one parameter, which is the independent variables, right? The reason being, the dependent variable is what it will predict, right? So y underscore test we don't have to pass, whereas here y underscore train we passed for training purpose, but y underscore test we do not pass because that is what the model will predict, so we don't have to pass that. And then the model will predict, and that is what we call it as y underscore pred, but we will use y underscore test to compare with what the model has predicted, and thereby we can determine how accurate the model is. Okay, so let me go ahead and run this code. So it has done with the testing or with the prediction of the values. So these are the predicted values, and now we can visualize, we can generate some plots to visualize this information. So let's plot this training set results information and see how it looks. So what we are doing here is basically we have the training data set plotted, the salary versus the years of experience, right? This is the training data, the dots basically. And then this line is what our model has. So this is the best fit. So linear regression, what is linear regression process? We find a equation of a line which is the best fit. So our model, this is the equation, or this is the line that our model has kind of come up with, saying that this is the best fit model. Okay, so as you can see, intuitively it feels okay because it is passing through pretty much the middle of our data set. Okay, so this is for the training part. Now we do the same for our test as well, and see how it is doing, or how it looks. Here also it looks pretty good because the line passes pretty much in the middle of the overall data set. That's what we are trying to do here. All right, and then how do we measure the accuracy? So these residuals are nothing but the errors. The term residuals is nothing but the errors we have seen in the slides as well. So we calculate the accuracy of our model by calculating the various residuals. We have like mean square error, then we have the mean absolute error, and then we have the root mean square error. They are very closely related. This is nothing but the error and the actual value, right? So for example, let me explain with this particular line. So what our model says is, if the value of the years of experience, right? So let me take this point maybe. If the value of the years of experience is 4, then the salary will be, according to our data, that salary probably should be, what is this, maybe around 58,000, right? And there are of course 3 data points pretty much around this 4 years experience. One may be around 58, or in fact 2 of them are around 58, and there is one more which is probably 60. Okay, now these are the 3 data points, whereas our model predicts that if the years of experience is 4, then the salary should be 60,000, let's say. Okay, let's assume this goes to 60,000, which means that one of the data points is very accurately predicted by our model, but there are 2 of them which are off. So there is an error for these 2 values. And what is that error? The error is nothing but the distance of this point from this line. Right, the distance of this point of each of these data points from the line is the error. Okay, so that's basically for each of the values it will correct, so it will calculate rather, and instead of taking the absolute value, we kind of take a square of that. So because the value can be positive or negative, so in order to avoid a cancellation, so there are some positive values, there are some negative values, and they get cancelled out, what we do is we take a square of that. So that is basically what is the root mean square, or the mean square error. And then if we take a square root of that, it becomes root mean square error, right? So this was explained probably in the slides as well. So that is what we will calculate here, and we print it Okay, and these values, the root mean square error, the mean squared error, and the mean absolute error, the lower these values are, the better. So the accuracy is higher if these values are lower. So in a way it is inversely proportional. Okay, so that's the way we measure the accuracy of our linear regression model. All right, so that brings us to the end of this demo, and we will continue with the other demos. All right, now that we have seen linear regression, let's take a look at our next machine learning algorithm, which is logistic regression. Now, what's interesting about this algorithm is that while it says regression, the name has regression in it, but keep in mind this is not used for regression, but this algorithm is used for classification. Now, many people get confused by this name, so you need to be aware of it. Linear regression is used to solve regression problems where we are trying to predict a value, whereas logistic regression is used to solve a classification problem. So we are trying to find, for example, whether a person will repay the loan or not, or whether we want to find whether this image is of a cat or a dog. So this is a classification problem. Okay, so just that you should be aware of the name. So in this slide, we are talking about whether a person, credit card user or credit card holder, will default on the payment. So we can create a profile. We have historical data and of people, their income and their credit card balance, and we have examples of people who have defaulted and people who have not defaulted, and based on that we let the system learn to predict this particular value, whether the person will default on the payment or not. Now, how does the logistic regression work? If we try to draw a straight line to determine the probability, so we are trying to predict whether this person will default or not. Okay, so if we draw a straight line, then the predicted value can exceed 0 and 1, which is not a good idea. So the probability is calculated between 0 and 1 using what is known as a sigmoid curve. So it is not a straight line, but we use a different formula, a different mechanism to find the probability and find the value between 0 and 1. And the formula for that is P is equal to 1 by 1 plus e to the power of minus z. Here, z is actually the linear equation that we used in figure 1, which is m1x plus c0. So this is fed to P and the value is calculated between 0 and 1. And we will see actually mathematically, you will see here that if z is negative and much higher, a very high value, the equation will be 1 by 1 plus 0, which is equal to 1. So we will see here that if the value of z is positive and it is some high number, then the value of P can at the most be equal to 1, because this portion here is 1 by a very high number, let's say infinity. So 1 by infinity is 0, so this whole thing becomes 1 by 1, so that is equal to 1. P is equal to 1. So that is where the maximum value it can achieve is 1. Similarly, if the value is negative, if the z value is negative or negative and very high value, then this will become very high and therefore the denominator will become infinity. So 1 by infinity is 0 and therefore P is equal to 0. So that's the way the sigmoid function works. This is how the graph looks, and there has to be a threshold value, which is like in this case 0.5. So if the value is greater than 0.5, we consider the output as 1, whereas if the value is less than 0.5, we consider the value as 0. Because remember, let me go back, in this case it doesn't exactly give us a 1 or a 0. Okay, so we need to keep that in mind. It doesn't give us exactly a 1 or a 0. It will give a value between 0 and 1, irrespective of what the value of z is. It will give us a value between 0 and 1. It's like the probability between 0 and 1. Now we have to have a threshold, and then based on what the value is, if the value is greater than 0.5, then we say okay, this probability is 1, and if the value is less than 0.5, the probability is 0. So we decide that based on the cutoff or a threshold value. So for example, if we continue on that, if a person having a balance of maybe this is 1750 50, then the probability that he will repay the loan is 0.2, which is less than 0.5, the threshold value which we have set. That means the probability is 0, which means the person will not repay. Whereas if the balance is somewhere in the range of 2250 maybe, which is this red dot, then the sigmoid function calculates the probability of default as 0.8, which means the output is 1, which means the person will default on payment. Okay, so that is how the logistic regression works. So in this case, it says that, okay, this person will default, so it is classified as a defaulter, in this case the second one, and in the first case it is a non-defaulter. So these are the two different classes of these two different cases. So let's move on and see how logistic regression is implemented. So this is another example of logistic regression. Can we predict whether a person is going to buy an SUV based on their age and their estimated salary? So these are our two inputs, and based on that, can we predict whether this person will buy an SUV or not? So this is a logistic regression problem. And we are going to demonstrate this using Python code and in Jupyter Notebook. And before going into Jupyter Notebook, let's take a look at how we go about solving this problem and how the code looks. So this is the implementation of logistic regression. This is the code, the Python code. I'll just take you very briefly at a high level what each parts are. So first section, of course, is importing the libraries, and then we import the data set, and within this data set we just take, for performing or for training our model, we only take the independent variables into one, create one vector, and then we extract the labels separately, and then we visualize our data. This is how the data looks. And then we split the data into training and test set like we did in linear regression, and we do some feature scaling as well, which improves the performance of our model, and then we train and test the model. So these are the test results, and we visualize the test results. So this is the visualization of the trained results. They look pretty good. The classification, they are reasonably accurately classified, the red dots and the green dots, and there are a few, of course, miscalculations or misclassifications, but by and large it looks pretty good. And this is the visualization of the test results. Again, looks pretty good. And then we evaluate our model, and this is what we'll be doing in the code as well. And for this we use what is known as confusion matrix. Now let's try to understand what this confusion matrix is. Now, I know the name itself is confusing, but actually it is very simple. Now once we predict these values and compare with the actual values, we can create or represent the results in the form of a matrix. So we have altogether 134 observations, and if we put it in a tabular form, the predicted values and the actual values. First of all, in order to identify whether our model is more accurate or less accurate, the criteria is that the values along the diagonal should be maximum. So for example, this is 79 and this is 38. The sum of these should be maximum. So what do we mean by that? That means that if we have a perfect model, then this sum will be equal to 134 and the values here will be 0. So that is an ideal perfect logistic regression model. That is of course very rare, but that is the aim. The sum of these numbers or the maximum numbers should be in the diagonal, and in the other cells there should be as less as possible. Okay, so here we see in this case that it is 79 plus 38, and so that is equal to 117. So 117 of them have been correctly predicted, which gives us an accuracy of 87%. So out of 134, 117 have been correctly predicted, and the 6 plus 11, 17 of them have been incorrectly. So this is 6 plus 11, 17 of them have been misclassified, so which is about 0.13%. So we have an accuracy of 87%. Okay, so I hope the way we calculate or the way we find accuracy from confusion matrix, I hope it is clear. By the way, once again, a quick reminder, if you need this data set to perform this on your own, please put a comment and under this video, and we will send you the data set. Alright, so let's go and check in Python Notebook how exactly this is done. Alright, so this is the demo of logistic regression. And here what we're doing is we've taken an example of a data set and a scenario where we will predict whether a person is going to buy an SUV or not. And we will use logistic regression for this. And the parameters we will take are, for example, the person's age, his salary, and a few other parameters. We will see very quickly what those are. Okay. So the first step, we import the required libraries. So that's what we are doing in this particular cell. Like, for example, NumPy, Matplotlib, Pandas. So for performing any preparation of the data before we actually launch into the learning process. And then we load the data. So let me just introduce one more cell and see how the data looks. So why don't we do that here? And if I say data set, and then if I run this is how our data looks. So these are the parameters or the features as we call it in machine learning language. We have gender, age, and estimated salary. User ID is also there, but it's not really a feature. It will probably not contribute, so we will not be using this. We will primarily be using these three columns, and in technical terms these columns are known as predictors, and then we have the labeled value. This is known as our target, and this is the labeled value, so it has 0 or 1. So we are basically performing a binary classification, 0 or 1, whether the person will purchase or not purchase. 0 means he will not purchase, 1 means he will purchase. Okay, and the other way of also looking at it is from a mathematical perspective. These are our independent variables. Gender, age, and estimated salary are our independent variables, and purchased is our dependent variables. So in our equation, like y is equal to something something m1x plus m2x and so on, this is our y. Okay, all right, so now let's move forward. What we will do next is to extract or separate out the independent variables and the dependent variables. How do we do that? So we load them into X, capital X and Y, and what we are doing here is we are taking the second and the third column. We are taking these three, right? So gender, age, and estimated salary. So that is what we are taking here, 2 up to 3. And then Y is basically the last column, which is the fourth column. So let's go ahead and extract that. And once again, why don't we take a look at how the data is looking? So let me just print X. So we are basically taking 2 and 3. So what is 2 and 3? 2 and 3 is our age and our estimated salary. Yeah, that's right. So these are the only two independent variables, and our dependent variable is obviously the last one, whether the person will buy or not. Okay, so we have the data loaded. Now that we have the data in Python, let's take a quick look at how the data looks. So in terms of visualization, let's visualize the data and perform a little bit of what is known as exploratory analysis, right? So as a data scientist, whenever you get new data, you just play around and see how the data is looking before you actually launch into the actual training or the modeling part of it. So let's run a small heat map and see how the data looks. So we have just passed the entire data set here, and this is how the heat map looks, how they are related, how the various features are related to each other. And this is a scale here. Very dark means basically there is pretty much no correlation. This is in a way to measure the correlation as well. And light means there is a very high correlation. So as you can see, a value or a feature will have very high correlation of 1 to itself. So the user ID, and this is user ID, it has a very high correlation to itself. Similarly, purchased and purchased it has. So the diagonal will be very high, so that is really not relevant. But then the other values is what we have to see. For example, there is a correlation of 0.6 in this area, which is basically if you take age and purchased, right? Whether the person has purchased and the age. So that's a quick look at exploring the data. So that's all we are doing here. Here's where the actual the crux of this code is. So from here onwards, what we do is the first step before we start the training process is split our data into train and test. Training data set and test data set. So whenever we perform any machine learning activity, we have, let's say, our labeled data. We never pass the entire data to the model, because when we are measuring the accuracy, whether the model is performing well or not, we will not be able to do that. If we use up the entire data for training purpose. So we split the data into what is known as a training data set. We train the model with the training data set, and then this test data set, which is kept separately, which the model has not yet seen, we use that to check whether it is able to perform the predictions correctly or not. Okay, that will give us a higher accuracy or a better estimate of how the model is doing. Alright, so this is a very common practice in machine learning. So whenever we perform training of the model, we split the data into training and test. Now, how do we do this? We don't have to write any special code. There is already a method available, which is train_test_split. And we just call this method. Only thing is, it takes these parameters and we have to specify especially this parameter, which tells the method how the data should be split. Now, when we are splitting the data into training and test, there are no hard and fast rules how we split this data. Some people prefer 50-50, some people prefer 80-20, and so on and so forth. So that is flexible, and it could be to some extent individual preferences. So in our case, we are splitting this data into 75-25, which means 75% of the data we will use for training, 25% we'll use for test. So that is what we are specifying here as a parameter. We say test_size is equal to 0.25. That means put or keep 25% of the data, set aside 25% of the data as test data, and therefore the remaining 75% will be used for training. Alright, so let's move on. I execute this. Then we perform what is known as feature scaling. So what is feature scaling? Usually what happens is the values that we have in the data, sometimes they can be some numbers will be very large, some will be very small. So there is a huge variation. So in order to, if we have that and if we use that as it is, the accuracy of our model may come down. So we have to somehow normalize these values. So that is what scaling does, feature scaling does. And again, we don't have to write any special code for this. There is a standard method available or standard class available called standard scaler. So we just create an instance of that and pass our data for scaling purpose. Okay, so let's go ahead and do that now. So this is all what we have done is more like a data preparation. So we chose what are the parameters, what features we want. We did the feature scaling and we split the data. Now everything is ready. Next is to start the actual training process. So this is the most crucial part of the code. So here, as we said, we will use the logistic regression model. So we have to create an instance of regression model. So I call that as classifier. You can give any name. And we just do some kind of a initialization, random value initialization. So we call this as random state, or we assign it as random state is equal to 0. And we have an instance of the logistic regression model. And we use that model, the fit method. So any algorithm that we have, when we want to perform the training, we have to use the fit method. Okay, we call the fit method. Now let's say instead of logistic regression, we are using k nearest neighbors algorithm. You will have k nearest neighbor dot fit, or linear regression dot fit, right? So that is the way it works. And we pass the training data set. The x is the independent variables and y are the labels. So we pass both of them for the training purpose. So once the training is done, we get the results of, or the model is trained. Okay, the model is trained. Now the next step is to test the model, how well the model is performing. This is where we use the test data set. We pass the test data set, and here there is another method that we have to use, that is known as the predict method. So again, this is a predict method is common across all algorithms that we have. So any algorithm we have to call the predict method for performing the test, or even when we deploy it, when new data comes in, we are trying to predict for new data set, we always use predict. Okay, so fit is only for training. Okay, then predict is used for testing and for the actual performance of the prediction. Now One thing we need to observe here again is we only pass the X part of it and not the Y part of it. So this can always, sometimes this can lead to confusion. When we are calling fit, we are passing X and Y. When we are calling predict, we are only calling X. The reason is the Y part is what the model will predict. So you don't have to pass the Y part. Right? So Y is what the model will predict for us. So you don't pass. Here we had to pass it because the model has to learn from the existing values. So that's why we had to pass label as well. But when we are testing it, the model will calculate this, and that's the reason we do not pass the Y value. Okay, so now when we run predict, it will calculate those values or find those values, and it will put it in y_pred, and that is what is being displayed here. And as you can see, the values can be either a 0 or 1, which means the person will buy the SUV, which is 1, which is a value of 1, or 0 means the person will not buy the SUV. Okay, now one more thing we need to remember is, while we have not passed the Y values or the labels to the system, but we have these labels available with us, right? Y_test is available with us. That is what we have to use to find out how accurate the system is. So it has given us the results. Now we will compare these results, which the system has predicted, with the actual values that we have, which is available in Y_test. So we will see how well, how that is done, how the accuracy is calculated in a little bit. Okay, now that the training is completed, we can go ahead and do some visualization of the training results. So let me execute this code and take a look in a form of a plot. So this is how the classification is done. So these are like the class, this is like the class boundary. The green color belongs to the class 1 and the red color belongs to class 0. And these dots indicate it has been misclassified. So some of them have been misclassified. So that's what we are seeing, some red dots in the green area and some green dots in the red area, right? Whereas if you, probably it's not very clear, but you can see here that there are also red dots in the red area and the green dots in the green area. So those are the data points which are correctly predicted, and these in the opposite locations are the ones that have been misclassified rather. Same for test as well. So test data set also, if we visualize, we plot, we will see something similar. But this also gives at a high level whether is that a major in a major way, are there major misclassifications, or there are only few here and there. It gives a little bit of an idea about the accuracy as well, but then that is not sufficient for us, right? So we have to quantify this accuracy. So how do we do that? We do this using what is known as confusion matrix. So it's a readily available method or a class which is there, and it takes two parameters, which is the, you remember I told you we will be using ytest. So this is where we will be using y_test, which is our labeled value or labeled data set, and this is what is predicted by our model. Okay, y_pred is predicted, are the predictions. Here, these are the values out here we saw. This is y_pred. Okay, so we pass these two parameters and we create a matrix, and this matrix is known as confusion matrix. Now, what is the significance of this? First thing is that the total number of values here is equal to the number of data sets in your test data. Okay, so let's go ahead and in the next cell, let me just add up these values. So 65 plus 3 plus 8 plus 24. So how many are there? There are 100 in number. So there are totally 100 observations in your test data set. That is the first point. Then the second point is the number in the diagonals, right? The total value in the diagonals, if that is a high, that indicates a higher accuracy. The higher that number is, the total in the diagonal, the higher the accuracy. Okay, and if we have quite a few numbers in non-diagonal locations, that means the accuracy is not very high. So here looks like the accuracy is pretty good. Now we can actually quantify the accuracy by using these numbers. So what we do is the sum along the diagonal we have to take and divide that by the total observation. So 65 plus 24 is what we have along the diagonal, and we have 100 observations. So 89 by 100 is our percentage. So we got about 90% accuracy for this particular model. Okay, so that brings us to the end of this demo, and we will move on to the next demo. Alright, so the next algorithm is decision tree and random forest. They are being taken together because they are very closely related. So what is a decision tree? Decision tree is another algorithm, and unlike logistic regression, which is only used for binary classification, decision tree can be used for classification as well as regression, even though it is more popular for classification. And it can be used to classify multiple classes as well, not just binary classification. So how does decision tree work? One of the good things about decision trees is that it is easy to represent and show how exactly it works, and therefore it is very easy to understand as well. Now let's take an example. Let's say a person receives a job offer and he needs to decide whether to accept the job offer or not. So we will use decision tree to come to the decision to accept or not to accept. So this is how, first of all, a decision tree looks. It is actually an inverted tree. So the root is at the top. Okay, so and that is known as the root node. The node where the tree starts is known as the root node, and then we have some inner nodes or decision nodes, and we have the nodes where we have a decision, either positive or negative. These are known as leaf nodes or terminal nodes. Okay, so we have the root node and we have leaf nodes or terminal nodes. There can be multiple of them, and in between we have decision nodes or internal nodes. There are different terms used, so need not be hung up by the exact terminology. Now let's say we have to use this decision tree to find out whether this person will accept the job offer or not. So first thing he considers is the salary. Is the salary greater than 60,000? If no, it's a clear decision, the offer will be rejected. So we reach a decision, therefore this is a leaf node. Now, if the salary is greater than 60,000, it is not a clear-cut decision because there are probably other factors based on which the decision needs to be made. For example, what is the commute time? If the commute time is greater than 1 hour, then the offer is rejected. Okay, so even though the salary is greater than 60,000, so this is again a leaf node. If the commute time is less than 1 hour, still it is not a confirmed decision because there are still a few other factors. For example, performance incentives. Are there sufficient performance incentives as a part of this offer? If no, then again the offer is rejected, and this is another leaf node. If yes, if there are sufficient performance incentives, then the offer is accepted. So this is another leaf node. By the way, keep in mind that these are all the leaf nodes. This is a leaf node, this is a leaf node, this is a leaf node, this is a leaf node. And they of course belong to different categories. In this case, it is still a binary classification. So this belongs to one class, which is accept offer, and these leaf nodes belong to a different class, which is reject offer. So let's take an example and see how we can solve this problem using decision tree. Let's say we have to implement a classification algorithm for kyphosis patient, and the problem is a bunch of kids have undergone a kyphosis surgery, and we need to predict whether kyphosis is present in them or not. And how can we do this using decision tree algorithm? So this is how the classification tree for kyphosis looks. So it starts with if the age is greater than 8.5. So this is how the decision tree looks. So the first criteria is the vertebra, the number on which the surgery has been performed. If it is greater than 8.5, then we need to perform further analysis and look at other criteria. If it is less than 8.5, it is clear that kyphosis is present. And if it is greater than 8.5, then we check whether the vertebra operated upon is greater than 14.5 or not. If it is greater than 14.5, then kyphosis is absent. If not, then the next criteria is the age. If the person's age is less than 55 years, then kyphosis is absent. But if it is greater than 55 years, then a further analysis is required to see if the person's age is greater than 111 years, which is, of course, almost impossible, but yes. So if If no, then there is no kyphosis. Then we check if the age is greater than 111 years, which means the person is between 55 and 111 years. If the person is between 55 and 111 years, that is this path, that means kyphosis is present, otherwise it is absent. So this is very easy to understand decision tree, and now what we are going to do is we are going to implement this in Python in our Jupyter notebook, and we have a data set that is available for this. And once again, if anyone wants this data set, please put a comment under this video and we will be more than happy to share the data set with you. Before we go into the Jupyter notebook, let's take a look at what the code is doing. What are the various sections of the code? So first one, of course, is loading the libraries as usual. Then we import the data and then extract the independent variables and then separate the labels, which is the dependent variable, and then we visualize the data. This is how it looks. And then we, as usual, split the data into training and test data sets and then perform the training of the decision tree. And then we test that model with our test data. And then, since this is a classification problem, we evaluate this model using the confusion matrix. Remember, we talked about this in the previous example as well. So this is the confusion matrix for this particular problem. And here you can see that 16 plus 3, 19 of them have been correctly predicted out of 25, which gives us a 64% accuracy. And this 4 plus 2, 6 of them have been misclassified. Just to recap once again, how do we determine from the confusion matrix whether this is accurate or not? The numbers in this diagonal should be maximum. So here we see that out of 25, n is equal to 25, which is the total number of observations. Out of 25, in this case, in this diagonal, we have 16 plus 3, 19 of the values are here. So that's the reason we feel there is good accuracy, which is 64%. They have been correctly classified. 64% of the observations have been correctly classified by this model, whereas 24% have been misclassified, which consists of this 4 plus this 2. So that's how we use the confusion matrix to determine the accuracy of our decision tree model. So let's go into the Jupyter notebook and take a look and run the code and see how it looks. So this is our Python notebook for decision tree, and I will take you through the code. Not line by line, of course, but we will see the blocks. As always, the first block is to import the required libraries like pandas and numpy and so on. And then we import the data. For this, we are using kyphosis.csv file. And then we extract the independent variables and then the dependent variable. Dependent variable is the target, which is our classification. And also we call it as the label data, whether this person individual has kyphosis or not. And then we will run a little bit of initial exploratory analysis on the data. So as a data scientist, whenever you get new data, you do that. So we plot age against whether the person has kyphosis or not. And then we plot the various parameters against each other. So for example, this is like age versus the number. And by the way, the data, how does the data look? Let's take a look at the data. This has primarily 3 columns, one attribute against the other. So for example, this is age versus the number, then number versus the start, and so on and so forth. So this is just to get a quick idea about the overall, how the overall data looks. So we can do a few more visualizations, like with respect to the age and the count, the number of vertebrae that have been operated upon. And the red color indicates kyphosis is absent and the blue color indicates kyphosis is present. So this is another view, and so on. So we can basically do as much of exploratory analysis we can, and then we start training our model. So this is where we split the data into training and test data set, like in all other machine learning examples earlier also. And we can visualize the data or just take a quick look at how the data looks. Just the first 4 or 5 entries here. If we do the head, that's what the head function does. And similarly, Y as well, we can take a look at how the target is looking. And then we can get into the training of the decision tree. So we train our model with the training data set using this fit method, and then we test whether the model is working fine or not using the test data set, and this is the result of our test data, and then we evaluate the model. And for evaluating, we use the confusion matrix. So just let's take a quick look at the confusion matrix and see what is the accuracy. So we get about 16, right? As I mentioned, the diagonal values is what matters. So we have 16 of them correctly identified out of 25. So that gives us about 62, I think 70% accuracy. So that is using a decision tree. Now, instead of decision tree, let's check what happens if we use random forest. So we use, let's say our forest consists of 100 trees, and we do the same. We train our model, and then with the test data set, we try to test the model. And here we see that we get 19 of them out of 25 correct. So that is a much better accuracy. So this is about 76%. So 19 out of 25 is 76% accuracy. And we saw by using the decision tree, we got only 64%. That is 16 by 25 was only 64%. So this is a quick demo of implementation of decision tree. So once we evaluate the model, the next thing we can do is what happens if we want to improve the performance. So that's where random forest comes into play. So instead of using a decision tree, what happens if we use a random forest? And what is a random forest? It's very similar to decision tree. Only thing is that instead of using one tree, we use a number of trees. That's why it's called a forest. So we use multiple trees, and we take like a average or a voting of all the trees for each observation, and we finally calculate or we finally classify each observation based on that. So in this case, it helps in improving the accuracy. So as we have seen here, if we take in decision tree, the accuracy now comes to 76%, right? In the previous case, it was only 64%. Using just the decision tree, now when we use random forest, the performance has improved to a good extent, and it has become 76%. So random forest usually helps in increasing the accuracy when we are using decision trees as our algorithm. Okay, the last algorithm is the k nearest neighbors algorithm. This is again a classification algorithm, and it is actually very simple and straightforward, very easy to understand as well. In this case, let's say we have historical data of heights and weights, and we also have the labels. So if the height and weight is in this range, these are cats, and if the heights and weights are in this range, these are dogs. So this is one class and this is another class. And now if we get a new point or new data set, and we find that for this particular animal, the height and weight, if we plot it, is here. So how do we determine whether it belongs to the cat class or the dog class? That is where the k here comes into play. So when we are using this algorithm, we need to specify what should be the value of k. So let's say we determine that the value of k is 3. So what we will do is we will find out the nearest three objects to this data point that we have. So let's go to the next slide here. Okay, and we define k as 3. So what happens? We find the nearest 3 objects to this data point, and then we find out what is the maximum number of items, which class the maximum number of items belong to. So in this case, there are 2 cats and there is 1 dog. Therefore, we determine that this new data point belongs to the cat class. Now what happens if we say k is equal to 7? In that case, these are the 7 data points which are nearest to this new data point. And now you see that instead of cats, dogs are more. So which means that now the point or this data or this new creature belongs to the class dog. So this is, while this is a slight drawback, but by trial and error, we should be able to find out the right value of k. And once we use that, that's how we train the model. Now let's use k nearest neighbors and take an example to solve one of our previous problems that we did using logistic regression. Whether a person is going to buy an SUV or not based on the age and estimated salary. So before we go into Jupyter Notebook, let's again take a quick look at the code. So what are the various sections in the code? As always, we import the libraries, we load the data set, we visualize the data, we split the data into training and test data set, we do some feature scaling, and then we train our model, and then we test our model. We visualize the training set results, and then we visualize our test results, and both of these seem to be looking pretty good. And then we evaluate our model using the confusion matrix. So remember, whenever we use a classification algorithm, the way to evaluate our model, to find out the accuracy of our model, is the confusion matrix. We have seen in logistic regression, we have seen in decision tree, and now in KNN as well. So in this case, once again, the total number of observations is 100, and we see that along the diagonal, which is the number we need to consider, there are 93 values, which means we achieve 93% accuracy, and a few of them, that is only 7 of them, are misclassified. So this is a pretty good accuracy compared to our previous example. So let's go and check how this looks in Jupyter Notebook. So this is my Python notebook for k-nearest neighbor implementation, and I will quickly walk you through this code. The first block is, as usual, we are importing the various libraries like NumPy, Pandas, and Matplotlib, and then we load the data set, and we split the data into training and test data sets, and then we do feature scaling, and then we start training our model. And here we are specifying k as 5. Okay, and now the data set is trained. Now we go and test it with our test data set. Then we evaluate the model, and here we get that as you can see in the diagonal, there are 73 entries. So total is 73, which means out of total of 80, 73 have been classified correctly, which is about 90% accuracy we are getting, and 7 of them have been misclassified. We can now visualize the training results. So these are the zeros and these are the ones. This is the training set. So there are a few, as you can see, misclassifications. The green ones in the red area and the red ones in the green area are the misclassified values. And same way we can visualize the results of the test data set as well. And here again we see there are a little bit of misclassification. And that brings us to the end of this Python notebook demo for KNN classification.
With that, we have reached the end of this session on Data Science Crash Course. Should you need any assistance on PPT and any other resources used in this session like code, documentation, etc., please let us know in the comment section below, and our team of experts will be more than happy to resolve all your queries at the earliest. Until next time, thank you for watching, stay safe, and stay tuned for more from
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.